on board still.
Welcome to Celestial Navigation Made Easy, Part 2. And tonight we'll be looking at the tables and pulling numbers out and showing you how to use the Nautical Almanac here and the sight reduction tables here. These are the two books that you need to work out a celestial sight and find your position. The Nautical Almanac tells you great information all about the stars and planets and the sun and the moon. It basically tells you the location of each star, each of the planets, the moon, and the sun for each day of the year and for each minute and second of each day. When you work out the numbers, when you interpolate, you can get the exact position for hours, minutes, and seconds of each day of the year. Now these tables, the Nautical Almanac, are year specific. So this is an older version, 1992. You have to use the year of your voyage, and so this gets replaced every year. However, the sight reduction tables are permanent. These last for always. And there's several different sight reduction tables. This one is HO publication 229, sight reduction tables. And these are used to do the final step, which allows you to get your problem onto a small chart. There's several versions of sight reduction tables. Here's another marine version. You can use either one of these. Once you understand the process, it doesn't really matter. It's easy enough to switch from one table to using a different set of tables. These are sight reduction tables, and this is HO publication number 214. This set of tables covers 10 degrees. This is latitude 20 to 29 degrees. So to cover all of the latitudes with 214, you need 9 tables. North and south are both included in here, north and south latitudes. Now 229, this is the newer set of sight reduction tables. They replaced 214, but they're both, you can use either one. These cover latitudes, this volume covers latitudes 45 through 60, so 15 degrees. So there are fewer of these volumes. 6 of these volumes cover all of the latitudes. However, you don't really need 6 volumes unless you're going to be an Arctic explorer. So you really just need the volumes that you'll be sailing in, maybe 2 or 3 volumes of the sight reduction tables. Okay, so let's see what we're going to be working on. How many? Oh, one other set of sight reduction tables that is another option. These are the air sight reduction tables, air navigation. And this is publication number 249, right up there. And these are fine too. They're a little less accurate though. There's only one volume for all the latitudes of air navigation tables. And there's a little bit more interpolation required. So it's not quite as easy to use these because there's a couple of extra steps. But once you understand the concept and the process and what you're doing, you'd be able to use the air sight reduction tables instead of the nautical ones. However, the nautical ones are a little bit easier, and so these are the ones we'll be talking about. We're talking about voyaging on your cruising boat by sea rather than by air. Now tonight we'll be doing looking at 5 different steps in doing a sight reduction. The first step is quite simple. Number 1. First step is going from local time or watch time to local time to Greenwich Mean Time. The only way to enter the nautical almanac and pull numbers out of the nautical almanac for the position of the sun and stars and moon and planets is to start with accurate Greenwich Mean Time, accurate within the second, to the second. So the first step is to correct watch time to local time to Greenwich Mean Time. We'll do that very quickly here. The second step is to correct from height sextant to height observed. There's several corrections in here. Height sextant is what you read off of your sextant. Height observed is an improved version of that, made with several corrections made to get to HO, height observed. Okay, number 3. Once we have the Greenwich Mean Time, we can enter the nautical almanac. And from the nautical almanac we'll be getting the declination. That's just another word, fancy word for latitude of the ground point of the body we're shooting, and we'll be getting the Greenwich hour angle, GHA, which is related to the longitude, is similar to the longitude of the ground point of the celestial body we're shooting. And then the fourth step, this will give us the position of the sun or the planet or the stars, the nautical almanac, in terms of latitude and longitude, or we call it declination and Greenwich hour angle. Fourth step, we'll enter the site reduction tables. And this step is what we were talking about as being the trick. The trick of getting your problem so it fits on a small chart instead of requiring a huge globe to work your site out. So the site reduction tables we'll enter, and we'll pull out the numbers we need to plot your final position on a small chart. And then the fifth step is plotting your position. We'll actually plot an LOP, a line of position. LOP from the site we took earlier. Okay, all of this can be done when you're working out a site, when you know how to do it. All of this can be done in between 10 and 15 minutes. So not a terribly difficult process. The big thing is understanding each step so you know exactly what you're doing, and that's the only way to avoid making mistakes. If you're just following notes saying instructions that say add this, do this, subtract this, take that number from here, you're going to get hopelessly lost and make mistakes. But if you understand each step and why it works, then it's really quite easy, quite simple. The math is easy. All the tables do all the complicated math for you. So not to worry about the process. Once you've done it once or twice, it becomes very routine. The sites from one night are very similar to the sites and process, the math, the whole steps. Each step is very similar to what you did just the night before and the night before and the night before. Or if you're doing sun sites, that works great too. Every sun site is pretty much the same. The numbers change, but the site and the process is exactly the same. So it becomes really very routine, something you can do really without thinking at all. Okay, let's start with number 1. We'll need our board here. Let's get space. So, accurate time. Accurate time is critical. So you need a watch or a clock that is going to be accurate, and then you will want to record your watch or clock error, and on a daily basis if possible, referring to GMT and seeing how far off your clock is. That gives you watch error. Okay, so step number one, let's start right when you take the sight. There's several ways to take a sight. First, easiest is with a second person to record the time. Then you're taking your sight, you have the sextant. If you're taking the sun in the morning as it gets higher and higher, you're going to take your sextant, set the sun so here's the horizon, the sun is dipping just below the horizon as you rock your sextant. And in just a few seconds, as you rock your sextant, you'll see the sun rising enough that it just barely, at the bottom of the arc as you rock your sextant, the sun just barely grazes the horizon, and you say mark. You think, how precise is that? It's very precise. The sun moves fast when you're looking through the sextant. You say mark, and the second person records the exact time of the sight. That is that would give you watch time. They're looking at the clock and they record the watch time, exactly the time on your clock. Okay, if you're doing your sight by yourself, then it's very hard to take a sight and then look at your watch. There are two ways to do this. One is you can take your sight, and then if you're good at counting seconds, right at the mark, right when the sight is exactly right, the sun's right on the horizon, you start counting down 5, 4, 3, 2, 1, 0, and look at your watch right at 0. And then you're going to subtract 5 seconds. So you might have so your watch time would be, you're counting down 5 seconds, so you're going to take your watch time and then you're going to subtract 5 seconds. Make that bigger. And that'll give you a corrected watch time. The other way of doing it is to use a stopwatch. With stopwatch, you're going to take your watch time and take a very precise watch time and start your stopwatch. So if you start your stopwatch, let's take it, it doesn't have to be an even time, it might as well be even minutes. So let's say you started your stopwatch right at watch time of 10:21 minutes. And now you take your sight with the stopwatch in one hand and your sextant, take your sight, you got your sight perfect, you click your stopwatch and your stopwatch reads 30 seconds. So your watch time in that case started at 10:21 minutes 0 seconds, and now your stopwatch added 22 seconds to that, and so your corrected watch time would be 10:21:22. That's using a stopwatch. This is using a counting down to the time you saw. This is added, this is subtracted. If you're counting down from your, and then looking at your watch after you've taken the sight, 5 seconds after you've taken your sight, in this case, if you're, when you look at your clock or your watch, it reads 10:21, 27, then you've counted down 5 seconds. You'd subtract the 5 seconds to get back to the time you took your sight. So you'd have corrected watch time of 10:21, 22. In this case, it was your watch time earlier than you took the sight, and then this is when your watch time is when you started your stopwatch, and then this is how long your stopwatch ran before you got your sight, and so you add that amount to your watch time, and this is your corrected watch time. Okay, so a couple ways to do it. If you just said mark and a second person recorded the time, they would just have recorded the actual watch time of the sight. So a few different approaches there. Okay, now let's go from watch time. Let's go from watch time to GMT. What's involved there? Okay, the first thing is your watch error. And that's going to be a plus or minus watch error. So think through watch error carefully, because if you go the wrong way with watch error, but watch error isn't going to change during your voyage probably. Your watch error might change a little bit incrementally. After a week it might have changed by 1 second or 2 seconds if your watch isn't exactly precise, and that's fine. But it's probably going to stay plus or stay minus. It'll keep changing one direction. Okay, so watch time corrected for watch error, plus or minus watch error. That gives you local time. Okay, if your watch is set to local time when you correct for watch error, now you have an accurate local time. Another approach, which saves having to correct from local time to Greenwich Mean Time, is to keep your watch on Greenwich Mean Time, or keep your clock that you're navigating with on Greenwich Mean Time all the time. Then you just go Greenwich Mean, your watch time plus or minus watch error would give you Greenwich Mean Time. And then you won't really have to change you won't have to rethink this every time. You won't have to change your watch time to meet, by the time zone that you happen to be in. But let's assume that you've got your watch time set to local time, and then you have to correct for the zone you're in. Okay. The Earth spins 360 degrees in 24 hours. So 360 divided by 24 means it spins 15, that's 360 degrees, 24 hours, 15 degrees per hour. That's how fast the Earth is spinning. Each time zone is 15 degrees. But the first time zone, the 0 time zone, is interesting. Here's Greenwich, here's 0. 0 degrees longitude. Here's England. Here's Greenwich right there. Greenwich is in the middle of its time zone. So the first time zone is 7.5 degrees to the east and 7.5 degrees to the west. That's 7.5 degrees. Total of 15 degrees. Okay, now how do you figure out what time zone you're in? Well, let's take a simple example. Let's say you're at 8 degrees here, just outside of the first time zone. 8 divided by 15 gives you, well, it's more than a half, right? It's greater than 1/2. So that rounds up to a time zone of 1, since it's greater than 1/2. If you're at just 7 degrees, 7 divided by 15 is less than 1/2, and you're in a time zone of 0. 0 difference time between your time and Greenwich's time. Okay, so if we're at a time zone, if we're at a longitude of, let's say we're at a longitude of 129 degrees, we divide that by 15, and now we have to do some math. That's 97, should be 8. So it's 8 and 9/15. That's a 9. 8 and 9/15. 9/15 is greater than 1/2, so that rounds up. So this rounds up. 8 and 9/15 rounds up to zone 9. Zone 9. So to figure out what time zone you are, how many hours different from Greenwich, you just divide by 15, and if it's over, if the remainder is over 1/2, then you round up. If the remainder is under half, you round down. Okay? So this would be zone 9. Let's take that example. Zone 9. Let's take a local time of 10, 20, 15, and we're in zone 9. So that was 129 degrees west. Important. If it was east, it would be a whole different problem. Since it's west, the sun got to Greenwich earlier than it's morning where we are, local time, 10 o'clock in the morning. It's already late afternoon, at least in Greenwich, or middle of the afternoon in Greenwich. The sun got to England a lot sooner than it got to us. So we add our plus 9 hours for the time zone, and we get 19, 20, 15 GMT. Okay, that's 19 hours, 20 minutes, and 15 seconds Greenwich Mean Time. Are the seconds important? Well, yes, you bet they are. They're real important. Let's go back to our problem here. 360 degrees in 24 hours. That was 15 degrees per 1 hour. That's 15 degrees in 60 minutes. 1 hour, 60 minutes. 15 degrees, each degree has 60 minutes in it. So 15 degrees is 15 times 60 minutes of arc. That's not minutes of time. This is an easy place to get confused in navigation, isn't it? This is 60 minutes of arc. 60 minutes of arc equal 1 degree. We got to be clear whether we mean minutes of arc, 60 minutes of arc, 1 degree, or 60 minutes of time, which equal 1 hour. Okay, so 15 times 60 is 15 degrees over 60 minutes. Our 60s cancel out, and we have 15 minutes over 1 minute. Okay, 15 minutes of arc over 1 minute of time. Okay, let's come over here. 15 minutes of arc over 1 minute is 60 seconds, right? 60 seconds of time. And where are we going with this? Let's divide top and bottom by 15. So the top is 1 minute per 4 seconds. That's the Earth spinning. 1 minute, remember 1 minute of arc is equivalent to 1 nautical mile. And so the Earth spins every 4 seconds. The Earth spins 1 minute of arc, 1 nautical mile. So if you're off in your sextant reading or your math by 4 seconds of time, you're going to be off by a mile. Okay, if you're off by a whole minute, you're going to be off by 15 miles. Okay, so that's the first step. Correcting your watch time for watch error, and then getting Greenwich Mean Time based on your local zone. Or if you're just using keep your clock on Greenwich Mean Time, then you only have to correct for watch error to get an accurate Greenwich Mean Time. Okay, next step is correcting your sextant site. And we'll start with HS, and we want to end up with HO, height observed. Okay, we start with height sextant. That's read right off of your sextant. And be careful reading the vernier scale, but that's not too complicated. So let's say we read off of our sextant a reading of 29 degrees 12.5 minutes. Okay, now notice here we use degrees, minutes, and tenths of minutes. We really don't ever use seconds in navigation. It's just too many conversions. Seconds, 60 seconds would bump up to 1 minute. 60 minutes would bump up to 1 degree. We do have to remember when we go from minutes to degrees, it's 60 minutes equals 1 degree. It's a 60 base system and not a 100 base system. But 29 degrees, 12.5 minutes. So this is tenths of minutes. Now, what are the corrections we need to make? Why do we have to correct our sextant site? We did it really precisely. Our sextant is an accurate instrument. Why do we need to correct it? Well, let's say our sextant has a slight error. We can set the sextant error out by adjusting the mirrors. But let's say our sextant has a very slight error, so that when we shoot something and read the sextant, there's always that error, always the same error. How do you find that error? Well, you find that error by taking your sextant and shooting the horizon, so the horizon lines up with itself. If the horizon lines up with itself perfectly in the mirrors here and straight through on the other side here, here's the horizon in the mirrors, here's the horizon on the other side where you're looking straight through clear glass. If those line up perfectly, when your sextant reads 0 degrees 0 minutes, 0.0 minutes, you have no correction to make. Okay? But if you set your sextant to 0 degrees 0.0 0 minutes and your horizon doesn't line up, it's like that. Or if your sextant error is the opposite way, your horizon's like this across here, you've got a sextant error. Now with the little set screws on the mirror, on the top mirror, you can tip that top mirror to take out that sextant error. And that's not a bad plan. Just be careful. You can't do it in a room, looking across the room at a shelf or anything, because that just simply doesn't work. You have to use something that is far distant. It's nice to use a true horizon out a mile or mile and a half away from your location, and line up those lines, and then look at your sextant. If your sextant reads, when your horizons are lined up, if your sextant is now reading a minus 0.2 minutes below 0, minus 0.2 minutes below 0, you really want it to be reading 0. So to correct for your sextant error, you're going to have to add 0.2 minutes. So your correction for, that's called the index correction. It's actually a sextant error correction, but it's called the index correction. Your index correction would be plus 0.2 minutes. If, on the other hand, when you line up your horizons, you have your sextant reading 0 degrees plus 0.2 minutes, that means it should be reading 0 degrees. So, but this is what it actually is reading. So to get back to an accurate reading of 0 degrees, 0, 0, you're going to have to subtract 0.2 minutes. So then your correction, your index correction, will be minus 0.2 minutes. Okay, so figure that one out correctly. Don't start your voyage and make a mistake with your index correction and use the wrong index correction, adding versus subtracting, or subtracting versus adding for an entire voyage. But I like to set the set screw on the mirror so my horizons line up right at 0 degrees, 0 minutes. And that's not that hard to do. And then if you're careful with your sextant, your index correction should stay at 0 or stay stable the entire voyage. But it is important to check your index correction at least once a week. It's pretty quick to check it. You might check it more often. Every couple of times you use your sextant, it's not a bad idea to check the index correction, make sure it hasn't changed on you. Should not change, but if it gets bumped, it might change. Okay, so index correction. That's just the inherent error in your sextant, the way the mirrors are set. Okay, now what else are we going to have to correct for? Oh, goodness sakes. We took a really good site. You know, it was calm, no waves. That's a big advantage, calm, no waves. And we weren't, hadn't had any cocktails. Time was, you know, everything seemed perfect. Everything seemed perfect. What else should we correct for? Isn't that good enough? We corrected for any error in the sextant. Well, no, wait a second. There are a couple of things. Oh, wait. Let's not forget these because they're important. If you're on the bridge of a ship 70 feet high above the water, or even higher, maybe 90 feet above the water, you think you're shooting out to the horizon and measuring the angle between the horizon and the sun or the stars or the moon or whatever. You think you're measuring that angle. But no, you're not measuring that angle from the horizon up to the sun or stars. You're actually measuring a bigger, you're looking down on the horizon. You're measuring too big an angle. You're looking down on the horizon from way up high. The horizon is below you. And now you're measuring too big an angle. That is called a dip correction. The higher you get, the more you're looking down on the horizon, and the more you have to correct. All this is based on your horizon being exactly tangent to the Earth, right at the point where you're standing. That means it's all based on your eye level being right at water level. It's very hard to take a sextant sight while you're swimming, but that's what the math is doing. So you're going to have to correct for how high your eye is. Even on a sailboat, where you're only 6 or 8 feet above the water, you still have to correct, make that dip correction. Okay, how do you make that dip correction? Well, we know one thing. The dip correction is going to be a lot less if you're on a sailboat than if you're up on the bridge of a big merchant ship or a naval ship. Well, it's one of the first things we do. So the almanac puts it in a very convenient place right at the very beginning. This is right the inside of the front cover. This is the front cover on the inside flap. And there we go. Dip. Dip correction. Well, let's take a dip. Height of eye. Meters. Oh, they have meters and feet. Isn't that convenient? Well, the tables make this easy. Here is 8 feet above the water, and the correction, here's correction, is, and it's in minutes, the correction is in minutes. Don't think it's degrees, you'll be way off. 3.8 minutes. That would be for a sailboat, 8 feet above the water. You're standing up, taking your sight, and the correction is 3.8 minutes. And look, they tell you, it's a minus correction. Remember, your sextant sight is too high because you're already looking down on the horizon, even at a height of 8 feet above the water. So the correction is minus 2.8. Minus 2.8 for the height of eye correction. That's the dip correction. Minus 2.8 minutes. Let's take a quick look and see what it is from the bridge of a ship. Let's go up to 70 feet. Here, dip of 70 feet. They don't give every... You could try to... There's really no point in interpolating here, because between 68.8 feet and 70.5 feet, there really is very little change here. Even between 67 and 70, there's very little change, only a tenth of a minute. So, and again, it is minus. If you did it in meters, this is the meters height over here. If you're way, way up high, look at this, way up high here, 130 feet, all of a sudden it's a minus 11.1 minutes. Okay? So, dip. Make sure you add your dip or subtract your dip. Dip's always going to be minus, because you're always getting too big a reading because you're looking down on the horizon. Okay, now those two corrections, when you make those two corrections, what do we get? We're subtracting our index correction because of the way our sextant is off, because we didn't reset the mirrors so it's perfect. And we're subtracting our dip correction. So this is minus 2.8 and minus 0.2. That's going to be a total of a minus 3 minutes. So we get 9.5 minutes. 9.5 minutes. And over here it's 29 degrees. That gives us height apparent. Okay, height apparent. Well, that's not what we're going for. We're going for height observed. Height observed, HO. Now we have an HA, height apparent. What else do we need to correct for? What else could make our sight wrong? We were so careful. Well, this is unavoidable. Here's the Earth. Here. And the Earth is surrounded with purple haze, with atmosphere. Now, when you're standing, this is the Earth, this is not the Sun, this looks like the Sun. Now, this is the Earth, and this is the Earth's atmosphere. Now, when you're standing on the side beside a pool, swimming pool, and other people are waist deep in the water, what's wrong with those people? It looks like their legs are only, a foot and a half long. They're regular people, they have long legs. But all of a sudden, their legs look really short. That's because the light, when it hits the interface between the pool water and the air, different mediums, different density mediums, the light gets bent. Well, guess what? That starlight that was coming in to the Earth from this angle hit the atmosphere and bent down. The lower the angle of the light, the more the bending. Light that comes straight down doesn't bend. If you're looking straight down into the pool and see a quarter lying on the bottom of the pool, straight down, that's right where the quarter is. The light didn't bend at all. Straight down through the interface between the two mediums, there's no bending. But the lower the light gets, the more the bending. So that's one reason we don't like to take really low sights. That's actually the biggest reason we don't like to take low sights, because of all that bending. And when the light gets bent really a lot by the atmosphere, different atmospheric conditions will have different effects on the light, bending it more or less. We can kind of average and predict what an average amount of bending might be, but below 15 degrees of altitude, when we're shooting a sight that's really low, the sun really low, below 15 degrees, that's a very suspect sight. Even though we're going to correct for the altitude being so low, we're still not going to feel that sight's very reliable. Okay, so we like to shoot things above 15 degrees because there's a little bit less bending, but there's still bending. Until we get up to 90 degrees, there's still going to be bending of the light. So how do we correct for that? In fact, this does introduce another interesting point. I've been asked this a number of times. Why do we have to take a sextant sight at all? Why can't we just wait till the sun is setting and right when it touches the horizon, check the time and figure out our longitude from that? Or when the sun's rising, figure out our longitude from the exact moment the sun touches the horizon. Well, the problem is that the light is being bent so much that we might have an error of 15, 20, maybe even 30 miles if we didn't figure out, because that adjustment becomes for the light bending at such a low angle becomes pretty much guesswork. Okay. In fact, when the sun is setting, you may notice sometimes it doesn't even look around anymore. It looks sort of stretched out and oblong, and that's because of the bending of the light. Okay, so this is our last correction here. We're almost done with our sextant corrections. We've done our time corrections from watch time to Greenwich Mean Time, and now we've almost done our sextant corrections. This is the altitude correction. Altitude correction. And it's based on the height apparent. Technically, this is the way you want to do your corrections. In reality, if you're on a sailboat, your dip is going to be a really small correction, and your index correction really shouldn't be very big either. So, if you're on a sailboat, you can do all your corrections all at once, instead of correcting HS to HA and then using HA to get a correct altitude correction. You can just do your altitude correction based on your HS. But if you're on the bridge of a ship and all of a sudden your dip correction's bigger, your altitude correction will not be as accurate if you base your altitude correction on the HS instead of on the HA. Okay, so but when I'm working a sight on a sailboat, I'll just do all three corrections together based on the HS. Okay, altitude correction. How do you find it? What do you mean based on the HS versus based on the HA? Well, altitude corrections. Let's find the altitude corrections. And again, it's really easy to find right in the front of the almanac. If you're doing sun, that would be right here. Now the sun from October to March is going to be in this column. The sun from April to September is going to be in this column. Now why is that? Well, sometimes we're closer to the sun and sometimes we're farther away from the sun. So the sun's diameter is going to be different. Well, why does that matter? Well, look at this. Here's the apparent altitude. And then the next column says lower limb. And then in smaller print, smaller typeface, the next column says upper limb. So what is lower limb and upper limb? Well, lower limb, dark typeface, the more usual one to enter. Lower limb is when you shoot the bottom limb or bottom edge of the sun. Whichever edge is closest to the horizon is the lower limb. Upper limb is when you shoot the top of the sun and set the top of the sun level with the horizon. A little bit more difficult to shoot upper limb because the sun is sweeping up above the horizon down till it's just the top of the sun is level with the horizon and then back up. Lower limb, the whole sun stays above the horizon and you just barely rock your sextant till the bottom edge of the sun just barely kisses the horizon. Okay, so apparent altitude, and that's in degrees and minutes. The entry point, apparent altitude. This is for the sun though. This was a sun sight in the morning that we were taking. When we corrected our time, we started with a local time of 1000. And so it was a morning sight, so that would have to be the sun. And our apparent altitude is 29 degrees, 09.5 minutes. Okay, so let's go in and find that. So apparent altitude right here. And since this is a hypothetical situation, we didn't have a month yet, but let's say this was August 9th. So which column are we going to be in? October through March? No. April through September. August, September. So, and we shot the lower limb of the sun, and we got 2909.5. So we go down apparent altitude to 29. Way down here. Between 28, 33, and 30. And our correction is going to be plus 14.3. What is that? It's going to be minutes, but always check the top. Minutes. Plus 14.3 minutes. Okay, so plus 14.3 minutes. And if we'd shot the upper limb of the sun that same time, we would find it's going to be a minus correction. So upper limb for 29 degrees. Upper limb 29 degrees April through September. 29 degrees here. Upper limb would have been minus 17.6 minutes. Now the reason there's a difference there is the sun is wide enough that the light from one edge of the sun is being bent differently than the light at the other edge of the sun. If we look at 90 degrees, we'll see that those readings are the same. The light coming straight down is not being bent. And those two readings actually tell us the if you add those together, 15.9 and 15.9, that tells us the diameter of the sun during those months. So almost 32 degrees, 32 minutes rather. 31.8 minutes is, if you took your sextant and measured the diameter of the sun during those months, you'd get a diameter of 31.8 minutes. Okay, so that's the altitude correction. Just add that on, and we get 0.8, 23.8 minutes, 29 degrees here. So if your sight doesn't seem right, you think, I can't be there. How can I be there? It's totally different from my dead reckoning. You want to go back and check your work. If you haven't labeled everything, it's almost impossible to check what you did and find a mistake. So make sure everything's labeled, everything's neat, all the columns are lined up, all the numbers are precisely very clear, because the mistakes you make in celestial navigation rarely will be because you don't understand or because you didn't know what you were doing. Almost all the mistakes will be because you misread a number that you wrote down, and when you added two things together, you thought a 2 was a 3 and it was just badly written, or you got things in the wrong column and you thought it was minutes and it was actually tenths of minutes. So be very, very careful about process, because that's what's going to keep you from making mistakes. Okay, so now we've done step number 2. We've gone from HS to HO. We have a height observed, and that is what we will be using when we get to the final steps of plotting our position. So HO. So if this was all on one sheet of paper, I'm going to have to keep erasing the board because we need the space. I want to make it big so you can see it. But if that was just a corner of our piece of paper that we're plotting things on, I would now put a box around this, because that number we need to hold on to. That is the number that we're going to use to plot our position. Okay? We'll get to that later. Okay, any questions here? You may be looking at this and thinking, oh, why are we... Altitude correction is... Oh, one more thing about altitude corrections. But low altitude corrections are always going to be minus, okay? Because look at the way the light is bent. It looks like the planet is up here, and it's actually down there. The light is bent down. So to get the accurate direction to the body, we have to subtract all the bending. So altitude corrections are going to be minus, but when we add in the limb correction as well as the altitude correction, then that's why it gets to be plus. But if we go to very low altitudes where there's really a lot of bending, let's go on the second page here of altitude corrections. This whole page is from 0 degrees to 10 degrees here at the bottom. 0 to, the whole page, 2 columns, 0 to 10 degrees. We go to the lowest corrections, and they're both limbs, upper and lower limb, there's so much bending, both limbs are going to give you a minus correction. Okay? So that's, the bending is always going to look like the sun is too high, is higher than it really is, and so you're going to be subtracting. If it was just altitude corrections, all of the corrections would be minus. In fact, if we take any of these corrections, let's take a correction here and add the limb corrections together, plus 13.2 and minus 19.1, and you add those two corrections for the limb, lower limb and upper limb together, you get a negative correction of about minus 6 minutes. So that just leaves the altitude correction. If you add those limb corrections together, you're getting rid of the limb correction and just getting the altitude correction. Altitude correction will always be minus if you don't have the limb correction added in. Okay, in fact, for the stars and planets, you'll see that right here. Stars and planets. All of these have to be minus. Here's the apparent altitude, and here's the correction. Okay, apparent altitude and the correction is minus always until you get up to 90 degrees, and then it'll be 0. Straight up, no correction at all, no bending. Okay, one other thing I want to point out. Look at the sun. From 9 degrees or 10 degrees, where do we start? 9 degrees up to 15 degrees is almost half of that page. It's this much of the page here. Okay? And then from 15 to 90 is just the rest. From 15, that's why we don't like to take sights below 15 degrees, because there's so much bending of the light, and these values are as close as they can make them, but based on atmospheric conditions, these can be quite far off, under 15 degrees. Okay? I think that covers this. Well, stars and planets here. These are just altitude corrections, no limb corrections, because these are points. A star or a planet, when you shoot that, you're shooting a point. You're not shooting the lower edge of the point or the upper edge of the point. It's just a point. And then, where's moon? Oh, darn it, no moon. Sun, sun, stars and planets, dip, and sun again. Okay, well, I guess we can't shoot the moon then, because if you can't do an altitude correction, you can't shoot a body. Oh, well, wait a second. Here, back cover. Now we're at the back cover, at the very back of the book. Here's the cover, see? Back of the book. Look at that. Altitude correction tables, moon. All right, 53 to 90 degrees. Now these corrections are different. Let's give ourselves a little space here. This was the sun. Always label whatever you're shooting, the date and the body. Okay? When you're working it out, make sure you label it. Again, if you have 5 sites and you haven't labeled them, you're trying to check your work. If you don't know which was the Venus and which was the moon and which was the star, you're going to really struggle. So always label everything. Okay, let's give ourselves some space here. Okay, recap. If you're on a sailboat, you can just do all 3 corrections together. Altitude correction, and that gives you HO. If you're on a merchant ship or taking a Coast Guard test on celestial navigation, start with your HS, plus or minus the index correction, always minus the dip. That gives you height adjusted, and then altitude correction figured in. That's also the limb correction. Remember, altitude and limb correction are the same thing. Upper limb, top of the sun, lower limb, bottom of the sun, moon, upper limb or lower limb. We'll get to that in a second. And then you get height observed after your altitude correction, height observed. Okay, let's give ourselves some space here and look at the moon. Now the moon's a little bit different. Okay, why would the moon be different? Well, we mentioned it in part 1, the problem with the moon. Here's our Earth, and here's the moon. I know the scale is wrong. I mean, our Earth would have to be the size of a pea for the moon to be still, you know, on our board here. But this will give you the idea. The moon is really relatively close to the Earth. Not this close, of course, but relatively close to the Earth. Remember, all of our navigational math works because of the assumption that all the light coming from the sun or stars or planets is coming in parallel rays everywhere on the Earth. Okay? Without that assumption, the math would be really, really complex and wouldn't work. However, with the moon, all of a sudden we've got a problem. We're going to assume that the light from the moon comes in parallel rays. so we can do the same type of math problem that we do with all the other celestial bodies. But the reality is, it's really not coming very parallel. The moonlight is coming in at this right to this GP, in the center of the Earth, right to this GP, right under the moon. That is the GP of the moon, right there under the moon. The light is coming straight, but now look at the light coming over to here. It's coming at a funny angle. Anytime you're not right under the moon, the light is coming at a funny angle because the moon is so close. All these lines are not parallel. This is not parallel to this or this. They're at different angles. That's called horizontal parallax, HP, horizontal parallax, HP. And that is something we're going to have to correct for. Not too hard to correct for it, but it is important to correct for. And then, once we've corrected for the fact that the moon is too close to the Earth and the light isn't coming in parallel lines, once we've corrected for that, then we can treat the moon basically like the other bodies as far as our math, our basic geometry, and the assumption that the light is parallel. Okay, horizontal parallax. Now let's look at the altitude correction tables. The altitude correction tables for the moon include a correction for horizontal parallax, as well as a correction for the limb and for the altitude. So three things are being corrected simultaneously in the moon correction tables. That makes them just a little bit more complicated. There are two entries, one in the top of the table and one in the bottom of the table. Okay, now, right here are the instructions, right there. You don't have to go to, some other book or anything to find the instructions. They're right here. What the instructions tell you is that you enter starting at the top of the table. And let's look at the top of the table. What are the entry values that they want? Apparent altitude. Oh, across here. Here's the apparent altitude. We had an apparent altitude of, well, we erased our corrected altitude, didn't we? The apparent altitude, remember, is index correction and dip correction gives you height apparent altitude. Okay. And let's say this was a minus 0.2 minutes. The dip was minus 2.8 minutes. And so, well, this is probably, I don't know if it's exactly the same. It looks the same. So that's minus 3, and that's 9.5 minutes, 29 degrees, 9.5 minutes. Okay, so that's our apparent altitude. So we're entering on this side here, apparent altitude 29, okay, 20 to 24, 25 to 29. Okay, so we're in this column here, and let's go down to 29 degrees, 9.5 minutes. Okay, here are the degrees here. We're going to be in this column. Oh, 25 degrees, 26 degrees, 27, 28, 29 degrees. And then here are the minutes over here. See, it'll tell you at the top. Minutes. Okay, so, whoops, 29 degrees, 0.5 minutes. Here's 0 minutes. That's 10 minutes. So 0.5, we're very, 9.5. 9.5, we're very close to 10 minutes. So we'll take this value here. You see, these values aren't changing very much, so we don't have to interpolate. We don't have to try to get between them because there's no space between them. So our correction here is 59.3. 59.3. And that's going to be minutes. It tells us. It says minutes. Minutes. Okay, and that's the altitude correction. Okay, now if you read the instructions, see there's no pluses or minus on these corrections anywhere. But if you read the instructions, it's going to tell you that all corrections for the moon are going to be added, but if you shot the upper limb of the moon, you're going to subtract 30 minutes. Okay, separate corrections are given in the lower part for the lower limb and upper limb. All corrections are to be added to apparent altitude, but 30 minutes is to be subtracted from the altitude of the upper limb if you shot the upper edge. So let's write out, you can read these every time. Probably a good idea to read them every time. Okay, but the lower part of the table you enter in the same column. It's a little tricky here to keep the column straight, but we're in this column here, 29 degrees. Here was our 29 degrees. And we stay in the same column and go into the bottom part of the table. Now where do we go? Well, lower limb, upper limb. Say we shot the lower limb of the moon here, so we're going to be in this line of numbers, but where do we go in that line of numbers? Well, the entry point is HP value. Oh, well, what is our HP value? How do we know what the HP value is? Okay, well, bit of a mystery. But let's look in the pages of the daily pages of the almanac under moon and see if that helps us. Okay, so we're on August 9th, and we had a GMT of 1900 on August 9th. So here we are, August 9th, right there. And here's the moon, August 9th. Oh, well, here's August 7th, 8th, and 9th. Here, and moon is here, and look at the top right there. Oh, the last value there is HP. Okay, so let's go down to August 9th, 1900 GMT, Greenwich Mean Time of 1900. Here's the GMT, 1900, down the sides, 1900. And we go across, the last value, 54.6 is the HP value, 54.6. Okay, now we go back into our moon altitude correction tables. And we're in this column here. Whoops, jump pages. We're in this column here for 29 degrees, and we go down to 54.6. 54.6 right here in this column. 54.6, see it right there, 54.6 in the HP column. That's our entry value, and we shot the lower limb. We get a correction of 1.4 minutes for the lower limb. 1.4 minutes for the lower limb. So 1.4 minutes, and that's the HP correction for the moon, and all corrections are to be added. So now, what do we have? So it's 8, that's 12, 10, 69, 70.2 minutes, and over here 29 degrees. Okay, good. glad we got to this point, because remember, this is a 60 base system. So 70.2 minutes is going to change to 10.2 minutes and 1 degree more over here. We're subtracting 60 minutes here. Now that's 1 degree here. So now we have 30 degrees, 10.2 minutes. And let's label that. What is that number? That's our height observed for the moon. Okay? And that's what we're going to be using later on, so we want to put a box around that one. Okay. Now let's check our work here. So we started with the height sextant, subtracted our index correction, subtracted the dip. Index correction, remember, can be plus or minus, depends on your sextant. But if it starts out minus, it's probably going to stay minus. And dip, minus, dip's always minus. And that gives us this height adjusted. We entered the tables with the height apparent and of 29 degrees, 09.5 minutes. We entered the moon tables. This is the moon. Always label your sites for the planet or star or celestial body that you shot, moon. And then we did the initial altitude correction from the top of the table, 59.3 minutes. That seems big, so let's check. For 29 degrees, 10 minutes, 59.3 right there. So if you think a number looks funny, check it, 59.3. And you look at the top, and that is minutes, tells you it's minutes, 59.3. And then the HP correction, just a little 1.4 minutes. And you can check that again for make sure you got the lower limb, not the upper limb. And because there are a lot of places you can make mistakes here. So notice for 54.6 and lower limb is 1.4 minutes. And all corrections are added. If we'd taken the upper limb, we'd have to then subtract 30 minutes. But we took the lower limb. This was a moon, lower limb. And so now we have a height observed. And that's the number we'll be working with later on. Okay, so moon's a little bit more involved, right? Stars and planets, though, very simple. Even simpler than the sun. It's always just one table. You don't have to go in by 6 months here or the other 6 months of the year like you do in the sun. The only thing to watch out for here, stars and planets, there's an additional correction for Venus and an additional correction for Mars on top based on the months, the time of year. Okay? So you take for Venus and Mars, that's because sometimes they're farther away and sometimes they're closer, depending on what part of their orbit they're in. So they get a little bit too close. That may be a parallax correction too, but a very small parallax correction. So you start with for the stars, you just take the apparent altitude here as your entry and take the correction out here. If it's Venus or Mars, you take the correction based on your apparent altitude, and then you add this additional correction based on the month, time of year. Okay? So not a big problem. And in fact, these additional corrections, if you make a mistake and blow it, you're not going to be too lost. These additional corrections are just 0.1 minutes, and here 0.1, and here 0.1. Unless it's a real low site, and then you have a bit more of a correction. Okay, so 0.1, that's just a tenth of a mile. If your sights are so accurate that you're worried about a tenth of a mile, you're doing really well. Okay, probably better than I could do. Okay, so that covers the second step, which is going from height sextant to height observed. Correcting for index correction, that's sextant error. Dip, which is based on the height of the eye, because you're looking down on the horizon, not straight out at the horizon. And then the altitude correction, because of the bending of the light as it comes through the atmosphere. And with the sun and the moon, the altitude correction, with the sun, the altitude correction includes the limb correction, upper limb versus lower limb, bottom edge of the sun, lower limb, upper edge of the sun, upper limb. And with the moon, the altitude correction incorporates the limb correction and the horizontal parallax correction for the moon being so close to the Earth. Okay, so that's step 2. Correcting for our sextant sight. So we have an height observed. Okay, step 3. Now, the fun stuff. Step 3. We're going to go into the nautical almanac and we'll be looking for 2 values. We'll want, let's give ourselves plenty of room here. We can take this out too. We'll want to come out of the nautical almanac with the declination and the Greenwich hour angle. Declination is exactly the same as latitude, north or south. There's no difference. We just call it something different. The latitude of the ground point of the sun or stars or moon, the point at which the light is directly coming down right on your head, down through your feet, down to the center of the earth. You look straight up and that celestial body is immediately over your head. It's not at some angle one way or the other, straight up above your head. Declination or latitude of the ground point and the Greenwich hour angle, GHA, which is related to the longitude. If you're in the Western Hemisphere with a longitude of less than 180 degrees west, Greenwich hour angle and longitude, if the star is in the Western Hemisphere, Greenwich hour angle and longitude are exactly the same. But remember, Greenwich hour angle, GHA, is measured from east to west, from Greenwich around across the Atlantic, across the U.S. It's measured all the way across the U.S. on around 360 degrees all the way back to Greenwich, around the equator, around the girth of the Earth. 360 degrees east to west. Whereas remember, longitude is measured 180 degrees from east to west, west longitude, and 180 degrees from west to east, that's east longitude. So if you're sailing in the Mediterranean, GHA is a little bit harder to think through because it's different from longitude. But if you're on the Western Hemisphere, anywhere in the Atlantic and most of the Pacific, then GHA and longitude are exactly the same. Okay, so these are what we want. We want to know where the sun is exactly when we shot it, at the exact minute, hour, minute, and second on the day that we shot it. We want to know exactly what point on the surface of the Earth is directly underneath the sun. And the nautical almanac will tell us that for stars, planets, moon, sun, and everything up there. Well, I think that's it. Stars, planets, moon, and sun. So, remarkable table. Okay, let's, our site was on August 9th, and initially, let's start with the sun. The sun is the easiest. In fact, the sun's easiest to shoot too, and easiest to use in a number of ways, because you're never going to get confused and think, you'll never have trouble identifying the sun. And it's in the middle of the day. You can shoot anytime, throughout the whole morning. It doesn't have to be very precise. Whereas stars and planets, you have to shoot right at dusk because you have to be able to see the star and the horizon at the same time. If it gets dark, too dark, you can't see the horizon anymore. If it's too early, you can't see the star. And right at dusk is kind of dinner time, and you know, dawn is kind of, you're just waking up time. So sun is awfully easy to shoot because you can shoot it, you know, throughout the morning. Yeah, it doesn't have to be very precise. But if you're going to use the sun, you want your angles, your two lines of position to cross more or less at 90 degrees, as close to 90 as possible, and because that gives you a more accurate crossing. And so you want to shoot one sight in the morning and one in the afternoon, and then you just take your morning sight and advance it based on your dead reckoning, the direction and the distance that you traveled. You just move the whole sight on your chart, that direction and distance, and that's called advancing your morning sight, and then to the time of your afternoon sight. And so then it's as though both sights were taken at the same time. If your dead reckoning's off, yes, your position will be off a little bit, but typically over 5 or 6 hours your dead reckoning shouldn't be too bad. Okay, so sun sights are easy. The sun is an easy thing to shoot. It's easy to find in your viewfinder because it's big and bright. And so sun is a great place to start. Also, it's a little bit simpler in the tables to get your declination and Greenwich hour angle for the sun. It's not really, it's not too difficult to do it for the planets. It's a little bit more difficult for the moon, but still not a big problem. And then there's one extra step also for the stars, a little bit more complicated, but not, again, not too difficult. Okay, so August 9th. Let's say we had a local time of 10, 20, 15, and we corrected that for a watch error of -2 seconds, minus 0.02, and watch error. And our zone difference, we're at 129 degrees divided by 15, and that gives us 8 and 9/15. And 9/15 is more than half, so that gives us a zone of 9 hours plus 9, because we're to the west. It's already, the sun's already past Greenwich a long time ago. So it's plus 9, and so we get GMT of 19, 20, 13. Okay, GMT 19, 20, 13. That's where we'll start, and we're doing the sun. Oh, we didn't put that up there. Sun, August 9th. That's the body, not the day. Sun, August 9th. For a GMT of 19, 20, 15. 13. 19, 20, 13. August 9th. Here we are. August 9th. Okay. Remember, we're trying to find out where the sun is. We don't need our sextant reading now. We're going to use it later. Our HO. Our corrected sextant reading. We're going to use that later. We don't need it now. All we're trying to do is find out where the sun was exactly when we took the sight, which was Greenwich Mean Time 1920 13. 1900, 20 minutes and 13 seconds. Okay, where was the sun? Well, we're looking for its declination, its latitude, and its Greenwich hour angle. Okay, so August 9th. This is August 7th, August 8th, and August 9th at the bottom of the page. Sun. Where's the sun? This is Aries. We'll talk about that later. Venus. Here are the planets. Here are the stars. And oh, here's the sun over here. There we go. Sun. And look, GHA and declination. That's great. That's what we're looking for. Greenwich hour angle and declination. We're going to start with the declination because it's a little bit simpler, and then we'll do the GHA. Remember, we're in the bottom, August 9th. Here's the declination at 0000 hours. Now with declination, you have to bring down that north, what is that, north 15. That applies to all these values. They just give us the minutes here, but it's not 0 degrees all of a sudden in minutes. It's north 15 and then the minutes over here. Okay, so we're at a GMT of 19, 20, 13. So we'll take the value for GMT of 19 for the declination. Here's the GMT of 19, and we get north 15, 36.9. North 15, 36.9. North 15 degrees, 36.9 minutes. Okay, well, we actually don't want just 1900. We want 1920 minutes and 13 seconds. Let's look at the next declination. Here we are, sun for 2000 hours. Here we are, there, 2000 hours. North 15, 36.2. Okay, this is the declination for 1900 hours. This is the declination for 2000 hours. We want to be in between these two. Roughly a third of the way between the two. 20 minutes is roughly a third of an hour. So we'll be a third of the way between these two values. We have to interpolate. We have to figure out where we'll be exactly for our site. Well, what's the difference between these two? Well, the difference is 0.7 minutes. And look at that. It's a minus. It's going down. As time progresses, the declination is getting less. Let's look at the values. As time progresses, the declination is getting less. That means the sun is actually heading south gradually. Is that correct? August 9th. Yes, the sun is heading south. Gradually it'll get to the equator, 0 degrees latitude, and then it'll be southerly latitudes. Okay, so the sun is heading south on August 9th. So that's why the declination is getting less. Okay, now the difference for whole hour is 0.7. So for 20 minutes, a third of an hour, we can say that's going to be roughly, if we call that 0.6, minus 0.6 instead of 0.7, we can say that the change, declination, change in declination, let's call that D, is going to, for 20 minutes, a third of an hour is going to be a third of 0.7. That'll be 0.7 minutes divided by 3. That's going to round off to 0.2 minutes. And that's a minus, remember? Minus 0.2 minutes. So our final declination will be for 19, 2013, our final declination, north 15 degrees 36.9 minutes minus 0.2 minutes, and that will give us a final declination of, here, we'll have to put it down here, 36.9 minus 0.2, that's 36.7 minutes and 15 degrees north, 15 degrees, that's the declination. Okay, so we just interpolated and got an exact declination for the exact Greenwich Mean Time that we took our sextant site. Local time, it was in the morning, but by evening, but it was evening Greenwich Mean Time. Okay, so the sun was 15 degrees north of the equator, 15 degrees, 36.7 minutes north of the equator. We're going to put a box around that declination value because that's something we'll need later on. We'll come back to that. That tells us the latitude of the sun right when we took our sextant site. Not too hard. Okay, now we did this sort of manually. We figured out the difference between these 2 hours, 1900 and 2000, and how much difference there was, how much change there was between them, and that was minus 0.7 minutes. Well, look at this. The table's kind of going to do some of our work for us. We can do it that way. In fact, it's good to understand that. But look at that value right down there. For these 3 days, the table's telling us, this is the sun column here. Go to the top, it says sun. For these 3 days, the table's telling us that the average change in declination is 0.7. It's not going to tell us whether it's plus or minus, so be careful there. You have to look in the table and see if it's going up or down. Well, it's going down all the time. Each value is less than the value before. So you're going to have to minus that 0.7. Now, that 0.7 is for a whole hour of change. How do we figure it out for 20 minutes? Well, and is the 15 seconds important? 13 seconds. Is that 13 seconds important or not? Or can we just ignore it? Well, if it changes just 0.7 minutes, that's, if we just use that 0.7 would translate into 7/10 of a mile of error if we just left that off entirely. 0.7, and we take 13 seconds of 0.7, that's going to be such a minute difference. So we don't have to worry about seconds of time. We just take our 20 minutes of time. Okay, and look at the back. Look how neat this is. For 20 minutes of past the hour, we go to our increments and corrections page in the back of the Nautical Almanac. That's the very back of the tables. Increments and corrections for 20 minutes. We take a D value of 0.7, and we get a correction of 0.2 minutes. And look, that's exactly what we got. 0.2 minutes as our correction. Here's the correction. Label everything. D correction. There's that 0.2 minutes. So the table will do the interpolation for you for the D value. Okay, but if you forget what that D means, you can figure it out. You just look at the difference between the 2 hours, and it's 0.7. It's minus 0.7, and the D value is 0.7. And then you can interpolate just in your head and get the 0.2, or you can look in the back of the tables and confirm, oh, 0.2. Yeah, that's how the table works. So you gotta, you don't have to memorize all this stuff. It all makes sense. You can figure it out just by, oh yeah, look, the difference between the 2 hours is the D value, 0.7. Okay, now Greenwich hour angle. Let's go back to August 9th, and we're on the sun. Greenwich hour angle, sun, August 9th. And this is the last thing we need, Greenwich hour angle. Look at the top of the table. You have to be careful you don't get in the wrong, wrong column. Especially the boat pitching around and you're trying to read little numbers and you'd rather be outside in the fresh air. So double check everything. Greenwich hour angle, August 9th at 1900. Here we are, 1900, 1819, and we have a Greenwich hour angle of 103:39.3. 103:39.3. 103:39.3. (103 degrees, 39.3 minutes). Okay, we don't have to say east or west. Greenwich hour angle is always to the west. So it's just a number. Greenwich, if it was Greenwich hour angle of 103:39.3 corresponds to a longitude of west 103 degrees 39.3 minutes. With longitude you have to say west or east, or else it means essentially nothing. But with Greenwich hour angle, it's always measured to the west, from east to west. Okay, and then let's take the value that's for 1900. And then let's take the value for 2000, same as we did for declination. For the next hour, for the sun, for 2000, Greenwich hour angle is 118:39.4 right there. 118:39.4. 118:39.4 minutes. That's a big difference, 15 degrees. We can't just interpolate for 20 minutes. We have to interpolate for 20 minutes exactly and 13 seconds exactly. Okay? Because the Earth's spinning really fast. For Greenwich hour angle, you have to interpolate for seconds, or else you're going to be major error. Remember, every 4 seconds is a mile, so this would be a 3-mile error right there if we didn't interpolate for the seconds as well. Well, the Nautical Almanac again is great. Sun and planets, 20 minutes of time and 13 seconds. We go to the back, increments and corrections, 20 minutes, 13 seconds, and we pull out a value for the sun. Again, make sure you're in the right column. Sun and planets here, 20 minutes, 13 seconds, right here, and sun and planets, the first one. And here's our correction, 5 degrees, 03.3 minutes, right at the top, degrees and minutes, 5 degrees, 03.3, 5 degrees, 03.3. Okay, that's the GHA correction. Okay, so 103 degrees, 39.3 minutes plus the correction. Always add the GHA correction because the Earth is always spinning the same direction. We'll all know it if it turns around and goes the other way. So for now, well, as long as it keeps spinning the same direction, always add the GHA correction. And we get 0.6, 42.6 minutes. And here we get 108 degrees. And that's our GHA. For the exact minutes, hours, minutes, and seconds of Greenwich Mean Time when we took our sight. So that's precise, and this is precise. So now we have our latitude, declination, and our longitude, Greenwich hour angle. That would be equivalent to a longitude west westerly longitude. Okay, that's what we needed. That's what we wanted. Pretty easy, eh? Only thing that I could show you is how to interpolate manually. That's not too difficult. Let's do it over here in blue. So 20 minutes and 13 seconds. It's easy interpolating for 20 minutes. That's just a third of an hour. But for seconds, we'll need to turn our minutes, our 20 minutes, into seconds. 20 minutes, 20 times 60 is 1200. So we get the total number of seconds we have is 1200 plus 13, 1213 seconds. And in an hour, we have 60 times 60 seconds, 60 minutes times 60 seconds, which is 3600 seconds. So now we need a calculator, and we do 1213 over 3600 times 15 degrees. And that's going to give us the value that we pulled out of the table, 5 degrees, 03.3 minutes. So easy to, with a calculator, it's easy to interpolate yourself, but it's still easier just to use the tables in the back, the increments and seconds corrections in the back, increments and corrections tables in the back of the Nautical Almanac. Okay, that's the sun. That's basically step 3. We corrected our time from local time to Greenwich Mean Time. We corrected our sextant site from HS, height sextant, to height apparent, and then on to height observed. So first, correct time, second, correct sextant error, and third, go into the Nautical Almanac and pull out the declination and the Greenwich hour angle. Okay, that's more than halfway there. Pretty good. But we do want to take a look at, next I think we should do planets, find the declination and Greenwich hour angle of a planet. It's very similar but slightly different. And then we'll want to do the same thing for the moon, find the declination and Greenwich hour angle for the moon. And then finally we'll do the same process, but again there's one slight difference, finding the declination and Greenwich hour angle for one of the stars. Once you figure out one of the stars, all the stars work the same way. Okay, so we're making great progress. When we finish with the Nautical Almanac, then we'll go into the site reduction tables and figure out how they work. Okay. You know what we're going to do with these numbers, if you remember where we were at with part 1. But let's look at it here quickly and see what those numbers do for us. Here's the Earth here, and a little flat on this side, I'm afraid. Let's get that a little rounder. Here's the Earth here, and here's the equator, North Pole, South Pole, and let's place the sun on the Earth. 15 degrees north, latitude is 15 declination, or latitude is 15 degrees north. Here's Greenwich, line of Greenwich, 0 degrees longitude. There. 15 degrees north of the equator and 108 degrees west of Greenwich. So we're 108 degrees here and 15 degrees north here, and that's the GP of the sun. Then, based on that ground position of the sun, we take our sextant reading, and let's say we had an HS or an HO. Remember, HS is corrected to HO. We had an HO of, let's take something simple. Let's say an HO of 65 degrees. 90 minus HO is our distance from the body that we shot. So our distance is equal to 25 degrees. And so we are 25 degrees away from the GP, which defines a circle around the GP similar to that, and with a radius of 25 degrees. And that's a line of position. We are someplace on that blue circle here. Okay, what we're doing here is not too complicated with the Nautical Almanac. All we're trying to do is get the latitude and longitude, which we call latitude declination, and they're exactly the same, north or south latitude, north or south declination, same as latitude. And the Greenwich hour angle is in many cases equivalent, exactly the same as longitude. All of the Western Hemisphere, all of the longitudes from 0 degrees to 180 degrees west are exactly the same as Greenwich hour angle. So not complicated what we're trying to do. Just find the position of the sun, or this, in this case that we just worked out, the sun, or the celestial body that we shot. The point where if you were standing there, that body would be directly overhead. That's what we need to find out. So not complicated, little interpolation. As we found with the sun, the declination doesn't change very fast. That's true of most of these. The moon, it changes a little bit faster though, so we'll figure that in a little bit more prominently. But usually the declination doesn't change much because most of the motion of the planets and the sun, all the celestial bodies, is caused by the Earth spinning so fast, 360 degrees in 24 hours, all the way around every day. So we have to be fairly careful about interpolating for the Greenwich hour angle to get the exact minutes, hours, minutes, and seconds of the GHA for the exact hours, minutes, and seconds when we took the sextant site. Remember that 4 seconds, if you're wrong by 4 seconds, that's an error of 1 mile or more, but nominally 1 nautical mile. So you do want to be careful about interpolating and be careful with your time and all. Now, the sun, hopefully that's pretty clear. Sun's probably the simplest, but the other bodies are not much different, but we'll take a look at them because there are minor differences. Again, it's better to understand the stuff so you can figure it out 5 years from now rather than to memorize it all. So I'll try to show you how it works, and then once you understand how it works, it's pretty obvious to go back and say, oh yeah, I remember, look at this is how it works. Okay, so the sun, let's take, this was the sun, now let's take a planet. All the planets basically work the same way, so we can just do one of the planets. Let's do Venus. That's the easiest planet to shoot. And let's take the same date, August 9th. And what time should we do it? Let's go into, well, let's take a morning sight on Venus. Let's say our local time was 6, and let's not use the same minutes here. Let's go 6:30:45 for our local time. And then let's give ourselves a new longitude, because I'm not sure if Venus has risen at that point, at this longitude. Let's put ourselves in the Atlantic this time, and we'll go at 56 degrees longitude, local longitude. So our time zone, 56 divided by 15, is going to be, 3 and 11/15. So that bumps us up to a time zone of 4. So our time zone difference is +4 because we are later in the day than Greenwich. And so Greenwich Mean Time, it's sort of mid-morning in Greenwich Mean Time, is going to be here. And we still have the same watch error of -2. So we get 1000 hours here, 30 minutes, and 43 seconds. So 10, 30, 43 is our time. Corrected for watch error and the zone difference. Local time corrected to Greenwich Mean Time, labeled Greenwich Mean Time. Okay, let's come over here and take these out. And here, and take this out. Okay. And we're still looking for the same thing. We're looking for the declination and the Greenwich hour angle for the exact hours that we shot those sites. Okay, so we're still trying to get the same things. Greenwich hour angle and the declination. Okay, so let's plunge into the tables for August 9th, looking for Venus. And again, it's the Nautical Almanac. And here's Venus right here. Venus, the brightest planet, -3.9 magnitude. This is August 7th, 8th, and 9th. August 9th is the bottom, and we're in the column right next to Aries. We'll talk about Aries later, as I said. August 9th. And our Greenwich Mean Time is 10:30:43. So we'll go in for 1000 hours. 1000 hours, Greenwich Mean Time. And here are values for GHA and declination. Remember, the north 11 has to come down in declination. It has to be carried all the way down for each of the declinations. So we have 313 degrees, 0.1 minutes. 313, 0.1 for GHA. Minutes. And that's at 1000. Let's put our 1000 over here. And it'll go all the way across. Okay, and for the declination, for Venus, we have 1000. We have, here we go, let's see, 1000. North 11, 54.4. North 11, carry that down, 54.4. Minutes. Okay, we better draw a line down there, keep them separate. Okay, now let's see what we've got. Venus. Let's look at the declination first. 1000. Let's look at how it changes. Declination. North 11, 54.4, and then it changes to 53.2. So that's going down. It's as time progresses, the declination is going down. This is the Venus is moving very gradually to the south at this point. The northerly declination is becoming less and less. So that's a change of 1.2 minutes. And now look at the bottom. Well, that's close enough. 1.1 D D equals the change in declination, 1.1. They give a value that's approximately correct for all 3 days. If you want it to be more precise, you could use a D of 1.2 because 1.1 applies for all 3 days as being the closest value, average value. Okay, so D equals 1.1. Well, that's 1.1 minutes. That's a pretty small change, isn't it? That's not, even if we just ignore that, that's not going to be a huge difference. But let's not ignore it. It'd be a 1 mile difference, right? 1 mile error. So if we are over the full hour for 60 minutes, a change of 1.1 minutes would be equivalent to, and if we ignored it over a whole hour, it would be equivalent to a mistake of about just over 1 mile. So let's use it, but we can just look at that. We're at 10:30:43. Well, we're halfway between 1000 and 1100 hours. So let's just take half of that 1.1 and say it's going to be a 0.6. Well, in fact, it was 1.2. Actually, the average value was 1.1 for the 3 days. So we'll take half of 1.2, and we're going down, remember? So that's a minus 0.6 minutes. And there's our declination. Now we can check that if you want to do it technically. Often with the declination, you can just look at it and say, oh, that's going to be about, a third of the way through the hour, or halfway through the hour, or 45 minutes, 3/4 of the way through the hour. And you can get a value that's plenty accurate for declination in a lot of cases, because the declination is not changing much. But let's do it the technically correct way. And we'll go into the page for 30 minutes and pull out and go to a D value of 1.1. Here's 30 minutes. And here are the D corrections, 30 minutes there. And D value of 1.1 for 30 minutes. And the correction, the D is going to be in this line, and the correction is going to be in this line. And we'll find that it's close to what we guessed. If we can read the table. 1.1. And there's the correction. So here's the D value, 1.1. And here's the correction, 0.6. So exactly what we guessed. I mean, we didn't just guess, we just figured it out in our head quickly and easily. Or you can do it with the tables. Okay, now, well, let's do that math. So we get 53. Let's make that a bit bigger. 53.8 minutes north, 11 degrees, 53.8 minutes. Okay, and that's our declination. That's all there is to it. That's our answer. North 11 degrees, 53.8 minutes. Okay? Really hard, really difficult, really confusing, eh? If you can subtract. Remember to subtract, though. Remember to look and see. The D value doesn't tell you plus or minus. So you do better not to interpolate for declination than to go the wrong way with it. Okay? So a little bit of attention, Make sure you're interpolating between the 2 hours where you took the site. Okay. Now let's get the GHA. GHA is always a little bit more involved because the GHA changes quickly. We can't just look at it and say, well, I guess it'll be about that. Okay, so Venus. Now for the next hour, Venus, for 1100 hours, GMT, the value for Venus, let's write it up here, was 327.59.7. 327 degrees, 59.7 minutes. Okay, what's the difference between those two? Well, the difference is, I'll write it in here, 14 degrees here, and 59.6 minutes there. GHA always is going up, so we're always going to add the GHA correction for minutes and seconds of interpolating. Okay, 14 degrees, 59.6. Well, how are we going to do that interpolation? Well, here we are at the back for 30 minutes, right here in the Sun and Planets column. Right here, Sun and Planets, right here, this first one, 30 minutes, Sun and Planets. Well, Venus is a planet, that sounds really good. Okay, but the problem is Venus doesn't necessarily move the same speed as the Sun, does it? Because this didn't move 15 degrees in 1 hour. If we went to a 1 hour interpolation for Sun and Planets, 1 hour would be 59 minutes and 60 seconds, right? So if we interpolated for 1 hour, we're not going to get the right next value for Venus, because here's Sun and Planets. Whoops, that's the correction. Here's Sun and Planets right here. 60 minutes. This is 59 minutes 60 seconds. That's 1 whole hour, and the correction is 15 degrees. Well, there's Sun and Planets, right? Yeah. So we'd have an error there of 0.4 minutes in this case. So what do we do with that? Well, let's take our interpolation for 30 minutes and I'll show you what we're going to do. Let's just hold on to the thought that our error here is 0.4. We're 0.4 short, right, of 15 degrees. If we interpolated for a full hour and added 15 degrees, we'd come out too high. We're short of 15 degrees here by 0.4 minutes. Okay, now I'm going to show you how we do this. The first we'll take the correction for 30 minutes from Sun and Planets. And we know that's not going to be exactly accurate, right? Because for an hour it wasn't accurate, so for 30 minutes it's going to be a little bit off as well. Okay, so here's our Sun and Planet, 30 minutes. See if we can stabilize here. 30 minutes, Sun and Planets, right here, first column. And we have 30 minutes and 43 seconds. Now we can't just take minutes now, because every second counts with GHA, because the Sun is moving so fast. So 30 minutes, Sun and Planets, and it's 43 seconds. Double check, yes, 43 seconds. Sun and Planets, 43 seconds. So we're going way down here. 43 seconds, and we get a correction of 740.8. 7 degrees, check the top of the column, it'll tell you. 7 degrees, 40.8 minutes. 7 degrees, 40.8 minutes. Oh, 7 degrees, 40.8 minutes. That's the correction. Okay, but remember, there's an error involved in that, because Venus has its own orbit. It's not just moving because the Earth is spinning, it's also moving in its own orbit through the sky around the Sun. So what are we going to do? Remember, we had a 0.4 difference. Well, let's look back at Venus in the daily pages. Here's Venus, and lo and behold, right at the bottom, oh, that's what that V value is. Well, again, that's an average V value for 3 days, minus 0.5. We know that the actual difference is minus 0.4, but how much of a difference is that? 1/10 of a mile, 1/10 of a minute, it works out to 1/10 of a mile of difference. If you want to use 0.4, it's better than what the table gives you, but either way, you can use either one. Okay, and what do we do with that? That's over a whole hour, it's off by 0.4. So we're going to end up with half of that. So we're going to take a minus 0.4 2 minutes. Okay, and that's going to be a little bit 1/10 different from what the table tells us. So we've got a V of minus 0.5 for 30 minutes. Let's go into our pages at the back again for 30 minutes. And this time we're going to take a V correction. Ah, that's what the V correction is. A V correction for 30 minutes. Whoopsie, where's 30 minutes? Here's 30 minutes. 30 minutes. Here's our corrections, V or D. We have a V right at the beginning of the table. The V, here's a V or D, and here's the correction. V of 0.5 is what the table gave us. So that would be a 0.3 correction. But we know it was actually a correction of 0.4. So the correction would be 0.2. Okay? And that's what we have. And remember, it was a minus because the values are going down. And if we look back to August 9th in the daily pages, indeed the table actually does us the courtesy of telling us it's a minus. So that's helpful. So August 9th, Venus down at the bottom, the V value, yes, minus 0.5. That's because these values are increasing by almost 15 degrees per hour, but not quite 15 degrees per hour. They're increasing by 15 degrees per hour minus 0.5 minutes. Okay, so the D value and the V value are work slightly differently. The D value is, here, where are we? Venus, this column here. The D value is actually the difference between each hour in the difference in declination from one hour to the next hour. The V value, however, is not the difference. You can just look at it and see that's not the difference between 1 hour and the next hour. That difference is much, much bigger than the V value. The V value is just how much the difference from 1 hour of GHA, Greenwich hour angle, to the next hour of GHA varies different from 15 degrees per hour. So that can either be a minus or a plus. So the V value is the change per hour is about 15 degrees, but it's not quite 15 degrees if V is minus. The D is the actual change from 1 hour of declination to the next hour of declination. Okay? So that's those mysterious V and D. Remember, at the top of the table, the numbers, Venus, minus 3.9 is the magnitude. Minus magnitudes are huge, incredibly bright, beautiful planets or stars. Plus magnitudes, as the plus magnitudes get to be larger and larger plus numbers, the star becomes less and less visible, less and less bright. So a magnitude plus 10 would not be a navigational star. You wouldn't be able to see it clearly enough through the sextant to use it as a navigation star. So all the planets are really quite bright. Jupiter's the other next brightest, minus 1.7. Okay, so let's get our GHA now. We just have to add these things together, and we've got the got this part of the problem solved. Let's turn. There we go. Okay, so be a little careful. This is minus, and this is plus. So 40.8 minus 0.2 is 40.6. Plus 0.1, 40.7. 40.7 minutes. And over here, 313 plus 7. Remember, GHA corrections are always plus because the Earth is still spinning the same way. So 313 plus 7 degrees is 320 degrees, 40.7 minutes. And that's it. That's all we want. Okay, let's blast ahead and see if we can cover the moon quickly here. The moon is basically the same. We're going to look for its value. It's the value for its declination and its Greenwich hour angle. Exactly. Let's use the same time. 10:30:43. Let's see if the moon was up on August 9th then. In fact, one of the uses of the almanac is to figure out which planets are which, because it tells you where the planet is. And if there are two planets and you're not sure which is which, they're both visible, they're both about the same elevation, that would mean their declination was pretty similar. One might be further west than the other one, and you can look in the almanac and say, oh, that's got to be Jupiter because it is farther west. And you can also check the brightness. Oh yeah, Jupiter's brighter this time of year than Saturn, and that must be Saturn because it's farther to the east. The almanac tells you those things, so that's very helpful. So let's see if we'd be able to see the moon on August 9th at GMT of 10:30. So we'll look under the moon tables. August 9th, moon at 10:30 GMT, and here we are, moon, August 9th, down at the bottom, that's August 7th, the first page, 8th, or the first top of the page, August 9th, and remember moon is one in, sun and then moon. Okay, August 9th, moon, 1000 hours, GHA of 194 at 1000 hours. 194. Greenwich hour angle of 194, and we're at 56. Can't see it. Okay, so let's go back over to the Pacific coast and put in our earlier longitude of 129 degrees. So we're at 129 degrees on the Pacific coast. That's west longitude. 129 west. And divided by 15, that gives us 8 plus 40 and 9/15. So that's going to round up to a time zone of 9. And local time has to change as well to shoot the moon, so we're getting a Greenwich Mean Time of 1000. So okay, 45, and our watch error stays the same. Watch error minus 2 seconds. Okay, so let's check this. We're at zone 9. We took our sight at 1:30 in the morning on August 9th. And we could do that because the moon was so bright. We had a horizon created by the moonlight. Otherwise, the stars would not be visible. The stars would be visible, but you wouldn't be able to shoot them because you wouldn't be able to see the horizon underneath them. But the moon at 1:30 at night, if it's bright, will create a pathway on the water, and right at the end of that pathway is the horizon. So sometimes you can shoot the moon late at night like this. So we shot the moon 1:30 in the morning, 1:30:45. Our watch error is minus 2. Our zone is 9, and so we get a GMT of 10:30:43, and we should be able to see the moon at that time, at that longitude. So let's get these numbers out. And this number out. And this number out. Okay, and moon. We're going for the same things though. All we want is the declination GHA. That shouldn't be too hard. Now let's look at the moon here at the top. Look. Well, we're familiar with the concept of what the D value is. and the concept of what the V value is. With the moon, instead of averaging the V value for 3 days and putting it at the bottom, they put it for each hour. Well, that's the reason for that is it changes pretty fast, because the moon has a much more complex orbit than the planets. It's going around the Earth, and it's traveling fairly quickly relative to the planet's motion that we see from the Earth's surface. So the V is changing quite quickly throughout the 3 days. Here was 9.2. After 3 days, it's changed to 20. Oh no, that's the wrong column. It's, columns. It's changed to, way at the bottom, after 3 days, changed to 11. So that's quite a change. 9.2 to 11. So they don't want to give an average V value for the moon. The D value is also changing relatively quickly. Look at those changes just in that one page. That's because the moon has its own fairly rapidly moving orbit. So the declination is actually changing. Now look at the declination. You can see right at the top, the declination goes from south 2304.6 to south 2308.2. That's a change of almost 4 minutes, 3 minutes and 3.6 minutes. Oh, well look, there's the D value, 3.6. So the D value is the same concept, just the change, hourly change from 1 hour to the next in the declination of the moon. Okay, and you can see the D value changes quite quickly through that day. So don't take a D value just at the top of the table. You have to take the right D value. Okay, now GHA, how's that working? That V, remember the V usually isn't the change over an hour. And no, it can't be the change, 9.5 minutes, 9.2 minutes rather. That's not nearly enough change for the longitude of the moon. The moon isn't moving quite at 15 degrees per hour, but it still has a lot of that 15 degree component due to the Earth spinning so fast. Remember, the moon rises about an hour later, 53 minutes or so later each day. So the moon GHA is going to be, what does that make it? A little bit more or a little bit less than 15 degrees? Well, look at the numbers. There from the first value for the moon, 75 degrees, 05.3, to the next value for the moon, 89, 33.5. So that's 14 degrees 30 minutes, right? Roughly. Look at the numbers upside down. Anyway, it's different. Let's take a look at, let's look at our moon at 1000 hours, the hours we're working with. Okay, on August 9th, down at the bottom, Sunday 9th. This is where the tables are sometimes a little tricky coming across. Remember that first one is sun and planets, or sun rather, sorry. And the next one over is moon. So 1000 hours, and come across evenly, we get 194.51.5. 194.51.5. 194.51.5 minutes. 194 degrees, 51.5 minutes. And I'm just going to double check that. Moon, 1000 GMT, 194.51.5. And we have a V value of 10.7. V equals 10.7. Okay, and then for the next hour for the moon at 1100 GMT, we have 209, 21.2. 21.2. And again, double checking that. That's where you're going to make your mistakes, is just getting on the wrong line, or pulling the wrong number out of the table in the wrong column or something like that. Okay, what's the difference there exactly? How fast is the GHA of the moon, the longitude of the moon, changing? We know it's not going to be too different from 15 degrees because most of the moon's motion is from the Earth spinning. But let's see what we get. So here's 15. Let's see, we're going up in value. So we're short here by 8.5 minutes, and then we have 21.2 minutes here. So that's 8.5 plus 21.2. So we have 29.7 minutes of change in minutes, and here we're going up, that's higher, and this, but we borrowed, did we borrow? Yeah, we borrowed 60 from here, so we have 208, so we're 8 plus 6, 14 degrees. Okay, so 14 degrees, 29.7 minutes is the change per hour. Oh, but wait a second. This V value doesn't work really, does it? That's supposed to be the difference from the change of 15 degrees per hour, isn't it? That's what we found with the planets. This is off by almost 30 minutes, not by 10.7 minutes. Oh, well, wait a second. That's using the sun and planets. We don't use the sun and planets for the moon correction. We use the moon correction. Let's look at 59 minutes and 60 seconds. 59 minutes, 60 seconds, the very bottom. And in the moon column, right next to the double lines there. So here we are. What's the change for an hour for the moon? 14 degrees, 19 minutes. So really different from the sun and planets. 14 degrees, 19 minutes. Oh, we're going to run off the board there. Let's go over here. 14 degrees, 19 minutes. And now, oh, look at that. We add this V correction for the whole hour, plus the moon's movement for the whole hour, and 14 degrees, 19.0 minutes, plus the V value, we get 14 degrees, 29.7 minutes. Oh, look at that right there. 14 degrees, 29.7 minutes. That's how much the moon moves in an hour on August 9th, around between the hours of 1000 GMT and 1100 GMT. So we could just interpolate for this. We can to interpolate for minutes and seconds. We can turn the 30 minutes into seconds, and then divide it by the number of seconds in an hour, 3600, and then multiply it times the change. But we can also just use the tables. We go to the moon for 30 minutes and 43 seconds. Those are the corrections, and then we'll take the V correction. So we go for 30 minutes, 43 seconds in the increments and corrections under moon, right? Yes, don't go in the sun and planets. This is the moon. Okay, so 30 minutes, go down to 43 seconds. So here's 43 seconds. Go across the moon, and we get a value of 7 degrees, 19.8 minutes. 43 seconds, 7 degrees, 19.8 minutes. We're going to put that in here. Seven degrees, 19.8 minutes. Okay, Now the V correction for 30 minutes. The V for 30 minutes here at the top. The V correction, now we go over to the corrections, and we go to a V of 10.7 and go down to the V value here and the correction over here. V value of 10.7. Oh, where are we going? It's pretty high. We have to go way over here. 10.7. Okay, V value of 10.7 and a correction of 5.4. Okay, well that makes sense. We're doing it for just over half an hour. So it's 10.7, 5.4. That's half of 10.7. 5.4 minutes. And let's check. Do we have a minus V or a plus V? We had a plus V. Okay, I think V's always plus for the moon. They give us a low value in the tables for how the moon's moving, and so V's are always going to be plus for the moon. Yeah, all of these are plus for the moon. And the GHA correction, this is the GHA correction. This is the GHA at 1000 over here. And the all the corrections are plus, 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 plus. And so it's 12, 17, that's 11, 16, that's 76.7 minutes. Let's move our V value out of the way. We don't need that anymore. $76.7 minutes, and this is 101 degrees. This bumps up to another degree, so we have 102 degrees, 16.7 minutes. That's the GHA, 102 degrees, 16.7 minutes. Declination is going to be easy. We just take our D value. August 9th. Did I switch pages on you? Hope I didn't switch pages. August 9th. No, we're good. Yeah, here we go. Okay, so the D value, the declination value, we don't have the declination yet, for 1000 is here, 2310.7. That's the column for declination, 2310.7. Double check that for 1000. Oh, that was 900. For 1000, 2307.4. For 1000, 2307.4. 2307.4. .3 degrees. Okay, but now be careful. Whoa, moon. Look at that. South for 1000. South. Oh, where's the south? South. Oh, the south is right up here. You have to bring that down. It's south. South. That makes a big difference. It's below the equator. South of the equator. 2307.4. So don't miss that S. The S makes all the difference. And then the D value is for 1000. The D value is, stay in the right column, 3.5 right here. 3.5 for 1000. 3.5. You have to go all the way to the top to see the D value, because it's right next, squeezed up kind of close to the HP value. Okay, 3.5, and that's how much the declination is changing per hour. 3.5, that's the average for all three Oh no, that's not the average. That's the rate for that hourly change, 3.5. So D equals 3.5, 5 minutes. And is that plus or minus? Well, let's take a look at it. Makes a big difference. Here's 1000 hours. The moon is going north or south? D is going from 07.4 to 2303.6. So that's D value is going to be a minus there, isn't it? 07.4 to 03.6. 03.9, I'm sorry. So the D value is a minus. It doesn't think to tell you that. You just have to pick that up. Okay. Remember, you're just interpolating between those two. If it's getting less as time progresses, the D value has to be a minus. So minus 3.5, and then up here, well, we can just look at it and interpolate for that. It's not a big change, 3.5. We don't want to ignore it, but it's for half an hour, it's going to be half of that. So that'll be 1.7 minus 1.7 minutes. Okay, in fact, keep your columns lined up. 1.7 minutes. So our declination is going to be 23, whoa, south. Don't miss that. South. 23 degrees. Let's see. 7.4 minus 2 would be 5.4. We took off too much, so we've got 5.7 minutes. Okay, so south 23 degrees, 5.7. Whoa, south. That's how you make mistakes. You know, we've been working with the sun, the planets, August, everything was north declination. All of a sudden now the moon's south of the equator. We have a south declination. And it's not even that obvious in the table because that south has to be, you have to bring it down. So that's the type of mistake you'll make. You've just been assuming everything's north declination. So south 23, 5.7 minutes. And that's the location of the moon. So not too hard. Let's see where that is. Here's our globe over here. Can we see the globe? Almost. Let's look where the moon is. Okay, so we have a GHA, or longitude, of 102 degrees. GHA of 102 is the same as west 102 longitude. So that would bring us over 102 degrees to the west from Greenwich longitude, 0 degrees longitude, and a south declination of 23 degrees. That would bring us south of the equator, 23 degrees. And here is the location of the moon when we shot it. So that's it. That's all we need. The Greenwich hour angle and the declination. Okay, so things to remember. Remember that the GHA correction for the moon is not the same as for the sun and planets or for the stars. You have to go for moon, and the column says moon. They always underestimate that. So you're always going to be adding your V correction. The V correction is just based on the V value for however many minutes you took the site after the whole hour. You don't do a minutes and seconds correction there, just for the minutes. Okay, and because the V correction is fairly small. Remember, our V correction was 10.7. The big part of the correction is the GHA correction, and that's based on the Earth spinning so fast, and So you do have to do minutes and seconds for GHA. You just go to the minutes page and then go down to the right number of seconds in the increments and corrections pages. And that gives you an exact reading for the exact GMT 10:30:43. Okay, and you add all the corrections for the moon, and you can double check that. You don't have to remember, oh, I have to add all the corrections for the moon. Double check it by going to 59 minutes, 60 seconds in the incorrect corrections, and take your V value and see if it works. Do you have to add them to get to the next value? Check it. Don't try to memorize it. Just know that you can always go to 59 minutes and 60 seconds and see if what you think is the right way to interpolate actually gets you to the next hour's value in the table. So you don't have to really know it. Just know that it all makes sense. It's not hocus pocus. It's nothing mysterious that you have to kind of just memorize because you could never figure it out because it doesn't make any sense at all. Of course it makes sense. Everything makes sense in math. So and remember the difference between the V value and the D value. The D value is just the change in declination per hour. The V value is always an added correction for the GHA. Okay, so that's the moon. Good job, well done. We're on to, well, we've done the sun and the planets and the moon. What's left? Well, all the stars, the navigational stars. And the stars are fun to shoot and fun to start to learn the stars. When you go outside, no matter where you are in the world, you're at home if you know all the stars and can recognize the patterns. So the stars, if you know a few constellations, you can start to place other constellations and stars with the ones you know in relation to the ones you know. But it's a marvelous thing just going outside and feeling familiar with the sky above you, even if you can only see one or two stars because of clouds or other trees or clouds or anything. It's like, oh, there's Sirius. Oh, there's no Sirius, okay? Oh, there's Venus. That must be Venus. It's right near the setting sun. Or the morning star. There's Venus on the other side of the sun coming up before the sun. So a lot of fun stuff here. And stars... Again, we're just going to be pulling out the declination and the GHA. The only difference with stars is they don't want to have a whole column like the moon for every star, or the sun, or whatever. They don't want to have a whole column for every star. So they're going to do something, one extra step that is simple enough to do to get the Greenwich hour angle of the star. You'll find that the declination of the stars is relatively easy because the declination does not change very fast. Okay, so stars, and then we'll be on to the last step, which is using the site reduction tables to pull out a height computed. The computed height that we would have gotten if we had been at the position that we chose as our assumed position. So just one more step and you've got all the numbers under your belt. Not too hard. It's really not too hard. A little bit harder when the boat's pitching around and you keep dropping. The table keeps sliding off the table and the nautical almanac keeps sliding off your navigation table and your pencils are going all over the place and everything. But no, it's really not very hard at all, and you can work out a whole site, a whole position with a couple of sites in about 15 minutes, 10-15 minutes. Okay, we'll do stars very soon. Okay, let's blast ahead and do the stars. You're doing great. You've done the sun, Greenwich hour angle, and declination of the sun for precise hours, minutes, and seconds of a certain day. You've done, what did we do next? Then you did the planets. You did Venus. The other planets are just the same as Venus. And then you did the moon. A few more variables there, but not much different. Getting the GHA and declination for the moon. Basically the longitude and latitude of the moon. And then the last thing is the stars. And then we're through with the Nautical Almanac, and we're on to the site reduction tables for the final step of in the tables and getting out the last information we need to plot your position. So we're doing great so far. Any questions? Hope not. And all these are sort of starting to seem a little repetitive, aren't they? All we're doing is going into the tables for the right date, the right time, and pulling out a Greenwich hour angle, which is exactly the same as longitude in the Western Hemisphere, and a declination, which is always exactly the same as latitude. So Greenwich hour angle and declination of the planet or star or celestial body that we're shooting. And guess what we'll be getting for the stars? We'll be getting the declination and Greenwich hour angle. In one way, the stars are simpler than some of the other planets, some of the other bodies, because the stars' declination really doesn't change very much over the time period we're looking at. The Greenwich hour angle of the stars, however, does change quite rapidly because, again, the Earth is spinning 15 degrees per hour. So let's take a look at the stars. How do we do the stars? Well, the first caution is here are our stars on this sort of insert in the Nautical Almanac. On one side, same list of stars on both sides here. On one side it's alphabetical, on the other side it's by, how is it by? It's not order of magnitude. Oh, it's by SHA. Yeah. On this side it's by SHA. New term. Oh, a new new initials. SHA. Well, we don't know what that is yet, do we? Declination. Oh, we know what that is. Mag, that's magnitude, name of the star, and number. They're numbered by, in order of their SHA, sidereal hour angle. Hour angle. Oh, that must relate to Greenwich hour angle. Hour angle, that's caused by the Earth spinning at 15 degrees per hour. So, well, we'll have to talk more about SHA, sidereal hour angle. Now, over here, the stars are there as well. But what I wanted to show you was declination. Oh, they give you declination for the stars. Well, wait a minute. Are all the stars at whole degrees of declination? If they're not, we could be up to 59 minutes of declination wrong. In fact, our final answer for our problem might be up to 59, well, probably they'd round this up or down, so might be up to 30 miles off. That's a big error. So what I want to warn you about is these are just approximate declinations. They're rounded off to the nearest whole degree. This is an average declination for each star over the course of a year. So we can't use these declinations. These declinations are just given you to help you find the stars, to help you locate and identify which star is which. These are approximate declinations. Okay, the SHAs are also, the SHAs are a little bit more precise, but they're also approximate SHAs, just to help you identify the stars. And they relate to hour angles. So starting at the bottom, the first star has an SHA of 14, the next is 16. Those stars are fairly close to each other as far as longitude, but you can see they're quite different in terms of declination. One's north 15 and the other's south 30 degrees. So, so they're not going to be actually close to each other in the sky. But if you took, let's see if we can find two that would be close to each other. This has an SHA of 14 and north 15 degrees. Here's a north 10 degrees and an SHA of 34. So those two stars are going to be fairly close to each other. This 20 degrees apart from each other. This one is 20 degrees further to the west than this one, based on the SHA being different by 20 degrees. So but they'll be at about the same height when they're both near the zenith. North 15 and north 10. This one will be somewhat farther south in the sky than this one. So this is just a cheat sheet. But when we go into the daily tables, all of a sudden we have much more precise information for the stars. So here's the star column on the daily tables, and these are all alphabetical. Let's see, let's take a look at Sirius. That's my favorite star, the brightest in the heavens, and always easy to pick out. Now let's go back to the top. SHA is the first column. We still don't know what SHA is, sidereal hour angle, whatever that means, and declination. Okay, and Sirius. See Sirius. Where's Sirius? Somehow in the viewfinder it's all backwards for me. Sirius here. So SHA is 258 degrees 47.9 minutes, and declination is south 16 degrees 45.4 minutes. Okay, so Sirius is actually south of the equator, but since it's only 16 degrees south of the equator, we can see Sirius from most of the northern hemisphere, but it'll always appear to be in a southerly direction if we're in the northern hemisphere. Okay, so you can see that's a much more precise declination. And at other times of the year, because of the Earth's orbiting around the Sun, this declination will be slightly different later in the year. But look at the bottom of the table, the star column here. There are no V's or D's, right? There isn't any V or any D value. Let's check what we're doing here. This is all part of, I want you to see how you can figure this stuff out. Here's the sidereal hour angle, 528, and this is good for all 3 days here. 528, 47.9. Let's go a day later. Are we going to have to interpolate for that? Here's Sirius. 258, 47.9. Almost exactly the same for the next 3 days. Let's check the declination and then here, and then we'll go back to the previous page. Declination, south 16 degrees 45.4 minutes. Here, the previous page. Sirius, south 16 degrees 45.4. Does that change? South 1642.4 and south 1642.4. So no, exactly the same declination. If we go to a much later part of the year and look at Sirius, we should see there is a change. See, big change. Sirius, south declination, south 1642.3, changed by a tenth of a minute. If you used, and we went quite a bit farther back, November versus June. So you can almost pull your declination for Sirius out of the tables anywhere, any page, and you're not going to be off by very far. And let's check the SHA. The SHA for Sirius here in November is 258, 47.0 versus here in June, $258, 47.9. what was... So a bit more of a change there with SHA, but not a huge change. So look at that. We're not going to have to interpolate for an hour of SHA or declination. Doesn't matter. So let's start with our declination. We don't know where the SHA is yet, so let's start with the declination. We know what that is. Okay, and so we're through with this, but we can leave up our declination. We don't need a D value, since the declination really almost doesn't change. And we're going to be working over here, more significant calculations over here, to get our GHA of the star. We want to end up with a GHA of the star, just like all the other things we've been working with, and a declination for the star. Okay, so, wow, declination, we don't even have to write anything up here. Let's take our time. Let's take this same position, and I wonder if Sirius is going to be visible. Where are we? We're west longitude. If we take a local time of, let's take a local time, August 9th of 9:30:45, and Sirius won't be visible on August 9th at that time. Let's take a different date entirely. So let's take December 9th, and let's take a local time of 8:30:45. That's probably a little bit late to be shooting Sirius in the winter. Although if we're farther south, we'd be okay. So let's go ahead with this, December 9th, local time 8:30:45. That gives us a Greenwich Mean Time of seconds, so watch error of minus 2 seconds, correction. So 43 seconds, 30 minutes, and our zone is still based on west longitude of 129. 129 divided by 15, 8 and 9/15 gives us a zone of 9, rounded up. And so we get 17:30:43 for our Greenwich Mean Time. Good. Take this out of here. Okay, declination. Do we have a lot of steps in here to get our declination? No. December 9th. Oops. Label everything correctly. Here we are. That's not Venus anymore. This is Sirius. S-I-R-I-U-S. Very serious to label everything. Okay, don't forget to label things. Every problem you do, label it all, or else you'll get totally lost. You'll make mistakes just because of labeling. Okay, December 9th, Sirius. Also, if you try to hold too many things in your brain, as you get more and more numbers, as you get through into the tables and stuff, you're trying to hold a lot of stuff in your brain, you're going to get confused and you'll start making mistakes that way too. So write everything down, make it all really clear, make your numbers very, very precise and clear, line everything up exactly right in columns so you can do your math, adding and subtracting easily, and label everything. December 9th, here we are. And we're doing Sirius for Greenwich Mean Time of 17:30:43. Here's Sirius. Declination south 16 degrees 42.4. You might have guessed that. Now, a real good practice is to write your number down and then look back in the table and check it, because you'll find that you've skipped a line or jumped a line or a column or something, and when you go back and check it, it's like, oh wait, I got the wrong number. But here we are, we're right. South 16 degrees, 42.4. So that was pretty easy, right? We got our declination already. So stars aren't so bad as we thought. I was leaving for last and you thought, oh, this must be really hard. No, the declination is simple. Just pull it out of the table. Even if you went to the wrong months, you'd probably be fine with the declination. But go to the right set of 3 pages. Okay, now you have to understand SHA. This is where stars are just a little bit more complicated because they don't want to have to do a whole thing like for each planet. They could do the stars this way, a whole column with all the GHAs for each star, and then you interpolate between them. They could do that, but the nautical almanac, there'd be 30 for each one of these. There'd be like 6 to 10 pages. The almanac would be huge, thick volume because they'd be trying to get 30 stars instead of just 4 planets. 1, 2, 3, 4. Instead of just 4 planets, they'd be trying to get 30 stars with all these columns. So rather than do that, since all the stars stay fixed relative to each other, we saw very little change in SHA over the course of quite a few months. Little change, but very little. The stars are basically fixed in place, and the only thing that changes the SHA is that the Earth is moving around the Sun in a fairly large orbit, and that's going to change the SHA just a little bit because we're looking at the stars from a slightly different position as the Earth gets on the other side of the Sun. But relative to the distance of the stars, some of them are thousands of light years away, relative to the distance of the stars, the Earth's orbit around the Sun is a piddling little, minute amount of space. Okay, so the SHA is not going to change very much. But what is SHA? Sidereal hour angle. That's this is where we're going to be working on the GHA. Now we can take some of our space out from the declination. Sidereal hour angle. Okay, now we're going to put that right here. Well, actually, I'm going to put it down just a little bit. SHA for Sirius. What is our SHA for Sirius? And here we are again. Right here, 258, 46.9. 258, 46.9. Minutes, degrees, minutes, and degrees and minutes. Okay, that's SHA. We don't have to interpolate or anything because it's not changing. We checked several months, earlier, and it didn't change much. So SHA is, you want to get it from the right set of pages. Those 3 days on the one page. Don't be 10 months earlier or something, but SHA is not going to change very much. Okay, now we go. Here's that mystery column, Aries. Very strange column because it's just GHA. There's no declination. What use is Aries if there's no declination given? Oh, wait, here's an idea. Let's look at our globe here, see if we can see this. And all there is a longitude given, the Greenwich hour angle for Aries. Well, let's take December 9th and look and see what we've got for Aries on December 9th at, Greenwich Mean Time, 17:30:43. This is December 9th. This is GMT along the side, 1700. Aries is 333:41.1. 333:41. 41.1. That's the GHA of Aries, right? Now, what Aries is just a line. It's going to be a little hard to draw that with our Greenwich hour angle here. Well, let's do that. We've got some big numbers there, don't we? Let's see where we can get. We're going to have to fudge things a little bit. Okay, so this is Greenwich here, 0 degrees longitude. And we have a GHA of Aries, which is, Aries is just going to be longitude, right? Doesn't tell us anything about latitude, no declination. Well, 333 all the way around is 360, back to Greenwich, you're back to 0. Okay, 333 degrees is going to be east to west, around almost back to Greenwich, but not quite. 27 degrees short of Greenwich there. So here is the line of Aries at 1700 GMT on December 9th. So here's that line, that imaginary line. An hour later, it's going to be close to 15. Let's look at where it is an hour later. Aries here. So we're at 1700. Where's the line of Aries at 1800 on the 9th? We're right in here. This is the 9th. Always check your date. 1800, 348, 43.6. How much different is that? Well, the degrees are going up. Oh yes, GHA always goes up unless the Earth starts spinning the other way, and that will cause all sorts of problems. Your toilet will flush the other way perhaps. So 348 degrees, so that's going up 15 degrees. So the degrees are going up 15 degrees, and the minutes are going up 2.5 minutes. So that's not exactly 15 degrees, is it? It's off by 2.5 minutes. It's 2.5 minutes more than 15 degrees. Do we have any D down here? No. No D. That's meridian passage. That's hours and minutes. So what are we going to do? Well, let's look in the back under stars. Oh, there's no stars. Oh, but there is Aries. Oh, good. That's helpful. Let's check the Aries for 59 minutes, 60 seconds, the Aries correction. So Aries is the middle column. Oh, look at that. 15 degrees, 2.5 minutes. That's just what we found. That's how much the line of Aries varies in 60 minutes, 59 minutes, 60 seconds, 1 whole hour. That's what we found the difference was between Aries for 1700 GMT and Aries for 1800 GMT. 15 degrees, 02.5. So, oh, well, let's use the tables to interpolate. We could do it by hand, but it's easier to use the tables. So we're interpolating for 30 minutes and 43 seconds. So we just go, this is pretty familiar, isn't it? I mean, this is not like we haven't done this before. And that's what you're going to find. You start navigating and it's like, wait a second, all these problems are basically the same problem. Whether you're shooting the stars or the moon or the sun, you're doing pretty much the same routine. So 30 minutes and 43 seconds. 30 minutes here. Oops, that's 29. 30 minutes here. And we're in the column of Aries. 43 seconds. 43 seconds. And where was Aries? Middle one. 43 seconds. And we get a correction of 7 degrees, 45 minutes. Is it 7:45? No, 42 minutes, sorry. 7 degrees, 42 minutes. Okay. Minutes. And that's the GHA correction for Aries. And everything gets added because the Earth is spinning the same direction as always. So SHA, oh, we didn't quite get to the end of our explanation about SHA. SHA, sidereal hour angle, is just the distance between the line of Aries and the position, the Greenwich hour, the longitudinal position of the star, in this case Sirius. So here's Aries, here, just short of Greenwich, and that line of Aries, just as the Earth spins, that line of Aries moves at about 15 degrees across the surface of the Earth, just every day, moves all the way around the Earth to almost the same position the next day. And so our SHA just tells us how far Sirius is farther ahead of the line of Aries, from the line of Aries. So Sirius is 258 degrees. I can't quite draw it, but I'm going to pretend that's 258 degrees. Not quite far enough, is it? 258. And this marker isn't very good. Degrees. And 46.9 minutes. I don't need to put that in. Okay, so here is the longitude of Sirius. Right there. So you start at Greenwich, you measure all the way around to the Greenwich hour angle of Aries, 333 degrees, and then you measure, well, in this case, we're going to have to add the 742 as well, 7 degrees 42 minutes, so that'd be 340 degrees, would give you the position of Aries, a little bit more because of the minutes. And then you measure an additional distance, you add on the SHA, that tells you the distance of Sirius, or whichever particular star you're shooting, the distance further to the west, going on around the same direction. We're not going to reverse direction suddenly. Going on the same direction, east to west, the distance of the star, that specific star, from the line of Aries, 258 degrees. The line of Aries keeps moving around the Earth. The distance of the particular star from the line of Aries always stays pretty constant, okay? So all the stars are sort of pegged, as far as their longitude, to their distance from the line of Aries. So, we've got some big numbers here. Let's add this up. Remember, the Aries, this is just the value for 1700 GMT. I gotta switch markers. This is the value for 1700 GMT. 170000. This is the correction for, let's get this out of here. This is the correction for 30 minutes, 43 seconds. Okay? For the line of Aries. Okay? That's the GHA correction for Aries. That longitudinal line, that make-believe line. Aries is just an imaginary line that we've pegged all the stars two as far as their difference in longitude from the line of Aries. Okay, so now we have to add these three things together, and we will have, if we just added these two together, the GHA of Aries and the SHA of Sirius, we would have the position, the longitudinal position, the GHA of Sirius at exactly 1700 hours. But we want it for 1730.43. And you can see this correction looks correct because in an hour, the line of Aries, well, Sirius, but the line of Aries and Sirius together are moving about 15 degrees in an hour. So, because of the spinning of the Earth. But we have 30 minutes, half an hour. So this number should be about half of 15, a little bit more because we have 30, almost 31 minutes, and the line of Aries moves because of the Earth's orbit around the Sun, not because of the spinning of the Earth. The spinning of the Earth gives the movement of 15 degrees per hour. The Earth's orbit around the Sun gives that extra little bit of change to the line of Aries that we're seeing here. So we add all this together, and what do we get? 10, 12. That's 8, 12. That's 12, 13. 132. Uh-oh, wait a second. Now this is see where I messed up? Put my 2 a little too far over. I think I messed that up. 42, and I didn't, here's something that's important. I didn't do that. And I messed up on the math. So a real good example of the types of mistakes that you'll make because you're doing a lot of numbers. They're not complicated, it's not difficult math, it's not a difficult concept, but it is a lot of numbers. So that was my mistake. Can you see that okay? Yeah, I didn't write 42.0 minutes. I was careless and casual. I just wrote 42, and I had the 2 over in the tenths column, so I added straight down, and I got a mistake. So let's do that over again. That's the other point that's important to make. Do your math, and then look at your math. Oh, wait a second. I made a mistake there. Don't do the whole problem and come out with an answer that doesn't make any sense. You're 500 miles from where you thought you were, and then go back and have to check the whole thing. Do each simple step and then check that simple step and see what you did wrong. If you expect to make mistakes, you'll catch those mistakes. If you think, oh, I never make mistakes, you may end up 500 miles away from where you think you should be. Okay, so let's do this again. So we get 0 there. That carries a 1. That's 8. 10 here. And 12, 13. We're running out of space here. Okay, 130 minutes. Okay, so what do we do with 130 minutes? Well, that's 2 degrees, isn't it? 60 plus 60 is 2 degrees. So that would be 120, so we're left over with 10 minutes. 10 minutes, and we have 2 extra degrees. So we carry the 2 into the degrees. Remember, it's a 60-based jump from minutes to degrees, not 100-based. Okay, now let's add our degrees. We have to remember not to get this into, we're sure if our columns are not as well spaced as they could be here. So 3 plus 2, 5, 13, 20 degrees. This is degrees. Carry the 2, 5, 10, 1, 6. So now we have 600 degrees and 10 minutes. In fact, we probably should have just done our 600 down there. 600 degrees and 10 minutes. Well, what are we going to do with a number like that? The Earth's only 360 degrees around. Well, we've gone around once and and a good bit more. So let's resolve that. Minus 360 degrees, and we still have the 10 minutes, and we get 240 degrees, 10 minutes. Let's move that up. Okay, and that's our GHA. That's the longitude of Sirius at the exact minutes, hour, minutes, and seconds on December 9th that we took our sight. 240 degrees, 10 minutes. From Greenwich. Okay, that's the GHA, Greenwich hour angle. So that puts the puts Sirius, well, 240 degrees is a little bit further than I can show on this diagram, but it'd actually be around a little bit. And oh, I'm not sure we can see it from 129. What's the difference there? 240 and 129. No, we wouldn't be able to see it. So Sirius has set by that late in the evening on December 9th. So we wouldn't be able to shoot it. We should have taken it, if we'd taken an earlier time, then Sirius would have been visible still. Okay, so that's how you work out the declination. Remember, that was really simple. And the Greenwich hour angle. That's a little bit more involved because you take the GHA of Aries, add the SHA of the star, and the GHA correction for minutes and seconds, and that gives you your final GHA. Okay, so not too different, and really not, I mean, it's almost easier because you don't have to do anything with the declination. You just grab the declination off the pages. So not to worry about shooting stars. It's fun and relatively easy. And remember, you can shoot 3 or 4 stars within really a 4 or 5 minute period, and you don't have to advance those sights if you're on a slow moving sailboat or sitting still. You can just plot all those sights, and you get a position line, 2 lines crossing. That gives you a position, and then you get a 3rd line that should cross fairly close to those. You get a 4th line that should close to the first 3, and each line you add gives you more and more confidence that your position is actually accurate and you've done all the math right and your sextant sights were really sharp and right on. So fun to shoot stars, shoot a few stars and the planet, shoot the planet and the moon and a couple stars. A lot of different combinations to do there. Okay, so sorry that we came out with a GHA with the star we were shooting not visible. It's over the horizon from our longitude, but if that ever happens, you know that it wasn't the star you thought it was. and so not to worry about it. Okay, now off we go into the sight reduction tables, and that'll be exciting. Last set of tables, and they're not too hard. You know how to interpolate now. What we'll be doing in the sight reduction tables is simple interpolation, just getting in between 2 values, partway between the 2 values. The table will give us a value here and a value farther down, and we want to be in between those, just the right distance in between them, so we interpolate. You're an expert at interpolation now. So the sight reduction tables should be fairly smooth sailing for you. Okay, let's look at Sirius again. Maybe you noticed what I did. I find it not terribly hard, but sometimes a little bit difficult to be talking and thinking ahead and at the same time getting the numbers correct. Does anybody know what I did there with Sirius, which made it so it wasn't visible when we were shooting it? Because I thought it should be visible at the time, evening on December 9th, from a latitude, from a longitude of 129 degrees. Okay, let's look at it. And this is, again, the mistakes you make are going to be really simple mistakes, not complex mistakes. But sometimes it's hard to see them, even though they're right in front of your eyes. Okay, so look at our local time. 8:30:45. We meant 20:30:45. We meant evening. So let's work this problem out for 20:30:45. Okay, and this gives us a good chance to look at time here too. That's one of the reasons I want to go back and look at this again, because we didn't really do any mistakes over here with the math, and our declination is going to stay the same. We don't have to rework that. But now, look what happens here. The watch error of -2 is the same, 43 seconds. 30 comes down, and here we get 29, 30, 43. Oh, what do we do with that? There are only 24 hours in a day. Well, okay, now that bumps us up to the next day. Now we're dealing with December 10th. And what's GMT? It's going to be 29 minus 24. So that's 5, 05, 30, 43. So now we're shooting Sirius in the evening in December. Sirius should be visible in the evening in December at this longitude, 129 degrees west longitude. Okay, so now let's pull out our numbers for 05, 30, 43. Well, our GHA correction for Aries from the back of the minutes and increments pages of the table at the back, increments and corrections pages at the back, that's not going to change because that was just for 30 minutes, 43 seconds. So this GHA correction for Aries is going to stay the same. And remember that did come from the Aries column in the for 30 minutes and 43 seconds. The SHA is not going to change. That's good for all those 3 days. In fact, the SHA doesn't change much throughout the year. A little bit, but not very much. So, but this is what will change dramatically, the GHA of Aries. So let's take that out, and our answer is going to change. So we'll take that out. Okay, now let's look at 1700. Well, this changed, sorry. This changed to 0500 GMT. So 0500 GMT. Oh, 500. And what is the GHA of Aries? But remember, we jumped it to the next day in Greenwich because of the time. So it's 0500, December 10th. So we're in the next day. And this is good to see this, how this works. December 10th, 0500. And is this Aries? There's Aries. Yep, GHA of Aries. So 0500. 154 degrees, 10.7 minutes. Okay, now what do we get when we add all that together? Remember, everything's added with the stars, always adding. 16 here, carry the 1, 8, 9, 5, 9. 99.6 minutes. That resolves to 1 degree, 39.6 minutes. Subtract the 60 degrees, 39.6 minutes. And carry that 1 degree up to the degrees column. And we get 5, 13, 20. Carry the 2, that's 10, 12. Carry the 1, that's 420 degrees. 39.6 minutes. Well, that's again more than once around the Earth. So subtract 360 and we get 60 degrees. 420 minus 360. We get 60 degrees, 39.6 minutes. Don't write that so big, it looks like a zero. There. 60 degrees, 39.6 minutes. Now, we have a longitude. Let's redraw all of this. Where's Aries? Here, the line of Aries is 154 degrees. So now it's not just trying to reach Greenwich, it's already well past Greenwich. So the actual line of Aries is 154 degrees, 10.7 minutes, plus 7 for the 30 minutes and 43 seconds, 7 degrees, 42 minutes. So that's roughly 162, rounding up, 162 degrees. So here's the line of Aries now, moved over here. So this is 162 degrees. And the SHA of Sirius is 258 degrees. So that's actually 162 is probably a little farther around, isn't it? Sorry. 162 is more like over here. That's Aries. 162 degrees from Greenwich. And that's at this time. 05:30:43, and then Sirius is an additional 258 degrees on around the Earth, around behind the Earth, 258 degrees all the way around and back to 60 degrees. GHA of Sirius, 60 degrees. So here's where Sirius is on this line, 60 degrees from Greenwich. 60 degrees, 39.6 minutes. That's where Sirius is. Now we're at 129 degrees, which is, better switch colors here, haven't we? 129 degrees, which is on this line about here, west, 129 degrees west. And so we can label that too, 129 degrees. And now we can see Sirius because Sirius is only 60 degrees away from us. It's in the east. It's to the east of us. It's rising. It's probably about 20 or 30 degrees. Well, maybe just 20 degrees above the horizon. Because remember the declination of Sirius, if we're in the northern hemisphere, our location, the declination of Sirius is in the southern hemisphere, below the equator. So it's still fairly low, but we probably can see it. Okay, so that's good. We worked out the position of Sirius for 8 o'clock in the morning local time and found that, oh, Sirius is behind the backside of the Earth. So we can't see it. It's not anywhere visible unless we could look through the Earth. And so we caught our mistake. We saw our mistake moments later after we finished the problem. And realized that our local time was in 12-hour segments instead of using 24-hour segments. And so when we corrected our local time to evening time, then on 24-hour time, and got our correct GMT for the evening, then Sirius, in December, Sirius is visible in the evening. So it was like, why? So I knew we had a mistake there. We just had to figure out what we'd done wrong. And but all we did was take 8 o'clock in the morning instead of 8 o'clock in the evening. It took 8 o'clock local time instead of 2000 hours local time. So that's actually a pretty good demonstration of the type of mistake that you're going to make. You're not going to make mistakes because this is really difficult stuff. You're going to make mistakes that you look at and you say, well, that was well, I don't want to use I don't want to use the word stupid, but maybe it applies in cases like this where the mistake seems so obvious. Trouble is, the things that are a little bit you have to think about, you're probably not going to make mistakes because you're actually engaging your brain. It's the things that are like seem so obvious that you don't really think about them, where that's where your mistakes will probably come in. Okay, on to the site reduction tables, and you're doing great. It's not too hard. It does seem like we've done almost the same thing. All we're doing is getting the declination, latitude, and Greenwich hour angle, longitude for whatever we shot, and the tables are easy to work with and kind of guide you through it. Oh, one more point though that is helpful. You saw how we were checking our interpolation by going to the end of the minutes and seconds corrections for 59 minutes and 60 seconds, which is basically a whole hour, and it should add up. That correction should get you to the next hour of the GHA value for the next whole hour. Well, another way to check your interpolation, which is sometimes even better, is to go to 30 minutes and see if that puts you halfway between those two values. Because the only problem with going to the whole 59 minutes and 60 seconds is that the V value in the 60 minutes, the V value and the V correction are the same. So you might be forgetting to take the correction instead of the V value. See here, let's take an example. This is 59 minutes. And here's the V value, where's the V or D and the correction. So here's the V or D, 13, and the correction is 12.9, almost the same. I think some of them will be maybe exactly the same. Yeah, here's like a V or D of 5.8. I can't quite see this. V or D of 5.8, and the correction is the same as the V or D value. So in this case, if you interpolated using the V value instead of the V correction, or the D value instead of the D correction, you'd think, oh, I'm doing it right. Whereas you might not be doing it right because you don't ever use the V value or the D value. You always use the D value or the V value, the correction, not the actual value. So when they're the same, that's not such a good check. Whereas if you go to 30 minutes, you should get exactly halfway between the two values for Greenwich hour angle or the two values for declination if you're interpolating correctly. So if you go to the minutes page and seconds, increments and correction pages for 30 minutes, 0 seconds, and take that, interpolate using 30 minutes, exactly 0 seconds, that should place you exactly halfway between in the GHA, if it's GHA, using the correction plus the GHA correction plus the V correction, or if it's for declination, just using the correction for the D value. Okay? Remember, declination D value corrects for the gives you an entry into the table to correct for declination. The V value is just part of the correction for the GHA. So you do the V correction and the GHA correction. Okay. I think that's should be pretty clear. We've gone over it, same material from several different angles. Hopefully it all just has started to gel. If any of this is not clear at this point, this is a good point to go back and watch the section on the Nautical Almanac a second time before you get into the site reduction tables. You don't want to enter the site reduction tables until you're pretty clear about how to get out of the nautical almanac, your declination and your Greenwich hour angle. Okay, here we go, forging onwards, and soon you'll be a master mariner, master navigator, and able to sail anywhere in the world using the stars and planets. Okay, on to the last steps in this process. Remember, the nautical almanac is used simply to get the latitude or declination and longitude or Greenwich hour angle of the star or planet or sun, moon, whatever. Declination, south or north. Greenwich hour angle is just Greenwich hour angle. It's not east or west. It's always west, measured 360 degrees around from the east to the west. So we don't need any west or east in front of the Greenwich hour angle. Okay, so I think we're through with most of this, but let's actually look at where Sirius is based on what we came out with for our declination and our Greenwich hour angle. This diagram's getting a little bit too complex here, so let's get a new globe up here, and we'll make this as big as, in fact, I'm going to put the declination over here. South 16, let me get off the board. Declination, south 16 degrees, 42.4 minutes. Okay, and let's get our globe here. Now really, you have everything you need to navigate now, to find your position. Look at this. So let's make this around Earth here. North Pole, South Pole, and line of Greenwich through Greenwich, England. 0 degrees longitude. That's 0 degrees. Okay, now we're south of the equator, about 16 degrees, and our Greenwich hour angle is 60 degrees. So that places us south about 16 degrees, and around this way less than 90 degrees, about 60 degrees. So let's put ourselves about there. And that's it's gonna be, you can label it, label everything. Deck south 16 degrees, 42.4 minutes, and GHA 60 degrees, 39.6 minutes. And that was Sirius. Yeah, that's exactly when we took, that's the position of Sirius, exactly when we took our sextant sight. Let's take a typical sextant sight and say we got an HS that we corrected for, what do we correct HS for? First for index correction, the sextant error. Second for dip, the height of eye. And third for the altitude correction, the bending of the light as it comes down through the atmosphere. So we corrected our HS to HO, and our HO was 65 degrees. Now based on our geometry and theory in part 1, we know that our distance from the ground point of the celestial body we shot is just 90 minus our sextant reading, or 90 minus our HO. 90 minus HO equals distance. And so we get our distance is equal to 25 degrees. We're 25 degrees away from, and check it, 90 degrees, yes. 90 minus HO. So our distance is 25 degrees. So we're 25 degrees away from this point on the surface of the Earth. That describes a circle around that point. And if you want it in nautical miles, just 25 times 60 nautical miles. Makes it easy. Or, see, if we figured this was 16 degrees, 25 would probably be about here. The diameter of our circle would be 25 degrees. From this point to this point would be 25 degrees. And we have a circle like that around Sirius. And that's our line of position. We are someplace on that circle. Now, if you're sort of thinking about this a little bit more, it'd be nice if that circle is a little rounder. Let's try to do that. Okay. If you're thinking about this, you might have realized that actually, when we took our sextant sight, all you need is one. Check this out. All you need is one sight to get a position. All we had to do was take our sextant sight, the height of Sirius, and the direction to Sirius, right? The exact direction to Sirius. And that would tell us, if we now had our direction to Sirius and our distance from Sirius, we would no longer be describing a circle around Sirius. We'd say Sirius was at exactly this direction and at exactly this distance, and this is our position right there. Well, what's wrong with that idea? Why don't we do that? Technically, yes, that is true. That would give you an exact position with a single fix, a single celestial sight. The problem is that it's very, very hard to get your direction accurately. Now, think in terms of sailing 10 miles on a compass course. If you're off by 1 degree, it's not that big a difference. You're going to still be able to see whatever you're heading for and, you know, distinguish, oh, there's the marina, there's the buoy, I was off a little bit. But if you're going 1,000 miles or 3,000 miles on a compass course and not correcting that whole time, you could end up 50 or 60 or 100 miles away from your destination, off course, if your compass reading was off by, you know, 1 degree or even half a degree or 2/3 of a degree. Over thousands of miles, a direction, and this ground point is, even in this case, it's not. It's where the sextant reading was fairly high. The body was fairly high. That means you're closer to it, to the ground point. Even in this case, it's over 1,000 miles probably away. And so to get a compass bearing or a direction accurately enough to make this actually work and not be 50 or 60 miles off is almost impossible. Unless you're in an observatory with a very, very accurate directional device attached to the telescope, a large telescope. And so you could get the exact direction very, very, very precisely. But if you're in an observatory, you know where you are already, so the whole thing would be pointless. So we're back to, well, that doesn't work. We're back to having a circle, because the sextant reading, which describes the distance from the ground point, is extremely accurate. Very, very accurate. You'll be amazed if you haven't shot sights before, you'll be amazed how to keep up with the star or the sun going up or down, you just have to keep cranking the sextant. It doesn't stay still for a second. And it's very, very precise getting that distance. So what do we do then? We just take a second sight and get a second position for a second body. Well, let's say it's a body up here. And then we get our second sextant reading. And we know we're 90 minus HO from this body, our new reading. And that describes a second circle, line of position. This is LOP for our second star. And since we're on this orange line of position and we're on this green line of position, we have to be where the two lines cross. Either here or here. And if you can't guess which one if you can't guess which location you're at, your dead reckoning really needs to be honed, and you need to work on your dead reckoning a little bit more. Okay, so you should be able to guess where you are. Okay, so why do we have to have the site reduction tables? We've already got we know how to do this. We've got a position either here or here. Well, this is actually all fine and good if you have a boat that's big enough for a huge globe and your pencil line isn't going to be 60 miles thick, just a skinny pencil line representing 60 miles of variation. So this could work on a really big globe, but we don't have space in our boats for that. So now's where we get into the trick, where we have to turn the whole problem into something that fits on a teensy little chart like this. Or maybe you have a bigger ocean chart. You know, it might be a chart like this. But it's still not big enough to have a star's ground point that is thousands of miles away. Even if it's really high, it could still be, several hundred miles away and off of your chart. And you're certainly not going to have a chart that has the ground points for all the things you want to shoot on it. You'd be shooting at, like 89 degrees all the time. Shooting things are almost straight up. And it's very hard to shoot really high objects. It's just a lot more difficult because you don't know where. Is your horizon over here or is your horizon over here? It's really hard to know exactly what's straight down if the thing is way, way up high. Okay, so now's the trick. How are we going to make this problem whoosh, shrink onto this teensy little chart? Well, let's put our chart. Let's now take our chart. And this is review. This is from part 1. I'm not going to go over it as thoroughly as part 1. If you don't remember this part from part 1, and this is too fast for you, listen to part 1 again. So here's our chart. And if we can, here's our dead reckoning position, DR, on the chart. And we got a certain sextant reading on a site, on a star. If we can enter our latitude and longitude, our position, lat and long, and we can tell the table the latitude and longitude or declination and GHA of the star. If we can enter our latitude and longitude and the declination, latitude and longitude of the star, those are two fixed points on the surface of the Earth. The table should be able to tell us the direction from our position towards that star, and it should be able to tell us the distance. That's just math. It's over the curve of the Earth, so it's spherical math, spherical trigonometry. Those formulas are complex, so you don't want to have to work with those formulas yourself. Let's let the tables do it. The site reduction tables do that. Now, if the site reduction table tells us that our sextant reading and the sextant reading from the book are the same, then we are at this point. Okay, but if the sextant reading and the sextant reading we got and the sextant reading that the book tells us we should have gotten are different, then something's wrong. We're not at this point anymore. We've got to be, this is our dead reckoning position, right? That's not an accurate position. That's not necessarily where we actually are. Our dead reckoning might have been 3 days, 3 days of just recording course and speed. If our sextant reading that we actually got and the sextant reading computed for this latitude and longitude and the position of the star's latitude and longitude, if those two sextant readings, the actual sextant reading HO and the height computed HC are the same, that means we might be here. because that's what we would have gotten given those 2 points. Okay, doesn't necessarily mean we're right there though. It means that we're on that grand circle around the ground point of the star that measures a distance from the star 90 minus HO. If HO, the sextant site we got, corrected section, the sextant site that we observed and then shot and then corrected, HO, is the same as the sextant site that we would have gotten if we'd been here and shot this star, just measured on 2 points. How far is it between the 2 points? 90 minus that distance gives you a height computed, the sextant reading we would have gotten if we were here. And our HO and our H computed are the same. We have to be on someplace on this arc that goes through this point. Okay, that's kind of a quick. I think it's quite a bit more thorough in the part 1 explanation, but this is just quick review. So if we're on this arc, what's that arc like? Well, this direction is pointing right towards the star. This direction we get out of the site reduction tables. They figure it out because they know this point and they know this point. And they just tell us, well, if you're here on the Earth and there's this point here, the direction from your position to that star is that direction. They give it to you in terms of degrees from, like that. How many degrees? What direction is that? Okay, so at this point, since this is a radius pointing right towards the star, this line of position is going to be perpendicular to that radius. And since we're just taking a very short part of that big circle, we're going to just approximate that short part of the circle as a straight line. And that's pretty accurate, especially if our dead reckoning is fairly accurate, we're in this area. If we're way down here, you can see it starts to be less accurate. Although this circle is still much, much bigger than I've drawn it. So even way down here on our chart, we're not too far off. Might be, half a mile off or something. By approximating a straight line to represent the curved circle around the ground point, because that's a huge circle. Okay, so if our sextant reading that we actually got is different from the height computed, the sextant reading that the table tells us we should have gotten from here, looking from this position to this position, just based on the distance between the two, from this point to this point, if they're different, we're not on this line of position. We're either farther away from the star or closer to the star. We're either on a line of position that's going to be farther from the star or a line of position that's going to be closer to the star. Now you can sort of figure this out in your head. As your sextant reading gets higher and higher, you're getting closer to the star. As your sextant reading gets lower, you're getting farther from the star. So if the computed sextant reading is greater than our actual sextant reading, the computed was for this point here. If the computed is greater than our sextant reading is less, our actual HO is less than the computed sextant reading, then we've got to be farther away, because this is where we actually had to be to take that lower site. Farther away means you're farther away from the planet. As you get higher and higher sextant readings, the planet gets higher and higher. You're getting closer and closer to the ground point underneath the planet. So that's a little bit of thinking to have to figure that out. We're talking about HO, height observed, that's off your sextant but corrected, and HC. And that's what the table computes, just based on the distance from our dead reckoning position to the ground point of the star. There's a little cheat that tells you can always figure it out. Well, if the height observed is lower is a smaller number, the sextant reading I got was smaller than the height computed, that means where we actually are, we're farther away from the ground point. And you can think that out, but there's a little cheat thing that is simple to remember. Coast Guard Academy, CGA. If the computed is greater, computed greater away. Computed greater away. If the computed sextant site out of the site reduction tables is greater or larger, then you move away from the star, the ground point of the star. You move further away. If the computed is less, then you move towards the star. So, Coast Guard Academy, CGA, that's a really easy way, so you don't have to rethink this every time. Oh, do I move towards the star or away from the star? Based on my height observed being different from the height computed. Okay, now let's look at what the table is doing. You can get a sense of it here, but I want to show you on a globe as well. Okay, only the last part of this is then you do your second site on second planet or whatever, and you get a second line of position, and where the two cross is where you'd be. That other planet or star would be sort of over here or something. Okay, but let's look at this again from a different perspective, seeing it on the globe. Okay, and I think now we're through with this here, our Sirius sighting, and we can take this out. Let's leave those two up there and that out. Okay, and here's our globe. Okay, and again, let's make it look round. A little bit cleaner here. North Pole, South Pole. Okay, and let's just orient ourselves. Here's the line of Greenwich over here. 0 degrees longitude. And here's the equator, of course, 0 degrees latitude. Right here. Okay, now, if we're here, that's our dead reckoning position. And the star, let's put the star or planet that we shot, or maybe let's make it the sun in the morning. The sun shots are so easy. You're going to end up doing more sun shots than anything else because they're so easy. The sun in the morning would be to the east of us, right? By a certain amount. And if we're this far north, that looks like about 50 degrees north. The sun's always going to be somewhat to the south of us there. Okay? So, this is GP sun, ground point sun. Okay? There. Now, what is the table doing? What is the site reduction table doing? We're stepping back just a little bit to see what we were talking about in the last diagram where we had everything onto a smaller chart. What is the site reduction table actually doing? What's its math? Well, it knows this position here. It knows its latitude, this distance here, latitude, and it knows distance here, longitude. Okay, so we can give the tables our dead reckoning latitude and our dead reckoning longitude. That's our approximate, where we assume we are. And we can give the tables, based on what we found out from the Nautical Almanac, we can give the tables the exact position of the sun from the Nautical Almanac for the hours, minutes, and exact seconds that we took our sextant sight in terms of basically latitude, which we call declination, and longitude, which we call Greenwich hour angle. Remember, GHA and longitude are exactly the same in the Western Hemisphere, measured from east to west. Okay, so we can tell the table, this point, latitude and longitude, this point, latitude and longitude. And we're going to ask the table to tell us in return, these are the site reduction tables, to tell us in return the distance between those two. So the table is going to say, well, oh, I can figure that out. It's just a triangle. Here, it's a right triangle. It is a spherical triangle. It's on the surface of the sphere. These lines are curved over the surface of the sphere. That makes it a more complicated equation than just a flat piece of paper. You know, drawing a right triangle. Anybody can solve a right triangle. It's just a squared plus b squared equals c squared. Simple enough. In fact, it might be kind of interesting. A right triangle right down near the equator, small enough, the spherical triangle should solve in a pretty similar way to a flat triangle if it's a very small triangle. I mean, it's not going to be exactly the same. You won't get the same answer, but you should get answers that aren't too far different if it's right at the equator. Okay, but here we are solving this. Now, it's going to solve the distance here, right? Because it's doing the math. You know, it knows this. It can figure out this distance, and then it just solves for this distance. But since we want to compare sextant readings, the table is going to take one step farther. And instead of telling us the distance between these 2 points, it's going to go 90 minus the distance equals height computed. So it does that step for us. If it told us the distance, we'd have to do 90 minus the distance to get the sextant reading we should have gotten if we were here and we shot that body. But this table will do it for us. It's not going to tell us the distance. It's going to tell us the height computed, the sextant reading we would have gotten. Okay, now, so that seems pretty simple, right? We just enter our latitude and longitude for our dead reckoning position. We enter the latitude and longitude of the star, the ground point of the star that we shot, and the table tells us the sextant reading we should have gotten if we were here, and the table tells us, the table can work out all these angles as well, because it knows the distance between these 2 points, that side of the triangle, and it knows this side of the triangle, and so it can figure out what these angles are, and x and y, let's just call them x and y. And since that's not an angle that we're used to really talking about, the table's going to do one more thing. It's going to tell us what the angle is, the direction from north. So it does a little of our footwork for us, right? Instead of asking us to do, take this angle and do direction from north, it's going to give us a z, which is the direction that we'd be familiar with from our compass. And in fact, in this case, the direction looks like it's about 90 plus 45, so about 135 degrees pointing towards the sun when we took the sun in the morning. That's about where the sun would be, 135 degrees if you look at your compass. Okay, so it's going to give us a z angle measured from north and a distance between our position, our assumed position or dead reckoning position, and the point where the sun is, directly overhead, from a person standing on the earth looking straight up. If he's standing at the GP of the sun, the ground point of the sun's straight up overhead. And that's what we got out of the Nautical Almanac. It's going to tell us the sextant reading we should have gotten if we were here and shot this body, which is there. And then we're going to be able to say, well, that represents a circle around that body, and we can just say that circle is, we're taking such a small part of that circle on our little chart that that's like a straight line which is perpendicular to the direction to the sun. Okay, so now you've seen the same concept several times, several different ways. Hopefully one of the explanations makes sense to you. It's like, oh wait, now I got it. Okay, that way made sense. So it's all the same, you've seen the same thing 3 times at least now. Okay, now the problem. Oh, you knew there was a hitch. It couldn't be that simple. Well, it's not. Yeah. Yeah, I'm making it too simple. I'm making it a little simpler than it is, but not a whole lot. The problem is, let's try to clean this up a little bit here. Because remember, we're trying to stay on our little teensy chart there. And we don't have the luxury of being able to draw huge circles thousands of miles wide on our chart. So we're trying to stick on that little chart. The problem is, how can you make a table that you can enter with 4 different factors? Latitude and longitude and declination and Greenwich hour angle. What kind of table would that be? A table where you enter with 2 variables is really simple. It's just one sheet of paper and you enter one variable across the top and one variable down, and then you come down and across, and oh, there's the answer. A table where you enter with 3 things is, well, that's not going to fit on one piece of paper. You have to have one value be each separate page, and then the other 2 values can be one across the top and one down. So you've got a book now. What happens if you're trying to create a table with 4 values? Wow, you've got multiple books. You got a library basically. You got a lot of books, and it's going to be hard. It's going to be a long process to enter with 4 different variables. So the problem is, does that mean it doesn't just work? It just doesn't work? Well, wait. There is a bit of a. Again, this is the trick. This whole bit is a trick. We know how to navigate, but now we're doing a trick just to get it on this little chart. Okay, so let's look at this. Clean up our diagram a little bit. Maybe you can think about the trick while I'm erasing this. What do you think? How can we solve that problem of not being able to enter a table with 4 different things? We have 4 things we want to enter with: latitude, longitude, declination, and Greenwich hour angle, to define this point and this point. Okay, well, let's say, the table really just wants to know this distance, right? Between our longitude and the longitude of the sun. That's what the triangle is, okay? This distance. It doesn't really need to know that and that. It just needs to know the distance between, the difference between the GHA and our longitude. Okay, well, we just got rid of, we combined 2 variables into a single variable. So we're down to 3. That's pretty good. Okay, well, let's call this something. Let's call this, it's an hour angle, right? Because, it's, there are all these things that change because the Earth spins 15 degrees each hour are called hour angles. So let's call this our local hour angle, LHA. Local hour angle. Okay, the difference in between the 2 longitudes, local hour angle. Oh wow, look at this. That worked pretty well. Why don't we combine our latitude and the latitude of the sun and give the table this distance? Is that a good idea? Then we've got the whole thing, a two entry table. It's all on one sheet of paper. Why do we need the sight reduction book? Those are expensive and heavy. And they're, several volumes to get the whole, all the way 0 to 90 degrees latitude. Well, wait a second. What's the problem with that? Combining the latitude. If we combine the latitudes, now the table doesn't know if we're doing a problem way up here, or a problem here in the middle, or a problem down here. And those are really different problems, aren't they? Because up here, the triangle is super different. Let's go all the way up. Always go to an extreme if you want to understand, oh, how does this concept work? Take it to the extreme. Take it all the way to the North Pole. Well, now the difference in latitude up here is like that, but the difference in longitude, the distance in longitude, that's the same. That's this distance, it's the same difference in longitude, but this distance is teensy compared to down here near the equator, where 1 degree of longitude down near the equator is about 15 degrees. I mean, 1 degree is about 60 miles. Whereas up here, as you get close to the North Pole, right up at the North Pole, 1 degree of longitude is nothing, you know, the length of your foot. So if we move the problem up or down, it changes the problem. So we have to tell the table accurate latitude of our dead reckoning position and accurate latitude of the sun or star, or declination, called declination. Okay, so we cannot combine latitudes because it totally distorts the problem. Doesn't make any sense anymore. Okay, this is our DR position up here, remember? And this is the GP down here. GP, sun. Okay, so we can't combine latitudes. Anything else we can do? Oh, we have 3 things. Now that's okay. We can enter a table with 3 things, 3 variables. That's not a problem. So is that where we're going with this? Oh, but wait, we do have another problem. Here's another problem. Oh, darn it. I thought we had it, right? Okay. Yeah, Will said it was simple. This is celestial navigation made easy. And he keeps coming up with all these new problems. Okay, well, the new problem is that our latitude, we're now entering with 3 things. We're entering with, let me get this out of the way here. We're entering the table with our latitude and our longitude. No, not our longitude. Our latitude and the declination of the sun and the difference in longitudes, local hour angle, LHA. Those 3 things. Well, all 3 of those things are very precise. We're going to have to interpolate between 2 entries of latitude and 2 entries for the declination in between 2 values, and 2 values for the LHA. How can you do that? Interpolate 3 different things. I can't quite wrap my head around it even. So again, are we at a dead end or a stopping point? Well, wait a minute. Look at this. Our dead reckoning position is just kind of a guess. We've been sailing for 3 days across open ocean. You know, and when I woke up, it was like, oh my gosh, our course has changed a lot. From when I last recorded our course. Maybe it changed about 3 hours ago. Maybe it changed like 10 minutes ago. I don't know. My dead reckoning position is pretty vague by this point because it's been cloudy. I haven't had any celestial sights for 3 days. And so this isn't really a very fixed point. We can mess around with this point, the dead reckoning position. We really can't mess around with our ground point of the sun or stars. That's where they were. That's where the heavens, that's beyond our power to mess around with that. That's where it was when we took our sight. We better not change the declination or Greenwich hour angle at all. Not a bit. But we can mess around all we want with our dead reckoning position. We don't have to, we're guessing we're there anyway. So let's not call it a dead reckoning position anymore. Let's call it an assumed position. Assumed position, AP. And now, look what we can do. We can choose an assumed position, so our LHA is even, equals even numbers, even degrees. We can choose an assumed position, so our latitude is even degrees. And now, all we have to do interpolate for is the declination. Now, in choosing a position in AP so our LHA becomes even, we have to look at the GHA of the sun, and if the GHA of the sun, just hypothetically, is Greenwich hour angle, that looks like what we're guessing about 60 degrees. 60 degrees, 14.2 minutes. Then our assumed longitude better be AP longitude. Better be, that looks let's say our dead reckoning longitude was 134 degrees. DR longitude 134 degrees. West 134 degrees. 49.5 minutes. That's our DR longitude. Well, remember, we're not really here. If we knew we were there, we wouldn't have to do celestial navigation. That's kind of just a guess. So let's just change that around to make it so it works with their GHA. So parent longitude 1, and again we want to line things up. Parent longitude 134 degrees. Well, should we go, what's closer? 49.5 to 14.2. That's 35 degrees. So it's going to be closer if we get an AP longitude of 135 degrees 14.2 minutes. Okay, that's closer to our dead reckoning longitude than if we went to 134 14.2. Either way would work. Doesn't really matter. Either way will work. It's just if we stay a little bit closer to our dead reckoning longitude, then we have a slightly higher degree of accuracy. Okay, and now our LHA, local hour angle, is going to be, what's the difference between these two? Well, there's no difference there, so the difference between 60 and 135 is 40 plus 35, 75 degrees. Even! All right, solved that last problem. Now, we don't have to interpolate with LHA. We don't have to interpolate with latitude because our latitude was about 60. Let's say our dead reckoning latitude, DR lat, was 60 degrees, 18.6 minutes. Well, get rid of the 18.6. Say 60 degrees. So that was easy, 60 degrees. So now we don't have to interpolate here. Can we round off our declination? No, no, no. The declination was where the sun was at that time. We're going to have to interpolate for the declination. We cannot fudge that. Okay? So now we're ready to look at the tables. The tables are just going to solve this triangle. They tell us that basically they're going to solve the distance between our assumed position and the ground point of the sun or planet that we shot. But they're going to take that distance, and which I'll call D, and turn it into a sextant reading, which is just 90 minus the distance. And they're going to call that sextant reading that we would have gotten if we'd been at this assumed position. They're going to call that height. They're computing it, so it's going to be called height computed. That makes sense. That's not too, it's a lot simpler than having to explain height coming out of the tables because they computed it based on triangle. Just height computed. Okay? So height computed, HC. And then we're going to compare HC, height computed, with our actual sextant reading, which we've corrected for the, for the inaccuracies in it, to HO. That's just corrected for dip, index error, and altitude correction, the bending of the light. So we're going to compare HO and HC and get a difference. And then that will tell us that we're either closer to the star by the amount of the difference, either closer to the star on a circle line of position closer than our AP, or farther from the star on a line of position that's farther away from the star. And those lines of position are going to be perpendicular to the direction to the star. And the table is going to tell us the direction to the star, the azimuth angle, the Z. That's measured from north down to the star. From north, just like your compass measures angles. That's the Z, azimuth angle. Okay, and remember, so you don't have to, don't have to strain your brain. We don't want anybody to strain their brain. Just remember CGA, Coast Guard Academy, easy enough to remember. Coast Guard Academy, computed greater away, CGA, computed greater away. If the computed is greater than the observed, then you're going to be on this green line, farther away from the star's ground point. If the computed is less than the observed, then you're going to be closer to the star. And again, you can think that out. Sextant readings get higher and higher the closer you get to the star. Okay. Now again, you've seen this concept a few times now. It's a little bit complex. It's a trick. It's just a trick to get everything to fit onto this little chart here. Okay, but it's clever trick. Clever. And the table does all the work for us. The table does all the work. The only thing left is interpolating for the declination. That's really not that hard. You can just do it with a calculator or by, long division or whatever. But the table also has an interpolation table inside the front cover and inside the back cover. So we're going to be looking at the tables pretty soon here. So here's the interpolation tables right inside the cover, and they continue. They're not repeated, but they continue on the back cover here, inside the back cover. And then the daily pages here, which look, oh my gosh, Will's really leading us on here. What's that mean? Oh well, there's LHA, there's declination. LHA right up here. Declination, down here. Oh, latitude across the top. Oh, what's the same name as declination? Oh, I have to think about that one for a minute, won't we? Huh? The funny thing is, when you first run into this, it does seem confusing, but it's not at all. It's so simple. It's such simple stuff. Once you grasp it, once you get it in your head, it's like, oh, why did I think that was confusing to start with? Well, because there are a lot of parts of it, and you have to put all those parts together. It's like building a puzzle. When you have all the pieces kind of spread out on the table, you have no idea what the picture looks like. Well, as you get more and more of the pieces fitting together, then you can see what the picture is. Oh, it's going to be a horse, or it's going to be a house, or whatever, a horse in front of a house, and once it's all put together, it's like, oh, that's pretty obvious. So anyway, we're putting the pieces together one by one. Now, a few more problems here. We want to look at the interpolation. We also are taking a very specific situation. I'm going to erase this and clean it up and then redraw it for you. Basically the same, but just a little bit cleaner. So here's our position, our AP. Now we can call it assumed position instead of dead reckoning position. Dead reckoning position is, are as precise as we could get. The assumed position has been doctored up to give us an even latitude. We just get rid of the minutes, either round up or round down, whichever is closest to whole number of degrees for latitude. If you go the wrong way, it's not going to make that big a difference. The problem still works out fine. And then we're going to doctor up our assumed position longitude, so when combined with the Greenwich hour angle, we get rid of all the minutes. We come out with whole degrees for an LHA that's even. So that's what our AP is. And here's the ground point of the sun, GP sun. Okay, and the table was solving this spherical triangle. It's a right spherical triangle. This is a right angle right here, right? And this distance was LHA. Label it bigger. LHA. And then it knows the declination, the latitude of the sun, it knows our latitude, and it's going to give us the distance. Okay, well, now the tables are pretty smart. The table all of a sudden realizes, oh, we've got a pretty similar situation over here. Same LHA, same difference between longitudes. If the sun was a GP sun here, in fact, that looks like an afternoon sight, doesn't it? Shooting to the west. If the GP sun was there, this distance would be the same, and if we just take, here's our zenith angle here that the table gives us, well, that's going to be the same as this angle here, the zenith angle there. So why don't we just take these two problems at the same time? And in fact, once we've done that, we can take this whole problem and slide it around the globe. We can't slide it up or down, but we can slide it around the globe anywhere. And it works the same. It's the same answers, same distance, same d, and the same zenith angle. We just have to know whether we measured from north around to the east and down to the south, or if we measured from north around to the west and down to the south. But this distance here is the same as this distance here. We don't usually talk about that direction as being, 135 degrees. We usually talk about it being all the way around past 180 and up to that point. So more like, let's see, 135, that leaves 45 to get to 180. So that would be 180 plus 45, 225. We'd usually say for this direction here, that direction there from AP to ground point, we'd usually call that 140, 200, what did we get? 225 degrees measured from north around to the east. The table's just going to measure it as this angle though, because it's the same as this angle, and it wants to solve these two at once. We've just cut the tables, half the pages out of the table by solving these two at once. Oh, and look at this. Wow, the tables are so good. We've got two triangles down here that work the same. Here's the AP. Here's GP Sun. Different, whole different. We're down in the southern hemisphere now. And here's another possible GP of the Sun there. And it can solve these triangles at the same time. The distance between the AP and the GP, distance between the AP and the GP there. These are both LHA. Difference in local hour angle. Exactly the same problem, just now in the southern hemisphere. And now it's measuring this angle. If we're taking this problem and saying, well, it also looks like the same as this problem also looks the same as this problem also looks the same as this problem, the Z is now measuring this angle from the south pole up. And in this problem, the Z is measuring this angle from the south pole up. Okay? So the table can solve this one problem, and then it doesn't have to solve this one separately, or this one separately, or this one separately. And all four of these triangles can be skidded all the way around. As long as the latitude stays the same, the problem stays the same. Doesn't matter where they're located as far as their longitude. So the table is doing four things at once. We just have to know which one of these four it's doing. Did we shoot the sun? Was it sun in the morning? Is it this problem? Or was it the sun in the afternoon? We should know that. I mean, we're pretty pretty clever. Whether we shot the sun in the morning or in the afternoon, we're doing great. We're really almost through with the tables. From the site reduction tables, we are trying to get two things. Just two things. We're trying to get the height that the sun, let's talk about the sun, the height that the sun would have been if we had been at our assumed position, or that same distance away from the sun when we shot the sun. So the table is just going to do the spherical trigonometry and figure out, based on our latitude and longitude and the Greenwich hour angle and declination, that's the our declination and Greenwich hour angle, that's the latitude and longitude of the sun or planet. It's going to do the spherical trigonometry, figure out the distance between those 2 points. We're giving it 2 points on the surface of the Earth. It'll figure out the distance between those 2 points and the direction from our assumed position to the location of the ground point of the sun or star. So the table's doing a fairly simple, I mean it's somewhat complicated math that is doing spherical trigonometry, but it's doing, the site reduction table is doing a fairly simple thing for us. We're giving it the information about 2 points on the surface of the Earth, and the table is giving us the distance between those 2 points, which it's then going to subtract from 90 degrees, 90 minus the distance, and it'll give us the answer to that problem, which is the same number that we would have gotten if we had shot a sextant sighting of the sun if we had been at our assumed position, and it's going to give us the exact direction from our assumed position towards the sun. And then we're going to use those two things on a small chart, doesn't have to be a huge chart, a small chart, to do our final plotting. So we're looking for the sextant reading we would have gotten if we'd been at our assumed position, and the direction to the sun if we'd been at our assumed position. Shouldn't be too complicated, shouldn't be too difficult. And you know, just a side note, this is one of the very valuable aspects of the site reduction tables when you're cruising long distances. Just as a side note, look what we've got out of this out of these tables. We can enter any two positions, any two locations on the surface of the Earth, and get the distance between those two locations, and we can get the direction, the shortest direction, the great circle route direction from point A to point B. So when you're planning a cruise across an ocean, you don't want to just go around a latitude, you're going a lot of extra miles. Currents and winds, of course, affect your course direction and your course deliberations as well. But if you want to find your great circle route, like cruising from the east coast of the U.S. across to Gibraltar, if you want to find your great circle route, then you enter the latitude and longitude that you're beginning at, and the latitude and longitude that your destination point is, and the value for the direction between those 2 points out of the site reduction tables is going to be your perfect course as far as the great circle course route, and the distance is going to be just 90 minus the HC, the height computed, the sextant reading that they give you in degrees, and then to get that in nautical miles, just multiply times 60. So great circle routes come right out of the table very, very easily. And as you progress on a great circle route, your compass course continually changes because you're going over an arc of the Earth. You're not heading on a constant compass course. You stay on the compass course you start at, you're not going to ever end up at the point you're trying to get to. So each day you recompute your ideal course to stay on that great circle route by entering your new dead reckoning position, and the destination point, of course, stays the same. So each day you're recomputing your great circle course, and then remember that's going to be in true degrees, so you need to turn that into magnetic degrees, so because of magnetic variation. Okay, so just a side note about how useful the tables can be for getting your great circle course. Okay, now let's go back to our diagram here after that little digression, and let's deal with the Z first. I can read you the definition of the Z value. Azimuth angle, this out of the glossary in the table here. Azimuth angle, Z, the arc of the horizon or the angle at the zenith between the north part or south part of the celestial meridian according to the elevated pole and a vertical circle through the body or point measured from 0 at the north or south reference, eastward or westward through 180 degrees according to whether the body is east or west of the local meridian. It is prefixed N or S to agree with the latitude and suffixed east or west to agree with the meridian angle. Okay, so that should make it totally clear, I suppose. This is what makes navigation seem so complicated. A definition like that, where just guessing you might have had a better idea what Z was before you read that than after reading it. But now let's look at it, because Z is one of the values. Now let's look at the table and see what this Z is. Z is one of the values that the table is going to give us. We're going to enter this table with, this is important, latitude contrary name to declination. That means either you're in the north, your assumed position is in the northern hemisphere, north latitude, and this body you shot is in the south, has a south declination, is in the south latitudes, or it means the opposite, that you're in the south latitudes and the body is in the north latitudes. So that's not what we drew up on our board, is it? We drew our declination north and our assumed position north, both of them north of the equator. So we better look again. Oh, here on the facing page, latitude, same name as declination. Well, that's a pretty easy place to make a mistake, isn't it? You get on the wrong page there. They're facing pages. You get on the wrong page there, and your numbers won't make any sense at all. So just make a note of that. Latitude, same name as declination. That means both the latitude of the AP, assumed position, your dead reckoning position basically, but close to your dead reckoning position, your assumed position, and the declination, the position of the star, are both north or both south. Okay, now let's look at what the table is going to tell us. Here's the local hour angle. Remember, the local hour angle is just the difference in longitude between your position and the your longitude and the Greenwich hour angle longitude of the star or planet. So just the differences in longitude. Now, why do you have 52 and 308? Well, those added together are 360, right? So it's you can use either one. Okay, now going down this side here is the declination. And you can see that's in whole degrees. Our declination is never going to be in whole degrees because that's actually the latitude of the ground point of the sun or star. And that's going to be degrees, minutes, and seconds. So we're going to have to interpolate. Let's, for instance, between 4 degrees and 5 degrees. We know about interpolation. That's not too hard. Okay, and what are the values that the table is going to give us? HC. Oh, that's height computed. That's the sextant reading we would have gotten if we had been at our assumed position or an equal distance from the star or planet on that circular line of position around the sun or planet. Okay, so that's HC. Here's a D value. Oh, we've seen D values before. Let's look at this D value. Okay, see if these numbers are easy to work with. Not especially easy to work with, but we can probably do it. What's the difference between this entry, a declination of 4 degrees, and this entry, a declination of 5 degrees? Well, let's take this number here 2855.3 and add 46.1 minutes. So we're going to be bumped up to 29, right? Because we're going to be over 60 minutes. So, oh, that's right, 29. How many minutes are we going to be over? So 55.3 plus 46.1. That's 90 plus 11. So it's 101.4. 101.4 minus 60 is 41.4. Oh, look at that. So this D value is simply the difference between a declination of 4 degrees and a declination of 5 degrees. The difference in the height computed that we would get if the declination switched from 4 degrees to 5 degrees. Okay, so the D value is just to help us interpolate between these two values here. Okay, so that explains the D value. Now let's go on to the Z value. Well, we just read what the Z value was in the glossary, so now you understand that, I'm sure. Crystal clear. Well, we'll go over it again just in case that wasn't quite as clear as it could be. Okay, the Z value. What is that Z value? The Z value, as we started to look at here in this diagram, is measured, since the table is doing 4 problems, the table says, well, this problem and this problem are basically the same. And this problem and this problem are basically the same. I'm going to get the same distance here as I get here if the LHAs are the same and the latitude of the AP is here and the latitude of the GP, or declination of the GP, is here. Same over here, same declinations here, same latitudes here. These are the same problems. I'll get the same D, same distance, and then I'll do 90 minus the distance to get the HC, height computed. Same D here, and oh, these are two of the same problems too. Same distance here, LHA, difference in longitude, local hour angle. Same latitude, just to south now, and for the GP of the sun, or declination really, and same latitude for our assumed position as up here. Distance from the equator is the same, just southerly now, and same for this problem. So these distances, that's going to be D, and this distance is going to be D. So just the same as in the upper, these two triangles. And remember, those triangles can slide around the Earth anywhere. Doesn't matter. The distance is still going to be the same. If that's set over England or set over Hawaii, the distance doesn't change. Okay? If we move it down to the South Pole or up to the North Pole, if we slide it up or down, all of it, the distance definitely changes. And the angles change. Everything changes. Totally different problems. So we cannot slide it. We cannot change the latitudes, but we can slide it around the Earth. Okay, Z is always going to be the answer to this problem. And they're going to compute this angle, but then they're going to give you this angle from north, because that's what we're used to doing. We're used to a compass that measures from north through clockwise around, from north to east to south to west, back to north, 360 degrees. They know we're used to that. So they're going to always solve as though it's this problem here and give us a Z that is measured from north around to this angle here. Okay, if it's this problem over here, the Z is going to be measured backwards here, because they really just solved this problem. And if it's these problems here, Z is going to be measured from south up to this line, and on this side from south up to this line, measuring, backwards and upside down. But as long as you know that this is the one that they're actually solving, Then you just do your little diagram, just like this. Do a diagram on a piece of paper and figure out, oh, if I was in this situation here, where the Greenwich hour angle of the sun, or so I guess we shot the sun here, the Greenwich hour of the sun was greater than my longitude, that means it was to the west of me. Oh yes, I shot it in the afternoon, it was to the west of me. Then you know the table is giving you this z here. That the z they give you means this angle. And so you just take 360 degrees minus z, and that'll give you the compass direction that we are used to talking about, which would be this angle here, from north around clockwise to that. So in this case, this triangle here, this 360 minus z gives you a course, a z, an azimuth direction, a direction from us, the assumed position, to the star that is in the standard, standard frame of reference for directions, based on measuring from north through the degrees east, south to west. So if the z they gave us in this case was 120 degrees, if z equaled 120 degrees, in this problem here, with the sun to the east, a morning sunshot, the direction to the sun would be 120 degrees. If it was an afternoon shot, in this situation here, where the sun was to the west of us, then our actual direction would be 360 minus 120, or 240. This angle here, 240 degrees. If we're down here, in this case here, this triangle, the actual direction is just from north through to where this is our assumed position, and the sun was north of us, lower latitude, and to the east, morning sight again. In this case, the direction to the sun would just be 180 minus 120, so we get 60 degrees would be our direction. In this case, the last one, where we're measuring 120 from south up to our position, up to the line, the direction towards the sun, we just have to add 180 to the z, and now the direction for this last, most complicated of all these z calculations, the direction would be 180 plus 180 to south plus 120, so it would be 300 degrees. Now, this part does seem complicated, but until you do it, when you do it, you know what direction we're looking at. In fact, if you want to, when you take your sight, record a rough compass direction, that's not a bad idea. But really all you have to do is compare your longitude and your longitude of your assumed position, your dead reckoning position, basically. Your longitude, compare it with the Greenwich hour angle or the longitude of the sun, and see whether the sun is to the east of you or to the west of you, or the star is to the east of you or to the west of you. And hopefully your cruising is starting in the northern hemisphere, because it's just a little bit simpler, because you have to think upside down in the southern hemisphere. But by the time you get to the southern hemisphere across the equator, all of this is going to be so obvious to you that you're not going to have any trouble at all flipping yourself and realizing that the z angle is different. In fact, if you look at your numbers and think about them, and you get a direction to the sun of 220 and you shot the sun in the morning, you know that's not right. The sun wasn't at 220 degrees. Look at your compass. It wasn't at 220 degrees. It was at, well, what would that equate to? You know, 220 over here would equate to 360 minus 220, so 140. Would have been 140. And you just think, well, was the sun at 220 degrees or 140 degrees? That should be obvious. So remember, your numbers make sense. If you take a morning sun sight and you come up with a direction to the sun of 220 degrees, you messed up on this part of the problem, the direction part. Look at it again and it's like, oh, wait a second, no, it's 140 degrees. That should be obvious. So remember, don't treat your numbers as just numbers. Treat your numbers as ideas. They mean something. They have an intrinsic meaning that has to be right. It has to make sense. So the Z really isn't that difficult. And what you're getting is, in this case, the Z was 120, and the azimuth was 120 degrees. It might be easier to call that direction, but we don't want to use the capital D because we use this capital D to indicate the distance between the 2 points. Surprisingly, interpolating for the declination can be confusing. It's not that complicated a concept, and in fact, doing it with a calculator is probably the simplest way to do it. But we don't want to be relying on too many electronic devices. That's why we're doing celestial navigation, where all we have to rely on as far as electronic devices is an accurate clock, accurate time. So let's do it both ways. Let's interpolate for declination using a calculator, and then we'll check that with the tables. With the interpolation pages of the table. See here, here inside the front cover is interpolation table, and it continues. It's not repeated, it's continuing on the back, inside the back covers. Okay, let's get some numbers going here. In fact, first let's clean up our board and take out the situations that we're not going to use. We're going to use that first situation that we were working with here, where we took a morning sun sight. Get rid of this down here. And there, that looks a lot better, doesn't it? Where we took a morning sun sight, and so the Z value we get will actually be the same as the azimuth. Z equals AZ. Okay? It's the actual direction from our assumed position. Let's label everything here. Assumed AP, assumed position here, latitude and longitude. GP of the sun here, latitude and longitude, actually declination, and GHA. And remember, we combined our longitude. This is longitude. That's actually called A lat and A longitude. Okay, assumed lat, and let's put that up here. Assumed latitude, 60 degrees. Remember, our latitude, we just take any latitude we want that's close to our dead reckoning latitude. Round up or round down, whichever is going to give you the closest latitude, whole degrees of latitude. You don't want to have to interpolate for minutes and tenths of minutes of latitude. You want to use whole degrees of latitude. So just round off your dead reckoning latitude. And we rounded off to 60 degrees even latitude. And our LHA, remember, we combined our Greenwich hour angle of 60 degrees 14.2 with an assumed longitude of 135 14.2, so we would get an even number for our LHA. and that gives us 75 degrees LHA. So here's our LHA, assumed latitude, and our declination. Let's take a declination of, the declination, remember, we've come out of the nautical almanac for the exact position of the sun. Let's take a declination of north. Well, we're going to need a little more room here so you can see it. Declination of north 10 degrees 12.6 minutes. Does that show? Yes. North 10 degrees 12.6 minutes. And what are we trying to get out of the tables? We're trying to get out a height corrected and a z that will correct to an azimuth angle. And in this case, our z is going to be our azimuth angle because we're doing the basic triangle shooting the sun in the morning, and so the table is going to tell us this angle. Okay, here's where we're going to have to interpolate for this 10 degrees, the 12 point, we can enter for 10 degrees, but we have to interpolate for the 12.6 minutes. So let's look what we've got. This is the right table, right? Well, we're just barely in it, aren't we? 45 to 60 degrees. Well, that's okay. A lat, 60 degrees. So that's going to put us onto the latitude across the top, so that puts us in the last column here, and LHA is the second thing we're going to enter with, or actually the first thing we'll enter with is the LHA because that's the page. LHA of 75 degrees right here, so LHA 75 degrees, and assumed latitude of 60 degrees. So that's this column right here, last column here. So we're doing good so far. We've entered with two variables, 75 degrees LHA, differences in longitude between our longitude and the Greenwich hour angle of the sun or planet. And then we've entered with our assumed position latitude, now which we were able to round off because it's just an assumed position, it's not real, it's just assumed. And let's see. Let's check that out. Latitude. Oh, contrary name to declination. Easy mistake to make. So, glad we caught that one. Okay, here. Latitude, same name as declination. That's right. North declination, north latitude, same name. Okay? So now, 75 degrees LHA. Latitude, we're way over here. 60 degrees. Latitude 60 degrees, we rounded that off to even 60 degrees, and declination 10 degrees 12.6 minutes. Remember, that's the latitude of the sun, 10 degrees north. So here's 10 degrees, and our value for the z value is 98, is that right? Yeah, 98 degrees. So Z is 98 degrees. Same name, 60 degrees. 98 degrees. Even, 0.0. 98.0 degrees. Okay, so we got that. That's the first thing. We need that. Let's put a box around it. We need that. Actually, can I call you back in a little bit?
Yeah, it sounds a little overgrown.
Yeah. Let me talk to you later. I'm recording. I'm in the middle of the recording. I'll talk to you. No, not tonight. Okay, so here we are. Latitude, same name as declination. 60 degrees, declination of 10 degrees, 12.6 minutes. So we start with 10 degrees. We're going to be interpolating between 10 degrees declination and 11 degrees declination. And here's our HC value. 1607.8, and here's the D value. The difference between 1607.8 and 1659.7 is going to be 51.9. Okay, that's going to be the change in the sextant reading we would have gotten if the declination had been 10 degrees and had changed to 11 degrees. That's the difference in the sextant reading. If friend had been, or if the sun, actually it's the sun, had a different declination, had a declination of 11 degrees instead of 10 degrees, then the sextant reading would have been the second reading, the difference of 51.9 minutes. Okay, so we're going to have to interpolate between these two values here. Well, let's write this first one down, and I think we've got enough board over here for this process because we need some space. So HC is same name for 10 degrees, 1607.8. 16 degrees 07.8 minutes, and the D value was 51.9. D equals 51.9 minutes. That's the change between a declination of 10 degrees and a declination of 11 degrees. Okay, and remember when you're interpolating, you got to know which way to go. 60 degrees from 10 HC, from 10 to 11, the value is going up. So we're going to be adding our interpolation value. Okay, remember adding it. Now, we can interpolate with the calculator just by taking 51.9 over 60 times 12.6. And let's do that. Okay, so we'll interpolate with the calculator first, and then we'll interpolate using the tables. And one would assume we'd get the same answer. So we'll do 51.9, the D value, the change in the HC, the height we would have gotten between a declination for the sun of 10 degrees and a declination for the sun of 11 degrees, the heights computed, the sextant reading would have changed by almost a whole degree, by 51.9 minutes. But we're not going all the way to 11 degrees, we're just going 12.6 minutes. So we're going to go 51.9. Here we go. So see if you can see that. 51.9 divided by 60 is that times 12.6 equals 10.89. 10.89. And that's going to round up. That's minutes, because this is minutes and this is minutes. We're not concerned about hundredths of minutes, so that's going to round up. 10.89 is going to round up to 10.9 minutes. Okay, so that's our correction to the HC. And we did see that the HC was getting higher and higher, going up in value as the declination went up in value. So this correction will be added to the HC to correct for the 12.6 minutes of declination over 10 degrees. So let's check this using the tables and make sure we get the same answer. You know, the tables you can enter with either value as well if you can find the value on the table. For now, let's enter the tables the way they were written, intended to be used. Declination increase. Our declination increment was 12.6 minutes over 10 degrees. So we're looking for 12.6 down here, and there we're going to find it right down in here. This is a heavy table, it's hard to hold up like this. 12.6 right here. So our declination increment 12.6, and 51.9 was the D value, the change in HC for a 1 degree change in declination. And we're going to go across to the 50 column, because we're looking for 51.9. So here's 12.6. Go across to this column here, the 50 column, and we get out 10.5. 10.5. Let's write that down. So our first correction value, first part of the correction for 50 minutes of D value is 10.5 minutes. And then our second part of our correction, we have to go to the top, and we're going to be in the units. We're looking for 1.9. So we're at 12.6. We go across to the first column is 0. The second 0 and then tenths. The second column is 1, and we want 0.9 tenths. So we get out of, for the 1.9, we get out a correction of 0.4, and that's added. 0.4 minutes. And look at that. Our final value from the interpolation tables is a correction of 10.9, the same here. So interpolating with the table will give you the same value as interpolator. You can do this long division if you want, but a calculator makes it easier. And remember, this problem is exactly the same as 12.6 divided by 60 times 51.9 minutes. These are the same problems and give the same answer, 10.9 minutes. Okay, now that we've got the 10.9, let's use the 10.9 we got out of the interpolation tables. Get ourselves more space here. Now we've got the 10.9 correction. Our correction that's the D correction, not the D value. This is the D value here. This is the D correction. D correction is 10.9 minutes, and our HC is equal to 16 degrees. This 17, area 1, 18.7 minutes. Okay, so our final HC corrected for the 12.6 minutes of declination over 10 degrees of declination is 16 degrees, 18.7 minutes. And just to get into the next step, the next step, remember, is all has to happen on this little chart, because this is way off the chart. We're trying to get the problem onto that little chart. Well, let's draw that little chart and surge ahead here and get this last step. Okay, here's our chart. And our assumed latitude was 60 degrees. Latitude 60 degrees. 59. These are north. North 60. North 59. North 58. North 61. So our assumed position here, north 60 degrees, is going to be on this line across here. And our longitude, our assumed position longitude, 135, 14.2. So 135, west 135, west 136, west 137, 135. We can't round this off, remember? That's our assumed position longitude. We couldn't take 135 because we had to get an LHA that was even. So our assumed position longitude is 135, 14.2 minutes. Even though we're not really there, we can't just drop those minutes. It throws the whole thing off. It changes the whole problem. So we have to get exactly 135, 14.2 minutes, which is going to be about there. So our position here, our latitude, we rounded off before we did our math, before we entered the tables, so that is whole degrees, north 60, and so there we are. That's our assumed position, AP, and it doesn't hurt to label 135 5 degrees, 14.2 minutes west, and north 60 degrees. Okay. And our Z, where's our Z? Did we get, yeah, here's our Z, azimuth angle. Remember, our Z equaled azimuth because we shot the sun in the morning, 98 degrees. So just over 90 degrees, almost east, not quite. So that's our azimuth angle. If you follow that line far enough, thousands of miles across the surface of the Earth, you get to Joe, who's standing right under the sun. Right when we took our sextant sight, the sun was right on top of his head, and at the GP of the sun. Okay, and then our height computed is 16 degrees, 18.7 minutes. Well, we don't have an HO here in this problem yet, so we better say our sextant, right? Our sextant sighting HS, we corrected to HO, and we got an HO equal to, we corrected for index correction, the sextant error, corrected for dip, and we corrected for the altitude bending of the light as it came through the atmosphere. Ooh, fairly low. A lot of altitude correction. That's as low as we like to take a sight. So there's probably quite a big altitude correction there. So our HO came out as this. We haven't done this. I'm just creating an HO here so we can finish this problem. Our HO from our section reading, let's say it was 16 degrees, 32.9 minutes. Okay, now what's the difference between, we're not at our AP because we didn't get an HO the same as our HC. We're not at the AP. We're either closer to the sun on part of that circle around the sun, or we're farther away from the sun on part of the circle farther away with a bigger diameter, bigger radius rather. What's the difference here between these two? Well, 32.9 minus 18.7. The difference is 0.2 there, and 32, that would be 14.2 minutes. 0 degrees. 14.2 minutes. Okay, so our AP, our assumed position was pretty good. We're only, it wasn't very far off. We were doing really good dead reckoning. We're only 14.2 minutes away from our assumed position, or 14.2 miles. So the arc, our actual position when we get two lines crossing, might be a little farther off. 14.2, which is bigger? Observed was 1632.9, computed was 1618.7. Remember, the one thing that is so easy to remember, rather than thinking, well, was I closer to the sun or was I farther away, is Coast Guard Academy, CGA. Oopsie. CGA, Coast Guard Academy. Computed greater away. Well, in this case, computed was less, wasn't it? Our HO was greater. So computed greater away, the computed is less, so we go towards. And that puts us on a circle, but it's such a big circle, we go towards the sun by a distance of 14.2 miles, or 14.2 minutes, measured on the latitude scale. 14.2, that's not very far, is it, on this scale? And that's going to put us on a line that's perpendicular to the direction to the sun, because that line represents part of the great huge circle around the sun. And that's our LOP. LOP for the exact minutes and seconds that we took our sextant sight. Okay? And that's the final step in the problem. It'd be nice to take an actual problem from the beginning all the way through and get to this stage. And so that's probably the next thing we'll do, where we'll use a different problem and actually throw the numbers up here, pull the numbers, and you'll see when I'm explaining it as we go, it takes longer, but you'll see that you can get to this line of position in about 5 minutes, especially with the sun side. It's one of the simpler ones to work through. And then, of course, the next step, and this confuses people, the next step is do a second problem, maybe the sun in the afternoon. If you've stayed still, that works great. If you have moved during the process, during the time between the morning sight and the sun's and the afternoon sight, you're just going to take this whole problem, lift it up, and move it whatever direction, whatever distance and direction you've sailed in your in the hours between the two sights. So not a problem. It's called advancing your morning sight to the time of your afternoon sight. And then the part that confuses people is your assumed position does not have to be the same at all. Even if you took several sights at once, your assumed position is not going to be the same, because you're always going to doctor up your assumed position to match so when it's combined with the position, the longitude of the sun or star or planet, the GHA of the sun or star or planet, your LHA, your local, the difference between your longitude and the GHA of the planet is going to come out even. The local hour angle has to be even to get into the tables. So your assumed position for your next sight is going to be different. The latitude will be the same, but the longitude will be something different. Probably not too different, not a whole degree different, because you're going to take whatever assumed position longitude is closest to your as close as possible to your dead reckoning position, so that you still get an even number for your LHA, even number of degrees. So you're going to have a slightly different assumed position, and then let's say the sun was in the afternoon, and now you have a second line of position, and in this case, let's say computed was greater, so you moved away in the opposite direction from the sun, from the azimuth direction. And remember, the z is not going to be the azimuth. Now it's going to be 360 minus the z is going to be your azimuth direction. And you're moving away, and then you have a line of position perpendicular to the direction to the sun in the afternoon, and you're going to be right at the where the two lines cross. That's your fix. And you circle that point, and you write the latitude and longitude of that point right next to it. So you now know exactly where you are. Okay. Probably about the third time you watch this, it'll make sense to you, because there are all these different parts that you're putting together. But the big thing is, make sure the numbers make sense. We're going to work through a site, and you'll see how quick and easy it is. With a little less explanation and more just moving through it quickly. First correcting your sextant site. First correcting your time. Watch time, local time to Greenwich Mean Time. Then going to the nautical almanac. And then correcting your sextant site. HS height sextant corrected for index error and for dip, height of eye above the water. That gives you HA, height apparent, and then correcting HA for altitude corrections, the bending of the light, gives you HO, height observed. That's the final thing that we'll be using. And then going into the nautical almanac with the exact time, Greenwich Mean Time that you took your site, getting out the location of the sun or planet, whatever you shot, the location on the surface of the Earth, which was directly underneath that sun or planet. And we'll get that in terms of latitude and longitude, but we'll call it declination and Greenwich hour angle. And then going into the site reduction tables with the latitude, the declination and Greenwich hour angle, and our assumed latitude and our assumed longitude, and that's actually assumed position longitude or assumed longitude, a longitude, and coming out with three things, combining the longitudes, here the Greenwich hour angle, longitude of the sun or planet, combining that with the assumed longitude so that we get an even number for the difference in longitude, and then taking our assumed latitude as a whole degree nearest our dead reckoning latitude, and then taking the declination latitude of the sun or star or planet, which we cannot round off. That's where it was. We can't touch that. We can't mess with it. And then entering the site reduction tables with the three values: assumed latitude, local hour angle, the difference in longitude, and the actual declination. First entering with LHA, that's the page, and then entering with the assumed latitude. Remember, same name or contrary name. If you're in the northern hemisphere and the sun is in the southern hemisphere, contrary name. If you're both northern latitudes, sun's declination is north and your latitude is north, same name, page. And then finally entering with the declination, entering with whole number of degrees, pulling out your HC value, height computed for the degrees, whole number of degrees, and then interpolating using the D value from the site reduction tables, using the D value to interpolate from 10 degrees towards 11 degrees, just the distance 12.6 minutes, which you can do just on a calculator, or you can do it with the tables in the back, either way. And getting a final height computed. Compare your height computed from the site reduction tables to your height observed. The difference is telling you whether you're closer to the sun or farther from the sun. And that's about it. Oh, the Z value. Remember, table height site reduction tables will also tell us the Z value. That's the direction towards the sun or planet. And you have to think about that? Was it the actual z value equal to the azimuth value? Or were you looking to the west, or were you in the southern hemisphere? And then do that diagram, and just every time do the diagram. It takes 30 seconds. Do the diagram, sketch diagram. Which direction was the sun? Is the z direction the actual azimuth direction, or is the z got to be adjusted because it was one of the other triangles rather than the right hand triangle? And so place your assumed position based on the assumed latitude and the doctored up assumed longitude, and then draw the direction to the sun, and then take the difference between the HO and the HC, and either go Coast Guard Academy, computed greater or away. If the computed from the site reduction table, the computed sextant reading that you would have gotten is greater, then go away from the sun. If the computed is less, then go towards the sun. Draw a perpendicular line which represents the great circle around the sun, and that's your LOP. That's it. To do the whole problem is literally about 5 minutes. To work out several sites, you might figure on 15 minutes or so to work out all the sites, or a second site for an LOP, or a third site to check the first two. Okay, so and as the big thing is, every time you do it, it's the same thing exactly. And the mistakes you're going to make are not because you don't understand it or something you can't conceive of it. It's just so simple once you've done it a few times. The mistakes you're going to make are just really simple mistakes, like misreading your numbers, getting in the wrong column, following across in the tables, but going up instead of across, or down instead of across, missing or getting too far across into the wrong column, pulling out the wrong number, or just messing up the number in your head between reading it in the table and writing it down on your piece of paper. Those are the types of mistakes you make. Remember, one of the really simple mistakes is is that a 0 or a 6? That's one of the numbers so easy to confuse. Did I write a 6 there or a 0? I don't know. Your guess. So write your zeros correctly. Make them join each other. Write your 6s like that. Make the numbers really, really clear. Always label everything, every aspect of everything, what planet it was, whether it was sun or star or Venus or whatever. The GMT, label it GMT. And all these things, each thing, every line has to be labeled. And always put in degrees, this degree symbol. Always put your minutes in, even if it's a 0 minutes, 0.6 minutes. Don't just write 0.6 minutes. You're going to mess up. You're going to get this in the wrong column. Always write everything as clearly as possible, and you'll find your navigation goes really smoothly and really easily, and it's a lot of fun as well. It's kind of like magic. It's very, very exciting and fun, especially the first few times you do your sights and come out within, very close to your dead reckoning position, or when you cross an ocean and you sight landfall within 5 minutes of when you anticipated sighting it based on your celestial navigation positions that you've been computing. So very exciting stuff, a lot of fun to do, and really quite simple. Even though it may seem a little bit complicated right now, it does start to seem very, very simple. Okay, last thing we'll do is work through an actual problem with real numbers, and you'll see how quick that can go. But you've seen it all now, and I think you should be in really, really good shape. Okay, one more thing we'll do is we'll show how to create a plotting sheet. You can use your chart itself, and that works okay, but you'll tend to get an awful lot of numbers and stuff on your chart. If you use a plotting sheet, which you can either buy a plotting sheet or you can create one. If you use a plotting sheet, then you just take the final fixed position, latitude and longitude, and place that as a dot on your chart, and your chart stays a lot cleaner that way, rather than doing all these different lines and lines of position and lines direction towards the sun and stuff on your actual chart. So we'll look at how to do a plotting sheet, and we'll go through a problem, and then I think you'll be in good shape. You're ready to head for New Zealand to see the America's Cup races. My daughter is actually on the design team for the AC 75s for the 2021 America's Cup, and so that's very exciting. I hear updates every now and then, or frequently, about progress on the New York Yacht Club's team designing the boats. They've launched their first 38-foot prototype, the half-size prototype, and the final boats, 75-foot boats, are going to be absolutely phenomenally amazing. So very exciting stuff. So if you're sailing to New Zealand for the 2021 America's Cup races, you're in good shape now, with the navigation part of it at least. Just a little bit more about the site reduction tables and what we're trying to do in the site reduction tables. Remember, we're trying to get our height computed and the Z out of the site reduction tables. The Z will turn into the azimuth direction, which is the direction from the assumed position that we've chosen, pointing right at the star or planet. Now, we're doing it in a slightly different way than the standard way. Not the HC, we're doing that in a very standard way. There's only one way to do that. Remember, with the HC, you're going to have to interpolate for the declination, because the declination of the star or planet is where the star or planet was. You can't change that. But we do that in a very standard way. For the Z, changing it to the azimuth, it's a fairly simple concept to make the switch from Z to AZ, the actual direction to the star or planet. And if we understand how the tables work, it's easy to make that transition from Z to AZ. The standard way of doing it involves creating an LHA, local hour angle, the difference in longitude between our assumed position longitude and the Greenwich hour angle, longitude of the star or body. The standard way of doing it involves a lot more complicated numbers, and it's a little bit like doing your income tax, where you get into numbers just like, oh, what does this number actually mean? So it's easier just to do it as the difference, LHA is the difference in longitude, and then figure out what the Z value actually means as given in the table. So I want to give you all the different examples of how the Z value can be figured. We've basically seen the four triangles, but I want to just go over that one more time, because we are doing it in a slightly different way, which requires that you just understand what you're doing, rather than doing it through some system that gets into adding larger numbers. And sometimes, well, you can see the notes. We'll find this note in here, and you'll wonder what it means, and you'll also wonder why these pages have two different LHAs, 13 and 347. They're, you know, the 360 minus 13 is 347. And you'll see these notes, where's the note? Over here. You'll see these notes about LHA, I can't read it. Oh, LHA greater than 180, ZN equals Z. And, you know, you can do it this way. Once you understand it, you can do it the way the tables are set up. Or you can just find the difference. LHA just is the difference in longitude. It doesn't matter if it's plus or minus. You don't go up to 360 or anything. It's just how far apart the longitudes are. And then you just have to interpret the Z correctly. And let's look at the different situations here. Here's the Earth. So, and equator here. First situation is the simplest. Here's the North Pole. Here's the South Pole. First situation is the simplest. Here's our AP, assumed position. Here's the GP of the sun or the planet or whatever. And in this case, the direction to the GP from our AP is measured from north around, and that is Z. And that's what the table is going to give us always for this when we're shooting a body that is to the east. It's going to give us Z such that Z is the direction to the body. We don't have to do anything to the Z we don't have to change the Z. It's measured from north. We're in the northern hemisphere, okay? Northern hemisphere, assumed position is to the west of the ground position. The ground position is to the east. We shot the sun in the morning, and Z equals AZ. Okay, another situation slightly different is this. You'll see this really isn't different, but I want you to see that it's not different. Here's our AP down here, assumed position, GP up here. That's pretty far north. That would probably be a star or planet. Now our direction is like that. Again, the table is going to be measuring from north to the direction to the GP, that's Z, and that's actually the same as azimuth, measured from north to the direction to the star. That's the way we measure, that's the way we're familiar with measuring directions, from north through to the east and on around 360 degrees. So in this case, again, Z is equal to AZ. Okay, what happens, and these are all same name, latitude and declination, same name examples. See that? Latitude, same name as declination. What happens when the AP is northern latitude, assumed position, and GP, ground position of the sun or planet, is southern latitude? How is this measured, that direction? Well, just the same. From north around to the east and on to the direction to the star. So again, Z equals AZ. But you're going to be entering, you will have entered the tables on the same name, declination, upside down, sorry. Declination, same name, no. Declination, a latitude contrary name to declination. You will have been working on those pages to pull out your AZ, your HC, and your Z. Latitude contrary name to declination. Northern latitude, southern declination. Okay? So contrary names. Let's take, we're still shooting to the east. Let's take the opposite situation, where we're in the southern hemisphere. Well, let's save the southern. Let's wait on the southern hemisphere. Okay, we'll wait on that one. Okay, now let's take the other northern hemisphere situation, where here's our assumed position, and we shot a GP that was to our west. Ground point was to the west, assumed position AP, and that's the direction to the star. Well, remember, the table isn't distinguishing between this problem and the problem we just saw where the GP was over here. It's going to solve it as though it's the same problem, because the LHA, the difference in longitude, is the same, and the latitude of the GP is the same as this latitude, and the latitude of the AP is the same as that latitude. Latitude of the GP being declination, of course. Okay, so in this case, the Z it gives us is going to be this angle, Z. So in this case, when we're shooting to the west, we want this angle here. This is the angle that we're used to talking about, is this angle. Well, we shot something to the west, so AZ, our direction, our actual direction, azimuth, is going to equal 360 degrees minus Z. You can just see it. Do the diagram. Do this diagram. How long does that take? 10 seconds? Do that diagram. We shot to the west. Oh, 360 minus AZ is going to equal 360 minus Z. The direction to the sun is 360 minus Z. Okay, let's do it where opposite. Okay, let's do it AP down here, AP, GP up here, ground point. That's the direction will be from us to the body that we shot. And what's the Z now going to be? The Z is going to be here, azimuth, that direction. Okay, the same thing. We're going to have to do, the Z is that measured here. So our azimuth is going to have to be our actual direction. The phrase, the way we're used to phrasing it, is going to be 360 minus Z gives us the azimuth, or the actual direction, phrased the way we like to phrase it. Okay, so that's all the northern hemisphere situations. Oh, I think there was one more, wasn't there? Where we have opposite. Here's our AP up here, and our GP, so opposite, contrary names. And this is going to be GP here, and this is going to be the direction there. And this is going to be the Z here, out of the table. That's what the table will tell us. Same as if the GP was over here. Table solves those two, it's the same problem. And so again, we're going to have to do, to get from north around to the east, a measurement, we're going to have to do azimuth AZ equals 360 minus Z. Again, do your diagram. Again, another 10 seconds to do the diagram, and it makes it super clear. Okay, so those are the northern hemisphere ones. Northern hemisphere is a little bit simpler than southern hemisphere, but southern hemisphere is easy enough. Okay, so now let's put ourselves in the southern hemisphere. Here's our assumed position. I have to think upside down now. Here's our AP, and we shot the sun to the east in the morning. Here's the GP, and this was the direction that we shot. Now, actually, our AP can be right here. And that's the direction we shot there. So what's the table solving now? Well, remember, it's solving the same problem as here. AP and GP. It's not going to distinguish between this problem and this problem because the, let's move that down a little bit. Because the declinations are the same, north versus south, but it doesn't care. The math is going to be the same. The local hour angle, the difference in longitude, is going to be the same. The latitude of the AP is going to be the same. I didn't do them exactly the same, but put that AP there. Latitude of the AP is assumed position is going to be the same. Just north versus south, but the math doesn't care if it's north versus south. And so it's solving this problem up here, where that's the azimuth. In this case, it's telling us this angle here, measured from south up, because this triangle up here is the same as the triangle down there. This triangle here that it's solving is the same as this triangle here that it's solving. They're mirror images of each other. But we have to be aware that we are being told this Z value here, measured from south around to the east and up to us. So in this case, we always think of direction measured from north. So we want this as our AZ, measured from north down to the direction. And so what are we going to do there? It's not that, it's not this. It's going to be 180 minus Z. 180 degrees minus Z. In this case, 180 straight down minus this much gives us the actual direction measured from north. Okay, let's look at another variation here where its contrary name. Declination and latitude are contrary names. Here's our assumed position still down here, AP, and our GP is up here. We shot the sun in the morning, but the sun was north of the equator. We probably can't see it if we're that far south. Let's move north a little bit. Here we are, AP. And that's our direction, AP to the ground point of the sun. What direction was the sun when we shot it? It was northeast. And the table is still going to, is again going to solve it for this angle here, because it's the same as the mirror image in the northern hemisphere. And so that's the Z. And so to get this direction, again, we want the direction measured from north. We always think of directions measured from north. Here's the direction to north. We want this angle here as our azimuth. So again, it's AZ azimuth equals 180 minus the Z value that they give us. Okay, let's look at the other situation where we're in the southern hemisphere. This is the last situation. And we're shooting to the west. Here's our AP. We shot the sun in the afternoon. Here's the GP over here. And we shot, oh, you know, I think we forgot a situation, didn't we? Let's go back. There's one more situation here. Here's our AP up farther, and we shot a GP of some planet or something that's farther north, but still east. So let's get our AP lined up there. Here's our AP, and here's our direction. The table again is solving the same, the mirror image up here, and it's going to tell us the Z based on this direction, because it's thinking in terms of this quadrant here. And so that's the Z. So to get our AZ, which is measured from north down to the direction to the sun, we like to think in that way. We just go 180 minus Z. So in the southern hemisphere, if we're looking to the east, we're going to do this. 180 minus Z is equal to the direction. Okay, now let's take the last set of situations where our AP, let's do our AP here, assume position, and we're looking to the west. Here's a GP over here, the sun. We're shooting the sun. That's the direction there that we're shooting at. The table is going to tell us from south, because it's thinking that it's the mirror image up in the northern hemisphere flipped over. Okay, so it's the same as this. The table is solving a problem that's the same as this. Here's an AP. Here's the GP over down here. That's the direction. The table is going to solve as though it's this question, this problem here, that being the Z value. So it's flipped over, and then it mirror image over here, and then flipped down to here. Those are the same problems as far as the table is concerned, because the difference, the LHA is the same. LHA, that's the same difference as here, local hour angle, difference in longitude to LHA. And the declination is the same. This one's a south declination, that's a north declination, but it's the same number, 15, that's about 15 degrees, 15 degrees. And the latitude is the same. That looks like about 55 degrees. 55 degrees. So it's the same triangle. It's solving once instead of solving the same thing 4 times. Okay, so that triangle is the same as this triangle as far as the table is concerned, because the numbers are going to work the same way. But the z is now going to be this angle here, measured up to the west from south. And so to get the AZ, now we have to do a little bit of fancy footwork. We're going to take 180 plus z. Okay, and that'll give us our angle measured from north around to the east through the south up to the direction to the GP. Okay, one more situation here, or a couple more. Let's do contrary names. Contrary. So now our GP is up here. AP stays down there. GP is just north of the equator. So contrary, AP latitude is south. GP latitude or declination is north. So contrary names. Now the direction is like that, up to the GP. The table is still doing the same thing. It's going to give us this Z. The mirror image flipped over here. It only solves this quadrant, remember? And then it is the same problem flipped over here, same problem flipped down here. So when you flip it twice, you get that Z is now measured from south up to our direction. And so again, AZ, the direction to the planet or sun or whatever, is 180 degrees plus Z. Okay, and one more variation where we're still in the southern hemisphere shooting to the west. Let's put our AP up here. We're back to same name, right? AP there and GP to the west. Both of them southerly latitudes, southerly declination. And now our direction to the GP is like that. And let's see what we get now. Well, what problem is the table solving? Well, it's the mirror image flipped over to this quadrant, flipped up and then over. So the Z that it's telling us is going to be measured from south up, I think I was using orange, wasn't I? Up to that angle. So that's the Z value that the table is going to give us. And to get our azimuth angle, which is the angle that goes all the way around from north, here's north direction, measured all the way around from north to the direction, that's going to be 180, this is 180, plus Z. So exactly what we had before. So these diagrams are really simple to do. If you don't remember, what if you shot almost directly south and from your AP and you can't remember if it was to the west or to the east? Well, just compare your longitude, your assumed position longitude, compare that to the Greenwich hour angle of the sun or planet. If the GHA is higher than your westerly longitude, then you shot to the west, okay? And it's going to be 180 plus Z if you're in the southern hemisphere. So just do your diagram, figure out if you shot something slightly to the west or way to the west or slightly to the east, figure out whether you're in the northern hemisphere or southern hemisphere, and remember that the table just gives you this one Z, and you have to figure out your Z based on what direction you shot. If you know you shot something to the west and your Z comes out as 103 degrees, I mean your azimuth comes out as 103 degrees, if you shot to the west and the Z was 103 and you think, okay, let's see, and you work out, somehow your diagram's wrong, and you work out that your azimuth direction is 103, but you shot something to the west, you're wrong. It can't be 103 if it was to the west. That's to the east. Okay? So the numbers, again, the numbers represent ideas. They represent what you did. They aren't just numbers. Okay? So that's the biggest problem with some of the traditional ways of doing celestial navigation. The numbers just become numbers that you're manipulating, and they lose their context. They lose their sense of, oh, wait a second, I was shooting north, I was shooting east, and I should have an azimuth direction from the assumed position to the ground point that indicates I was shooting east, because that's what azimuth direction means. That's the direction I was shooting. So the direction makes sense. So it's not a difficult thing to figure out. And if you do it the standard way, with just manipulating the numbers and then following some formula that tells you, subtract this if that and such, it's very hard to wrap your head around that and make sense of it. Whereas these diagrams make it really obvious, where you can understand what is happening and why it's happening that way. And you're much less likely to make mistakes when you understand what is happening and why it's happening and what the numbers mean. And you're not just manipulating numbers that really seem incomprehensible. Okay, so those are all that's just wanted to go over that Z, correcting it to azimuth, the actual direction, the Z out of the table, the site reduction tables, correcting it so you know the actual direction from the assumed position to the ground point of the sun or planet or stars when at the point when you shot the sun or planet or the stars. Okay, now moving on to almost our final stage. But we were talking earlier about how you could plot your lines of position on your ocean chart, your nautical chart, but your chart is going to get, kind of cluttered up with lines of position and pencil marks and probably erasing stuff where if your pencil slipped or you realize you were doing something wrong and you have to erase it all. So it works great to use plotting sheets, and you can buy a pad of plotting sheets for hardly anything. They don't cost much at all. Or if you run out of the pad of plotting sheets, you can make your own. The best way to understand what a plotting sheet is and how it works is to make your own at least once, and then it won't be a mystery anymore what it's about. So let's make a plotting sheet here. This is just a piece of paper. 8.5 by 11 would work, although it's probably a little bit smaller than you really want to work with. A little bit bigger is probably a little bit better. Okay, so we'll have a middle latitude on the sheet, or if it's a blank sheet, we'll draw a middle latitude, like so. And then we'll need a compass, or some way to get angles fairly accurately. And we'll take the compass, this is the 0 degrees on the compass, right? Let's get that lined up right there, lined up on our latitude. And we'll take this point here from 0 up to 90, and that will be the space between our lines of latitude. We can use our compass, our protractor, our dividers, and take that, and all our lines of latitude will be the same distance apart. And we're basically constructing a Mercator projection. All these lines are lines of latitude, equally spaced, and that's what you'll find on charts. Lines of latitude on smaller charts are equally spaced. Okay, and then how do we get our lines of longitude? Remember, as we go north, the lines of longitude converge to the point where at the extreme, the latitude of 90 degrees, the lines of longitude are touching each other. Okay, so our lines of longitude are going to be closer together. Let's construct this chart for a latitude of 54 degrees. So now we go up to 54 degrees. We need a center line of longitude. Sorry about that. We gotta get this off. We put our center line of longitude on here, and that's going to be close to our dead reckoning position. Let's put a dead reckoning position on here. DR of north 52 degrees, 13.5 minutes, and longitude west 135 degrees, 15.9 minutes. Okay, so our middle latitude is going to be 52 degrees. 52 degrees. Oh, well, we had 54. Let's go to this DR. Our middle latitude is going to be 52 degrees, and so as we go up, we go higher. 53 degrees north, and 51 north 51 degrees. And our middle longitude is going to be 135 west, so 135 degrees west. Okay, let's get these correct notation. North 52 degrees, north 53 degrees. Okay, now to construct our other lines of longitude, we have to know how far apart they are at 52 degrees of latitude. Remember, they get closer and closer. At the equator, lines of longitude are going to be the same distance apart as the lines of latitude. But as we go up towards the North Pole, they get closer and closer. Here at 52 degrees, we go up on our protractor. This is 0 and 0 here. We go up on our protractor to 52 degrees and make a little bit of a mark there, right there. Well, that's 50. Sharp pencil. Don't use a felt tip marker. So that's 52 degrees on the protractor. Measuring up on the protractor. You're not going to be able to see very well there, are you? From 0 degrees to 52. I can't see it. 52. And at 52 degrees, let's get that a little cleaner. At 52 degrees, whoops. At 52 degrees, we'll make a mark right like that. Okay, and that's going to be our line of longitude there. And our lines of longitude, again, we can measure the distance and just keep moving it over, because the lines of longitude are going to be all the same space as the first one. So essentially we've created a Mercator projection here. And now we should label it 135. We're going west 136 degrees, 137 degrees, 138 degrees, and east east will be 134 degrees, etc. Okay, and now we want to put, if you wanted to, you can make this 30 minutes, a half a degree, and this half a degree, and you'd have a little bit more precision. Your pencil wouldn't have to be quite as sharp. But let's go with this for now. we have our latitude labeled. You can label it on both sides. That's helpful. North 53 degrees, north 52 degrees, north 51 degrees, and your longitude's 135 west, and so on across the bottom. Now let's put our assumed position on. Remember, it's a little bit different from our dead reckoning position. We're going to round our latitude off to a whole degree, 52 degrees, so our assumed position will be on this line of latitude. And our longitude, we're going to make so that we're going to adjust our longitude so the local hour angle, the difference between our longitude and the GHA of what we shot, comes out even. So let's take a GHA, Greenwich hour angle, of let's say we were shooting to the east, to this, and so we can take a Greenwich hour angle of, let's say, 96 degrees, 26.4 minutes. Okay, how do we combine that with a west longitude of 135 degrees, 15.9? Well, they're both to the west because GHA is always to the west. And so the difference between those two, can you see those numbers? No, we're coming off the screen, aren't we? Sorry about that. The difference between those numbers, the GHA and the westerly longitude, is going to be, let's do it. So we're going to get an LHA, the difference between the two, 135. Well, let's doctor this up right away. So this is our dead reckoning longitude. Our assumed position longitude is going to be 135 degrees, 26.4 minutes. Now it's easy to do the difference. The LHA is the difference between assumed longitude and Greenwich hour angle. Now it's easy to do the difference. 135, 26.4 minutes minus 96 degrees, 26.4 minutes. LHA, local hour angle, is going to be 135 minus 96. 136 minus 96 will be 40, so 39 degrees. Local hour angle of 39 degrees. Okay, so where are we at? Let's get our latitude, our assumed position latitude, AP latitude, remember, is going to be just 52 degrees even. We just drop the minutes, or round up or round down. In this case, round down because we're less than 30 minutes there. Let's rounding down and looking down a little bit. Okay, AP latitude is just going to be 52 degrees even. That's 52. That's our center line here. Latitude, and our AP longitude now is going to be 135 degrees, 26.4. We can't round that off because it has to come out with an even LHA when combined with the Greenwich hour angle. Okay, so we can't mess with our AP longitude anymore now because we need an even LHA. So our assumed position longitude is 135, 26.4. So this is our AP 26.4, just a little less than halfway. Okay, how do you create accurate minutes and seconds on here? Well, if you're using the site reduction, the plotting sheets, the formal plotting sheets, you'll find down here a diagram that looks like this, and you just go up to your number of degrees. It's labeled with latitude degrees here. We're at a latitude of 52, so you take the reading here, and that will tell you distances. The longitudinal distances are recorded down here at the bottom, 0 to 90, I believe. And so we want 26.4, we go where 26.4 down here shows up, 26.4, and we go up to our level, use our dividers, and take that distance and put it up here. If you're making your own chart, you can just divide the distance between two lines of longitude in half, that's 30 minutes. Divide that again, that's 15 minutes. And then divide that in into three parts, equal parts, and each of those is 5 minutes. Okay? So it's easy enough to divide up the 60 minutes of longitude from 135 to 136 into 5-minute increments, and then you can pretty accurately get your smaller increments. So 135, 26.4, so we're short of 135.30. So here's our assumed position right here, AP, assumed position. And then you'd write on it 50 north 52 degrees, 135 degrees, 26.4 minutes west. Okay, and that's our AP. And that's a plotting chart. Then, just to follow through, you're going to get a height computed from the site reduction tables. You're going to get a Z value from the site reduction tables. If you shot to the east, the Z is going to equal the azimuth. Z value will equal the azimuth. And if you shot to the west, it's you have to do your little diagram and do 360. Z is going to the azimuth direction is going to be 360 minus the Z value out of the table. We shot the sun to the east, and so sun's always going to be south of us. So the azimuth angle is going to be something like that, looking southeast. And then we compare our HC with our HO. Let's say our HC was greater, HC greater than HO, computed greater or away. We'd move away by the difference between the HC and the HO, and we'd draw a line of position that was perpendicular to the direction to the star by the distance that we moved away, the difference between HC and HO in degrees, minutes, and tenths of minutes. And that's our LOP, and we would label that LOP sun, and then GMT, Greenwich Mean Time, whatever that was. Okay. Okay, so and in this case, the Z and the AZ were both measured from, told to us from the table, measured from the north, because we're in this quadrant looking to the east. That's the problem that the table solves for us, looking to the east. Okay, so you've seen all this stuff a few times now. This was how to construct and how to use a plotting sheet. And then, of course, you do your second AP. Is going to be, again, near your dead reckoning position. In fact, if you've been sailing, your second AP is going to be near your new dead reckoning position. So you might have an AP that goes way over here. Let's look at one more thing while we have the plotting sheet up here. So we did a second problem. We shot the sun in the afternoon. Here's the direction towards the sun here. And in this case, we had to doctor up the Z to get our actual direction. We did, the table gave us a Z here. We did 360 minus Z and got the direction from north, which is what we like to think of, like that, as an azimuth, AZ. And then in our second site, when we computed the height computed out of the site reduction tables and compared it to our height observed, the height computed was actually less than the height observed. Let's pretend. And so computed greater away, CGA, computed greater away, Coast Guard Academy. Well, computed wasn't greater, it was less. So in this case, we move towards the sun in the direction of the sun by the difference between HC and HO. Let's say there's a bigger difference this time, and we move towards the sun to a new line of position there. Now the problem is we sailed all through the day between these two sites. Let's create some numbers. Let's clear our space here a little bit and create some numbers for dead reckoning, our dead reckoning distance sailed, our dead reckoning speed, 5 knots, our direction, dead reckoning direction, 220 degrees. Is that on the board? Yeah. Dead reckoning direction, 220 degrees. And time between sites, just the difference between watch time of the first site, watch time of the second site, or the difference between Greenwich Mean Time of the first site and Greenwich Mean Time of the second site. It's going to be the same difference, right? The time between sites, let's keep our math simple in this case and just say it was an even 6 hours between the sites. 6 hours at 5 knots is 30 nautical miles. In a direction of 220, we take our first problem, at any point on this first line, let's use a different color, any point on this first LOP, we take that point and advance it 30 nautical miles at the direction 220 degrees. That will be about this direction, and 30 nautical miles is going to be measured on the latitude scale, so half of the distance between 30 nautical miles, remember, it's equivalent to 30 minutes of latitude. So we take our dividers and measure 30 minutes on the latitude scale. Make sure you don't use the longitude scale. It's not equivalent to nautical miles. Latitude scale is equivalent to nautical miles. Use our divider. Move 30 nautical miles in the direction that we were sailing, because that's the distance we sailed. And then through this new point, we're going to advance our line of position. We're not going to move our line of position just sideways 30 nautical miles. We're going to move it in the direction that we sailed, and then redraw our new advanced line of position and label it LOP advanced to GMT, the GMT of the second site. And now where that advanced LOP crosses the second LOP is our position. So this is where we are, right there. That we can call a fix, although technically a fix is, you only call it a fix if you have 3 lines of position crossing, but we can call it a fix. And the fix of that time is the site, the time of the second site, the GMT of the second site, because we advanced the first site. You can't just move the first site sideways. You have to move it, take any point on that line, move it the direction and distance that you sailed during the interval between the two sites. Okay, that's about as complicated as it gets. Advancing your LOP, creating a plotting sheet from a blank sheet of paper, but it's easy to get plotting sheets. Just buy them, buy enough. But if you know how to create it, then you'll understand the plotting sheet much better. And you still have to create your plotting sheet. It just has your latitude and your central longitude, and you have to label them just like we did. The plotting sheets just have the compass rose in the middle, so you don't have to pull out a plastic protractor. So you still got to create your plotting sheets for the latitude that you're at, but they just give you a starting point. Okay, and then we saw how to advance your morning sight to afternoon sight, because really sun sights are so easy. You're going to end up doing more sun sights, and when you do a sun sight in the morning and a sun sight in the afternoon, you're going to have to advance your morning sun sight unless it's dead calm and you haven't sailed at all. So we're doing really well moving through this. You've seen it all now. Let's just work out a sight and take some numbers, put some numbers in, and work out a sight, and you can see how simple it is when you've got all this together, and just work through it. It's fast and easy, and the only mistakes are going to be adding mistakes that are super obvious. I'll try not to make any, but I might. I'm good at making mistakes while I talk. I would like to point out that I could edit out all my mistakes. Since this isn't live television, I could just edit out any place I add things wrong or draw something wrong on the board. But the value of seeing mistakes is that these are the types of mistakes you'll make, simple mistakes. And so it's really helpful, I believe, to see somebody else make simple mistakes, careless mistakes. And so it's best if I leave those in, even though it makes, sometimes I wonder about myself, the type of mistakes I can make. But that's the type of mistake you'll make too. Okay, a deep breath, and here we go. First sight that we're going to work through all the way through. And so exciting moment here. And we are going to start with a sight on May 6th. Sight of the sun, lower limb. And let's get our dead reckoning position up here. Just based on our estimate for the last 24 hours, or however long since we last got a celestial fix. Latitude north. Give ourselves a little more room here. DR, dead reckoning, latitude north, 52 degrees. 26.2 minutes, and longitude, that's pretty precise, dead reckoning, but that's fine. 129 degrees, 13.5 minutes west. That places us fairly far north. More than halfway north between the equator and the North Pole, 45 degrees being halfway north. So about off of Seattle, but farther west than Seattle. So we're in the Pacific Ocean, off the coast of Washington, or maybe at 5240 or Fight. The Canadians. We're off the coast of Vancouver Island, a little way, 123, oh gosh, more than 100 miles out at sea, I believe. Okay, so that's our DR position, dead reckoning position, latitude and longitude. And our sextant sight was taken at a local time of 10/20/16. Let's get over here on the edge of the board and do our time over here so we don't run out of space. Local time 10/20/16, and watch error. We've been calibrating our watch, checking our watch error. And it's pretty small still. We're early on in our voyage. Watch error -2 seconds. And what zone are we in? 129 degrees divided by 15 gives us 8, 120, and 9/15. Plus we have some extra here, additional 13.5 minutes. So 8 and 9/15 is already more than 8.5, so that's zone 9. Okay, we're in zone 9, so we have to add zone. We have to add 9 hours here. And that will give us Greenwich Mean Time, GMT. That's what we want for our watch, for our time. So we got 14 seconds, 20 minutes, and 19 hours. So 19, 20, 14 is our GMT. Anything that's messy, rewrite, because you might misread it. 19, 20, 14, and we are keeping our columns all lined up correctly. If you have your 9 just served randomly, you might add it in the minutes column instead of in the hours column. So keep your columns clear. Okay, so GMT, and what was our HO? HS rather? Height sextant. We read right off the sextant. We got 52 degrees, 02.6 minutes. Sextant reading uncorrected. Let's correct the sextant reading. And sextant index correction, sextant error, index correction on this sextant's pretty small. It's a minus 0.4 minutes. And then let's get our dip. We're on a sailboat. We figure our height of eye is about 8 feet above the water when we were taking our sextant's height from the cockpit. Small sailboat. We go to the front of the nautical almanac, the dip column, and we're right at the top. And dip is always minus, remember? Feet minus 2.8. Dip. Height of eye, 8 feet. Correction, minus 2.8 minutes. Minus 2.8 minutes. Dip. And the last correction, altitude for the lower limb of the sun. Remember, sun, lower limb. And we're in May. So here's the sun altitude correction. Altitude correction tables. Sun, April, March, April, May. April through September. Apparent altitude, our sextant reading was 52. Technically we do this part, this correction here first, and then get the apparent altitude. But the dip is so small on a sailboat, it really doesn't make any difference. You're not creating any real error. You see how I went to the wrong? I looked away from the table, I came back, and here I am, stars and planets. You've got to, every time you look away, you've got to recalibrate yourself. Oh, I'm not stars and planets, I'm sun. Go back and check that you're not, all of a sudden in the wrong part of the table. Sun, apparent altitude, our HS was 52 degrees. So, way down. We're not going to have a big correction at, and lower limb, apparent altitude, lower limb. We're not going to have a really big correction at 52 degrees. If somehow we got a huge correction, we'd know we were wrong. So our correction between 50 and 54 degrees is going to be, let's take the 15.5. See, it doesn't change much in here. 15.5, that's a plus because it's lower limb. Plus 15.5. Oh, yeah, I got in the wrong column again. That's the type of mistake that's so easy to make. I came out of April through September and got over here in October through March. Let's go back down and check that. 52 degrees. Oh, here we are. That's what we want. Plus 15.2. Plus 15.2. Okay, so good mistake. That's why you always look 15.2 minutes. always take the number out of the table, write it down, and then look in the table and do it a second time and check everything. If you assume that you did it right, you're not going to catch a single error ever. Assume that you did it wrong, you'll catch all your errors, or at least most of them. So assume that that number you just wrote down that you just took out of the table, the basic assumption is that you made a mistake, you wrote down the wrong number, now you're trying to find the mistake. And it's not like you finished the whole problem and it didn't come out right, obviously, and you're now going back and trying to find any mistake that you made in all the numbers. It's each number you write down, you're trying to find the mistake. You're assuming you made a mistake because you're going to make mistakes. And when you can't find the mistake, after double checking the whole process, not just part of the process, double checking the whole process, you can't find a mistake, it's just like, can't find a mistake. I wonder, maybe I did it right after all. Okay? The assumption is that there's some kind of mistake. Plus 15.2. Okay, now let's add this all together. And it looks like we're going to come down here with 52 degrees. We'll make sure that's correct. This is going to give us height observed, right? After we've corrected for all this. So minus 0.4, minus 2.8, that's minus 3.2. That's minus 3.2, that's 12. So we get 14.6. Okay, so minutes. label everything or else you're sure to make mistakes. So our height observed. Now that's something we're going to want at the end, right? So we're going to put a box around that. We're going to box that. That's one of the things we need right at the end. We want to be able to find it easily. It's got a box around it now. It stands out from everything else here because it's boxed. Okay, where do we go now? We have our height observed, and which is the sextant reading corrected, and we have our GMT, which is the local time corrected to GMT, Greenwich Mean Time. Now we're through with this for a while. We're just going to be working with this number, the Greenwich Mean Time, and the date for the sun. We want to know where the sun was on May 6th at 1920 minutes and 14 seconds. Okay, so, and we want to know in terms of latitude and longitude basically, but we're going to call that declination and Greenwich hour angle. Okay, and in this case, since the sun is still in the western hemisphere, GHA is going to be exactly the same as longitude. There's no difference between the two, but we will call it GHA. Okay, May 6th. So, right date. And here we are. Sun, May 6th. Yes, it is May 6th. It says across the top, 6th, 7th, and 8th. So we're in May 6th. That's going to be May 6th, 7th, and 8th. That's going to be May 6th right there. And our Greenwich Mean Time is 1900 hours. And we're in the sun column, and we're looking for the Greenwich hour angle of the sun, or the longitude, and the declination, or the latitude. Same things, longitude, latitude, GHA, and declination. And so 1900 hours GMT, here's 19, and our GHA, check the top again, GHA, yeah. Greenwich hour angle is 105.51.7. 105.51.7. 105 degrees, 51.7 minutes. Label it GHA, Greenwich hour angle, same as longitude. Okay, and let's put our declination over here. Declination. Sun, declination, May 6, 1900 hours, 1819, declination. Easy mistake here, just take 46. Oh, well, we have to take the north 16 down. North 16, 46.0 minutes. And check it. 1900. North 16, 46.0 minutes for May 6th. Okay, so we've got our declination and our Greenwich hour angle. Let's look at the declination again though. How much is the declination changing between hours? Here's May 6th, 1900 hours, north 16, 46.0, 2000 hours, 46.7. Still north 16, 46.7. Well, our time is actually 1900 hours and 20 minutes. 20 minutes is about a third of an hour. So we're actually about a third of the way between these two values. So let's just interpolate by guessing. If this was 46.6, the difference would be 0.6 minutes, and a third of that would be 0.2. So let's, our declination is going to be really close to north 16, 46.2. We've just, by eye, just interpolated there. 46.2. Okay, so let's just change that here. 46.2 minutes. And if you want to do it more formally, you can look at the bottom of the page. There's the D value, 0.7. Yes, that was exactly what the declination was changing per hour when we just checked it. D is 0.7. If you want to really do it formally, instead of just saying, well, look, that's obviously going to be about 0.2 correction, you can go into 20 minutes pages in the back of the tables, back of the almanac, 20 minutes, and go down to a D value. Here's the D value of 20 minutes. I'm going to take a look at it here. D value of, oh, here's the 20 minutes. Here's the D value of 0.7. D of 0.7. Here we are. D value 0.7. This is 20 minutes. We forget about the seconds because the declination changes, so it just doesn't change very much. And the correction is 0.2 minutes, okay? Minutes at the top of the column. You see, check the top of the column always. 0.2. And the declination was increasing. We saw it was increasing, so it's going to be plus the 0.2. So declination, that's something we're going to want at the end. We're going to put a box around this. We're going to have to use this later on. But that's all there is to the declination for the sun. Very simple. Okay, and if we'd forgotten to interpolate for the sun, the declination for the sun, that's a 0.2 error. That's 0.2 of a mile. If we'd forgotten, if it was more like 59 minutes past the hour, it would have been a maximum of 0.7 of an error, 0.7 of a mile. That's getting to be a little bit more. That's, the greater part of a mile. So, but the declination doesn't change very much. But remember to interpolate for it. Just make sure you go the right way. Sometimes plus, sometimes minus. May, and I don't think, here, we can check, but I don't, March, April, May. I can't, I don't think they told us, I don't think they tell us plus or minus for that D. I think you're just supposed to be smart enough to, May 6th, yeah. You just have to be smart enough smart enough to figure out whether, as the hours go past, increase, time passes, whether the declination is getting greater or smaller. See, there's no plus or minus there. You can figure that out. Okay, now we're on to the Greenwich hour angle. Remember, Greenwich hour angle, that's equivalent to longitude. That changes really fast because the Earth is spinning 15 degrees per hour. It's actually not spinning quite 15 degrees per hour, but when you add together the spinning speed plus our year-long orbit around the sun, those two motions together equal 15 degrees. Almost. Well, actually very precisely. So our Greenwich hour angle, that's always, the Earth's always spinning the same direction, right? So far. Hopefully it keeps up. So for 20 minutes, we're going to need a correction here of about a third of an hour of 15 degrees. A third of 15 should be a correction of about 5 degrees. If we get a correction that's really different from 5 degrees, we're wrong. We did something, we messed up. Okay, so let's look at our increments and corrections pages here in the back. 20 minutes and 14 seconds. Here's our 20 minutes. And let's get in the right column. Sun and planets, that's good. And 20 minutes and 14 seconds. Here's the 14 seconds. And our correction, oh good, we were pretty close on. We figured it'd be close to 5 degrees. It's 5 degrees, 03.5 minutes. Yes, degrees and minutes, sun and planets. 5 degrees, 03.5 minutes. 03.5. Don't leave out that O. It'll mess up your columns and you'll make a mistake. And so, what is our Greenwich hour angle? Remember, for the sun, that's our only correction. So, and the corrections are always added because the sun's GHA is always increasing as hours pass. And so we get 12 here, 5, and 5. So 55.2 minutes and 110 degrees. And this is the GHA correction. That's plus. And this is GHA. And let's put a box around that. Can you see this? Yeah, you can still see it. Let's put a box around that because we're going to need that later on. Okay? So we've got the things we are going to need. The position of the sun, latitude and longitude of the sun, declination and GHA of the sun in boxes because we're going to need those here. Okay. Let's, I think we're through with this time zone up here. We're going to need a little more space. Let's get rid of the time zone up there. Okay, and now we are on to our site reduction tables. Or to enter our site reduction, we're ready for the site reduction tables. But what we've got are four things that we want to basically enter with, and we can't do that. We've got to get down to 3 things. We got our DR latitude. Well, let's change we need our assumed position. Our assumed position latitude. Well, remember that's just an assumed position. We're not really there. We're just pretending we're there. So let's make life easy. I like that concept, make life easy. So instead of our accurate DR latitude of north 52, 26.2, let's just take an assumed position latitude of north 52 degrees. If this was over 30 minutes, then we'd round up to north 53 degrees. But since it's just under 30 minutes, we'll round down to north 52 degrees even. Okay, and AP longitude, assumed position longitude. Oh, here's the place. We're not there either. I mean, this is, again, just a guess. It's just a pretend place. We're not there. We don't have to be there. We want it to be somewhat close to our dead reckoning position, but we're not really here. So our longitude, we can mess around with that all we want to. Assumed position longitude. Let's make our assumed position longitude, as we were talking earlier, close to our DR longitude, but such that when we combine it with the longitude of the sun, we get an even difference between the longitudes, between those two longitude positions, an even number of degrees as the difference between them. So here's our GHA, 110 degrees, 55.2 minutes. So our assumed position longitude, we could make our assumed position longitude 129. We're going to need a little more space here, aren't we? AP longitude, right small. We could make our assumed position longitude 129 degrees, 55.2 minutes. And our problem would work out, but we're losing a little bit of accuracy there, because from our dead reckoning longitude of 13.5 to 55.2 is almost 40, is a little over 40 minutes. We can have an AP longitude that's closer to our DR longitude if we go down to 128 degrees, 55.2 minutes. Either one will work. Either one will work because, again, it's just an assumed position. But remember, when we draw our final lines of position, we're using a straight line to approximate an arc of a circle, a huge circle. So the straight line's a pretty good approximation. But the closer we are to, the closer our assumed position is to our actual position where we, end up locating ourselves based on our celestial fix, the closer our assumed position is to that final position, the better approximation that straight line is to the arc of the curved line around the sun. Okay, so assumed position 128, 55.2. But again, if you took 129, 55.2, that would work. Even if you took 130, 55.2, you would never do that because why go so far from your DR position? But you'd still get an answer that was really pretty close. You might be like half a mile off then by going so far away from your actual position. But the problem still works out. You haven't messed up the way the problem works at all. You're just losing a little accuracy. Okay, so AP longitude 128, 55.2. And what is our difference between longitude and GHA now? LHA, local hour angle. And we are getting excited because we're getting close. I mean, this is all that's involved in the whole process. So the difference, well, the 55.2 cancels out. So the difference is 18 degrees. LHA, 18 degrees even, right? Now, let's circle, let's use other colors. We're going to put a box around our assumed latitude, because we're going to use that. We're going to put a box around our local hour angle, and we already have a box around our declination. Even degrees, assumed latitude, we just drop the minutes, or round it up or round it down. Local hour angle, even degrees, because we played around with, we jimmied our assumed longitude to match the Greenwich hour angle. Well, why not? Make life easy. And that's actually, you always do that. So, because you have to have an even number of degrees for LHA. And declination, should we just change this up to 17 degrees, have it be even too? No! Wait. That's where the sun was. Don't change the declination. You can't change the declination. That's where the sun was when we took our sextant site. Okay? Assumed positions, you can change assumed positions all you want, but you cannot change real positions where the sun really was. Remember, we didn't change the Greenwich hour angle of the sun at all. We just changed our assumed position longitude to work better with the Greenwich hour angle. Okay, so now we have, and this is the third thing we need to enter the site reduction tables. So now we are ready to pick up our big site reduction tables. And what are we looking for? We are looking for height computed. That's the sextant reading that we would have gotten if we had been at our assumed position. Latitude north 52, longitude 128, 55.2 minutes. If we'd been right at that point and shot the sun right at a GMT of 19/20/14, we would have gotten exactly this computed sextant reading. Okay? And what else are we looking for? We're looking for the direction to the sun, which they'll give us in Z. In this case, since the sun is to the east, remember all those diagrams, we've done those ad infinitum. You don't need to see them again, I hope. Although this is when you would do that diagram in working this out if you didn't have it in your brain because you've done it every day since you left shore. We know that since we're in the northern hemisphere and we shot the sun to the east, that the Z that comes out of the tables is going to be the same as our azimuth, which is the actual direction measured from north around to the east towards the sun. And we're expecting, we shot the sun in the morning, we're expecting a direction greater than 90 degrees but less than 180. That's where the sun is in the morning, right? Between 90 degrees and 180 degrees. So let's say our latitude's fairly high and we shot at 10 o'clock. I'm guessing like 125 degrees or something for our direction. And remember, that's not a magnetic direction, that's a true direction. Okay, and our height computed. We're going to have to interpolate there, right? Because the table's not going to give us an accurate reading for 16 degrees 46.2 minutes. Okay, we can enter accurately for these two values, even numbers, but this one we're going to have to interpolate for. Well, we can interpolate for one thing. That's great. It's not more than one thing. That's easy. Okay, LHA of 18 degrees. That's our first, that's where we start. 18 degrees. And easy mistake here. Latitude, north. Declination, north. Latitude, same name as declination. Same name. Both of them are north. Okay, so let's get on the right page. That's an easy place to make a mistake. You drop your pencil and you come back up from leaning over on the floor, and all of a sudden you're on the wrong side. And you can finish the problem on the wrong side of the page here, and nothing's going to work. It won't make sense. Latitude, same name as declination. Okay, and entering across the top, and we're on page LHA of 18 degrees. Double check. 18 degrees, great. Latitude, same name as declination. Latitude across the top. Our assumed position latitude, 52 degrees, right here. Declination, 16 degrees and 46.2 minutes. Okay, let's get out the value for 16 degrees. You can almost see the top. Okay, so 16 degrees, remember, so the HC, then the D value, and then the azimuth angle, the Z value. So 16 degrees. Let's get the Z value first. 151.7. Now, we're actually going to be interpolating for 46.2, more than halfway down to the next value, which would be 1700. How much difference is there in the Z value? Well, very, very little. Look, 151.7 to 151.2. If we wanted to interpolate a little bit by I, we could just go 151.3 or something. So we're getting down below 151.5. So let's just round it to 151 degrees. We're not going to be able to tell 1/10 of a degree very easily on our, on our plotting sheet. So let's go to 151 degrees. Now my estimate, my initial conjecture that since we shot the sun in the morning, it would be between 90 degrees and 180 was correct. My just a rough guess of 125 degrees was not terribly accurate, but we're not too far off that 151 degrees. That's, yes, southeast. That's where the sun was. Yeah, I remember I was standing on deck and I was looking southeast. I shot the sun in the morning. That makes sense. We don't have to change that around at all. It's the accurate direction measured from north around to the east to the direction of the sun. Okay, so we've got our direction. We're going to put a box around that because we're going to need that. And now let's pull out our height computer. Remember, we're going to have to interpolate for this, for that extra 46.2 minutes of declination. 16 degrees. Let's start with the 16 degrees. Here's 16. 51, 15.9. And then check it. Latitude, same name as declination. Declination, 18 degrees, 52 degrees assumed latitude. And so we're down here to declination of 16, 1642. 16, and our height computed, double check, 51, 15.9. 51, 15.9, great. Now let's pull out our D value. D value at the top for 16, easy to lose your place on these tables. D value of 57.1. 57.1. And we're going to squeeze that in over here, a little bit awkward. 57.1. Is that a plus or a minus? Well, let's check that. 52 degrees, back to where we were. Plus or minus for that D value. Is HC getting bigger as the declination increases? Is HC getting bigger as the declination increases? 52 degrees. 16. We have 151. 17, we have 151. Oh, that's the angle. Here's the HC. We have 51 going up to 52. So the D value is the difference between the HC for 16 and the HC for 17, and it is a plus. It's going up. So this is our interpolation value, 57.1. It's going up 57.1 minutes per degree of declination. So we can look at that and we can interpolate with our calculator, or we can interpolate with the tables. So we'll just go 57.1 divided by 60, 57.1 divided by 60, and that times 46.2. 46.2, and we get 43.96 minutes. 43.96 rounds up to 44. The 6 rounds up and the 9 rounds up then, so plus 44 plus 44.0 minutes. That's our correction for the 46.2 minutes. And let's do that interpolation with the tables as well. Okay? So we're interpolating for a D of 57.1 and a declination increment of 46.2. We're in the back of the tables. So declination increment of 46.2, 46, and a D value of 57. So the 50 column there at the top, that last column over there, this column here, down to 46.2, and our first correction value is 38.5, and then we have to get the rest of our correction value. That was for 50. Now we need for 7.1, and so we go over to our units of 7 and down to the same 7.1, 7.1, and that's going to be a correction over here, 7.1 of, a little hard to do this in the camera, if I back up, an additional correction of 5.5. So we have 38.4 plus 5.5. So that's a correction of 0.9, 43.9. 43.9 rounds up. It's a tenth of a degree different from the correction we got interpolating with the calculator. So essentially the same. So 43.9 versus 44. So we'll go with the 44, and we're almost there, you guys. Our height computed now is equal to 0.9. Are we still? We're getting off our camera, aren't we? We almost fit the whole problem on here. Height computed. 0.9. That's 9. That's 59.9 minutes. 51 degrees. 59.9 minutes. Height computed. Okay. What do we do with that? Let's put a box around it. Height computed. And we are right at the bottom of our board. Height computed 51 degrees, 59.9. Check it. 0.995, 51 degrees, 59.9. Don't want to make a mistake at this point. We're almost there. And can we still see the top? Yeah, more or less. So where's our HO? Remember, we're going to compare our HC with our HO. Both of them have boxes because we knew we'd have to use both of those things. What is the difference between the height computed and the height observed? Well, this is essentially 52 degrees, right? This 59.9, that's just a tenth of a minute short of 52 degrees. So 52 degrees, 14.6 minutes, so the difference is 14.6 plus an additional tenth of a minute for that. So we get 14.7 minutes. Minutes is the difference between the height computed and the height observed. 14.7. Remember, computed greater away. Coast Guard Academy. The one thing that we're going to just remember as a memorization trick. I think we can all remember one thing, especially that's pretty memorable. Coast Guard Academy. Computed greater away. Is our computed greater? No, our computed is less than our height observed. So we're going to go towards the position of the sun, which was at 151 degrees. Let's just review what we've got here. We took an AP latitude of whole degrees so we could get into the site reduction tables. We took an AP longitude let's get a box around that because we're going to need that. That's another one of our values that we'll need here, AP longitude. We doctored up our assumed position longitude. It's close to our dead reckoning longitude, but it doesn't have to be the same. In fact, it never will be the same because we want our AP longitude to be such that when it's combined with the Greenwich hour angle, we come out with a difference of longitude between the position of the assumed position and the position of the ground point of the star. So we want that difference in longitude to be whole degrees. So we're going to change the minutes of the AP longitude, assumed position longitude, around. We don't really care where the assumed position is. We're going to change those minutes around so when we find the difference between the assumed position longitude and the Greenwich hour angle, the longitude of the sun or planet, the difference will be whole degrees. And we'll keep our assumed position longitude as close to the dead reckoning longitude as possible. It should always be within 30 minutes of the dead reckoning longitude, but even if it were further away than 30 minutes from the dead reckoning longitude, the sight would still work and we'd still get a fairly accurate fix. So we have our assumed position latitude, our assumed position longitude, the difference in longitudes here, which we use to enter the site reduction tables. Here was the, what else do we use to enter the site reduction tables? The AP latitude, the difference in longitudes between our assumed position and the ground point of the star, and the last factor was the declination of, or latitude of, the ground point of the sun or star. And the declination is the only thing that we can't fix, so it's whole degrees. The declination is where the sun was or where the stars were. In this case, I guess it was the sun site. Yeah, sun lower limb. So the declination is going to be degrees and minutes and tenths of minutes. We can't change that. We'll have to interpolate for that. When we interpolate, when we entered the tables, we entered the tables for 16 degrees, and then we interpolated for 46.2. Just about 3/4 of the way down to the next value, the value that we would have gotten for north 17 degrees of declination. Remember, north, declination north, assumed latitude north. Same name, not contrary name. Make sure you're on the right page of the site reduction tables. Okay, so we pulled out an HC value for 16 degrees. The height corrected, the sextant reading we would have gotten if we'd been at our assumed position. Latitude and longitude, assumed position, and we'd shot the celestial body of the sun with, if we shot the sun with a declination north 16 degrees 46.2 and Greenwich hour angle 110 degrees 55.2. So we would have gotten a height corrected if of HC 51 15.9 if the declination had been 16 degrees, but it was 16 degrees 46.2. So we have to do a correction based on the change in declination, the change in declination per degree, the change in HC, pardon me, the change in height computed, the sextant reading we would have gotten, the change in HC per 1 degree change of declination from north 16 to north 17 in declination was 57.1 minutes. So we had to interpolate for this 46.2 minutes. That's roughly 3/4 of the way. Remember, it's a 60 base system. 3/4 of the way up to north 17 declination. So we're basically aiming for about 3/4 of 57.1, the change in HC when we go from 16 degrees north declination to 17 degrees north declination. So about 3/4 of that, 3/4 of 60 would be 180, 90, 45. So just our rough estimate is 45, and yes, 44.0 minutes. So we didn't mess that up. I mean, we didn't check the precision of that, but we checked the general concept of it, the ballpark number. And when we did it just roughly in our head real quickly, we got 45 minutes. So 44 looks like a good value pulled from the tables for the correction, for the extra 46.2 minutes of declination. And then we add the correction here because the HCs were getting bigger as the declination got bigger. So we interpolated the correct way. We add the correction to the height computed value that we pulled out for 16 degrees, and we get 51 degrees, 59.9 minutes. And that is correct. We did the adding correctly. Good job. It's easy enough not to do it correctly. So good job here. So we have a height corrected of 51 degrees, 59.9 minutes. That's the sextant reading we would have gotten if we had been at this assumed position latitude, assumed position longitude, and the sun had been at a GHA of 110, 55.2, and declination of north 16 degrees, 46.2. Okay, that's the sextant sighting we would have gotten precisely if we'd been at the AP and the sun had been at the GP. Okay, so now we can compare the height computed with our height observed right up here. So we're coming back up to this box. And nice we have it in a box. It's easy to find. So what's the difference between 51, 59.9 and 52, 14.6? Well, this is, we'll take that tenth, we're not going to just throw away that tenth of a minute, but we can say that this is, for just computing in our head here quickly, we can say this is 52 degrees. It's only a tenth of a minute less than 52. So 52 degrees versus 52 degrees, 14.6 minutes. And so the difference is 14.6 plus that tenth of a degree that we dropped there. So the difference between the height computed and the height observed is 14.7 minutes. And let's put a box around that because we're going to need that. And remember, Coast Guard Academy, computed greater away. Is the computed greater? No. The computed is less. 51, 59 versus 52 height observed. So computed greater away, well, the computed is less. So we're going to go towards. So let's make space here. Towards. So the distance we're going to go is 14.7 minutes, or nautical miles, either way. Southeast. The sun was to the southeast when we shot it. We're at a latitude of 52 degrees, fairly far north. The sun's latitude was 16 degrees north, and the sun's longitude was 110 degrees. Our assumed longitude was 128. So yes, the sun was southeast of us. So this Z that we got out of the table is actually the azimuth direction, which is actually 151 degrees, measured from north round to the east and down to 151 degrees. Okay, so we have everything we need. And now we want to go to our plotting sheet. And I'm just going to put, I don't want to erase this because we need some of these numbers, right? What do we need? What numbers do we need? We need our assumed position, latitude and longitude. Okay, we need to start with that, assumed position. And we need the azimuth direction. We need the distance. We don't need our HC or our HO anymore. We just need the distance, the difference between the HC and the HO, which is going to be the different distance that we go towards this direction. Okay, so let's put our plotting sheet over here, and we can still see all the things we need, and they're all in boxes so we can find them easily. And let's create our plotting sheet here. Okay, the precision here will be a little bit less than what you want, but the ideas will be exactly what you want. Okay, here's our plotting sheet. We have a line across the middle, for our mid-latitude. Our mid-latitude is 52 degrees. And a line down the middle for our mid-longitude. And our mid-longitude is, well, it looks like we're closest to 129, closer to 129 than 128. So we'll make this 129 degrees west. Okay, longitude, whoa, look at that. Wow, that was slippery. We didn't put west here. We know it's west. You still write west. You still write it. You label everything. Okay, 122 west. And let's finish our box here. 128 west. 128, 55.2 west. Well, 129 is, so we're closer to 129 than to 128. So that's going to be our mid-longitude, 129. Okay, and then we take our compass and put the 0 mark right on our mid-latitude. And we make a small mark here. And that's going to be the distance between our lines of latitude. But we're going to make, so we have a little bit more accuracy, we're going to make each of these, let's see what that is. That's exactly 3. So we'll mark this off in 3-inch increments. And we're going to make each of these lines half a degree instead of a whole degree. 4, 27, 30. Okay, that should be plenty. Of course. Okay, and building our chart. Basically building a Mercator projection here. And down, that should be enough there. This is what you do. You can do this on a blank sheet of paper, or you can do it on a plotting sheet. If you have plotting sheets, that's great. It saves a few minutes. Okay, so we're doing these as half a degree. So we have a little bit more accuracy. 52 degrees, 30 minutes north. Whoa, look at this. Sloppy, sloppy. We didn't label it north. And this would be 53 degrees north and 53 degrees 30 minutes north. And 51 degrees 30 minutes north and 51 degrees. Okay, now our lines of longitude. Remember how we get those. Here's our mid-latitude. We get our compass up here, and we look at our longitude, our latitude rather. Our mid-latitude is 52 degrees. We go up the arc to 52 degrees and make a little slash mark right there. That is half a degree of longitude. If we made our latitude scale, if this was 1 degree of latitude, this would be 1 degree of longitude. But since this is half a degree of latitude, this is half a degree of longitude. Okay, and that is inch and, well, let's see, 1 7/8 inches. So we'll do our 1 7/8 that way, 1 7/8 that way, and let's go a few more so we make sure we stay on our created chart. 1 7/8, 1 7/8, and the same over here, 1 7/8 and 1 7/8. Okay, remember each of these is half a degree of longitude because we made each of the latitude lines half a degree instead of a full degree. And we'll label these. Now, of course, you know, you do this a little bit more accurately. I'm just doing them perpendicular by eye, and they're coming out fairly good, but not perfect. Okay, and here's our chart. Now, those lines of longitude look awfully close together, don't they? Well, at the equator, the lines of longitude would be the same distance apart as the lines of latitude. But at the North Pole, these lines of longitude actually are going to, at 90 degrees north, those lines of longitude are touching each other. There's no space between them right at the North Pole. They converge. And we're pretty far north, 52 degrees. That's fairly far north. So yes, it does make sense that these lines of longitude are getting closer and closer together. Okay, so we have our chart now. And let's label our longitude. 129 degrees west was the middle one. So going back towards Greenwich, well, let's go west further. It's easier to think. So 129 degrees 30 minutes, and this is 130 degrees here, and 130 degrees 30 minutes. These are west, right? West, west, west. Just writing the west where I can find space. Now going back towards Greenwich, we go down. So this is 128 degrees 30 minutes west. This is 128 degrees west. And this is 127 degrees 30 minutes west. Okay, so we have our chart created. The only thing we don't have is an accurate longitude scale. Well, we don't have a very accurate latitude scale yet either. We have to create that. But we don't actually need an accurate latitude scale. We could create it, but our latitude that we're using is 52 degrees. Then the only place where we're going to need an accurate latitude scale is to be able to measure the 14.7 nautical miles, the distance, 14.7. So we will create an accurate latitude scale too. Let's do our accurate longitude scale first. This is 30 minutes of longitude from one line to the next. Let's divide that in half. That's 15 minutes. And let's divide that in thirds. So each one of these little marks is 5 minutes. Let's label that 5, 10, 15, and all the way is 30. And then we better resort to a pencil here. Let's divide that into 5 equal marks. That's 1, 2, 1, 1, 2, 3, 4, 5 spaces there. So we have an accurate longitude scale now. Let's do the same for our latitude. This is let's do it over the side. That's halfway. That's 30. That's halfway to 30 minutes. So it's 15 minutes. Let's divide that into 3. 1, 2, 3. And each one of those is 5 minutes, 10 minutes, 15 minutes. And then let's divide that 5 minutes into 5 equal spaces. Okay. So we're dividing the 5 minutes into 5 equal spaces. And each one of those is 1 minute or 1 mile. Okay, so we're not dealing with I mean, this is pretty sloppy, really, but you know we're going to get an accuracy of half a mile out of this, even though we're using a thick felt pen and our lines aren't even perpendicular and everything will still be within half a mile. That's not too bad for doing this, creating this chart on a vertical surface and with rough instruments. Okay, now let's get our AP latitude on there. We're not concerned with DR latitude and longitude at all. Those are out of the picture. We weren't ever really there anyway, necessarily. They were guesswork. We're just concerned about our assumed position latitude and our assumed position longitude because those were the numbers we used to get our azimuth direction and our distance. If you go back to your DR latitude and longitude, none of it's going to work anymore. AP latitude, north 52, so that's right across here on our mid-latitude 52 degrees. And AP longitude 128.55.2. Well, that's west. That's just short of 129 degrees, right? That's our middle longitude. How far short is it? It's 4.8 minutes short of 129 degrees west. So we can take our dividers up here to our little longitude scale that we created. Don't use a latitude scale to measure longitude. That's an easy mistake. Latitude scale doesn't measure longitude. Okay? So we can take our dividers up to our longitude scale, 4.8, and take that distance there and bring it down to our latitude, 52 degrees, and we're short of 129 by 4.8. So we make a little slash, and right there is our assumed position longitude and our assumed position latitude. So we're going to write that right up here. Assumed position, AP, label everything. If you just put a latitude and longitude without AP, you really don't know what you've got. North 52 degrees. Write everything really clearly so anybody can read it. So you can read it yourself when you come back to it. 128 degrees, 55.2 minutes west. Okay, did we do that right? 128, 55.2. Yes. AP lat, 52. Yes, 52, 128, moving to the west, 128, 55.2. Yes, that all makes sense. We did that right. Good job. Okay, now our azimuth direction, our direction to the sun when we shot it in the morning, is 151 degrees. Does that make sense? Yes, it does. It was the morning. It was southeast of us. Great. Okay, 151. So we have, on a plotting chart, you'll have a compass rose in the middle of the chart. But here we just use our protractor. We have 90 degrees down to here, plus we need another 61 degrees. So we go to 61 degrees here. And then, remember, that's got to start centered right on your AP. You can't center it on the, the crosshairs of the latitude and longitude. It has to be centered right on your assumed position, wherever your assumed position is. Then we go down, that AZ is measured from north round to the east, just like we usually do with a compass. And so we have 90 degrees to here, and then 61 to here, and that gives us 151. And so from our assumed position to the star is going to be this direction here precisely. There's nothing guessed about that. If we had been here and the star was where it was with its GHA and declination, this was the direction to the star. That's mathematically correct and computed and everything. Okay, the distance based on the difference between our sextant site HO and the height computed out of the tables, the site reduction tables, the difference was 14.7 minutes. That's the same as 14.7 nautical miles. And you get that, if you take that from the longitude scale, you messed up. Longitude scale is only good for measuring longitude, differences with longitude. Nautical miles and everything else on a Mercator projection is measured using the latitude scale, where 5 minutes of latitude equals 5 nautical miles. Okay, so we want 14.7 for the distance. So let's take 14.7. That's almost all the way to 15. Well, let's measure from 15 down to 14.7. That's almost all the way. That last one is almost, we use almost all that. We take that distance. I better measure that more precisely. It's, our measuring devices are a little bit primitive here, but just, I mean, I have very good dividers and everything, but I want you to be able to see this. And we're going towards the direction to the star. Well, we shot it in the morning, so we're going southeast towards the star, 14.7 nautical miles. That's right here. Measured off of our latitude scale. HO is greater than our HC, so if the HC is greater, computed greater away, we would have gone away. Computed was less, so we're going towards, and that makes sense. Our HO was greater, which meant we had to go, as you go towards the star, the sextant reading gets higher and higher until you're right under the star and it's 90 degrees. So our sextant reading, our HO, corrected sextant reading, was greater than this computed. Computed greater away. If the computed had been greater, then we would have moved away. Our sextant reading had been less, but our sextant reading was more. That means we're closer to the star, and then so we move towards the star by the D distance, 14.7, measured on latitude, and then we do a perpendicular line across there, perpendicular to the direction, because the direction towards the star is the radius pointing at the star, the radius of a huge circle around the star. That whole circle, that immense circle, thousands of miles, is the actual line of position. We're going to approximate that immense circle with a single straight line, like so. And so here, let's zoom in there, so you can see what we've been doing. Assumed position. Here's our direction. 151 degrees. AZ equals AZ, azimuth direction. And of course that's true, that's not magnetic. All this is true. All directions are true. And the distance of 14.7, that's 14.7 minutes there. The distance, D equals 14.7. And here's our LOP, sun lower limb for GMT of 1920-14. Okay, that's our LOP. We're on that line someplace. And if we're going to do a second sun sight later in the day, doesn't matter how long that line is, just so our second sight crosses it. If we're going to do a second sight later in the day, we just take any point on that LOP. Let's say we're heading due west and advance that point. Let's say we sailed between our two sites, we sailed 30 nautical miles due west. We would advance this point 30 miles, that's 30 nautical miles, 30 minutes of latitude. Don't use longitude, 30 nautical miles, 30 minutes of latitude, 30 nautical miles. Take any point, advance it in the direction you sailed, by the distance you sailed, and here's that point, just moved over 30 nautical miles based on our DR, and then do a parallel line through that point, and now we have LOP sun, LOP 1, advanced. Then we take an afternoon sight, new AP, because we probably still have the same latitude, but all of a sudden our assumed longitude is going to be different. So we'll have a different AP. The latitude will probably be the same, unless if we had to due south, we might have gotten to a new latitude, but in this case we're heading west, so our latitude would be the same. Our longitude, our assumed position longitude, is going to be different because we'll have a different Greenwich hour angle for the sun in the afternoon, and we have to have our assumed position longitude fixed up so the LHA, the local hour angle is going to come out even. So we're going to have a new longitude for our AP. This is AP for the second site, and then we'll have computed greater away, or computed less would go towards. In this case, I drew it towards the sun. Sun's in the afternoon, going towards the sun, and certain distance based on the difference between the HO and HC. A perpendicular line representing our LOP from the afternoon, and where the two LOPs cross there, that's our fix. The advanced LOP from the morning and the afternoon LOP, that's our fix. The GMT time would be the time of the afternoon sight, and the GMT date. Okay, and then the last step, we take this position and now go to our ocean chart and find that position on our ocean chart and write the same information, fix, and in pencil now. All this probably in pencil, but definitely in pencil on your good chart. Write the location and the date and time, GMT, and fix. And that's where you are. If you're doing stars, you might have a third LOP coming in to check these first two, or even a fourth one. And if one of them's off by more than the others, you figure that one wasn't as good a sight. Okay, that's it. That's where you are. And so you're ready to go. And hopefully I'll see you out there. I'm just finishing off a 37-foot round-bottomed steel cruising cutter. That is very exciting. A boat that could potentially go anywhere in the world. So that's terrific. And we're all sailors here. We build model sailboats as well. Thousands of them. 70,000 model sailboats. Modelsailboat.com. So if you want to take a beautiful radio-controlled toy with you while you're cruising, to play with in the harbors, or to meet other people, as a fun way of introducing yourself, sailing around their boat 3 times and then sailing back, look us up, modelsailboat.com. By all means, if you have any interest in our boats or any questions about this, or just want to say, express your thanks for our doing this, happy to have you call us anytime or email. And so let me give you those pieces of information, and then we'll be signing off and leaving you on your own here. It's been fun. I feel like you're our personal friend now, and love to hear about your cruising plans. So email is fun@modelsailboat.com. And phone number is 360-684-2833. Okay, and I'll leave you with those. Let's just zoom in. That's actually my personal cell phone, but love to hear from you if you're a sailor. Okay, good night and good luck. Happy sailing.